Oh, you all are so ready to get going. You're so quiet. I'm just giving it one more second for the meeting to start. Okay, great. Hi, everyone. Thanks for joining and for coming so early on the last day. I want to just thank you for coming to the Harnessing Machine Learning for CESM cross-working group. Just to provide some general overview, the slides aren't progressing. Well, I'll just speak. Oh, perfect. Great, because I'm not good at speaking without slides. So I just wanted to bring up this slide that Dave Lauren showed at the beginning on Monday morning, and about the vision of going forward with CESM, and I think machine learning is really well incorporated within this model development lifecycle here, and in terms of improving our physical understanding, enhancing parameterizations, creating training data, et cetera, and I think machine learning has an important role going forward within NSF NCAR, and so I'm really excited to see all the talks and what people have been doing in regards to that space. We've decided to split the session today into three main points, just based off of the submissions we got. We're going to start off with the first little bit, talking about how machine learning has been used for parameterizations. A lot of this is focusing on the LEAP and M-squared lines work for our system models. The second little bit, we'll talk about machine learning emulators and physical constraints incorporated within these emulators. And then lastly, talk about how machine learning models are trained on our system model data to do awesome, really cool science. So the first half is actually going to be purely machine learning for parameterizations. Then we're going to take a break. There's snacks and coffee. And then the last two sections will be before lunch. And so I don't want to take any more time other than just to say, speakers, as a reminder, you have 8 minutes for your talk with 2 minutes for questions. Once you start going in those 2 minutes for questions, you'll see me in the front for the first half and Linnea in the front for the second half put up a peace sign to let you know you have 2 minutes of your time left of your full 10-minute total. So just to wrap up so you have time for questions. And with that, we can move to our first speaker.
Thanks, Kirsten. So this first session is going to be on hybrid ML, and this builds off of a workshop we had last week where we worked with our colleagues from Veronica Eyring's group at DLR. So I'm very pleased to introduce our first speaker, Julian, who is leading the efforts to build the hybrid version of the ICON ESM. Thanks, Julian.
Perfect. Yeah. Thank you, Linnea. Thanks for having me here. This is probably going to be one of the very few talks during the week where the word CESM will not be pronounced. What I'm going to talk about is our effort to develop a fully hybrid version of the ICON model. So hybrid, we implement machine learning along with physical parameterizations in there. Before starting, I would like to thank all the persons who contributed to this talk in a way or another. I would like also to thank Linnea and Dave and all the CSM MLE implementation group. They welcomed us last week. We also visited last year. This has been a very fruitful collaboration so far. And to finish, I would also like to acknowledge the European Research Council for the financial support through the US-MILE project. Tiny bit of background here. So as you know, Earth system models have improved over the years, and this is evidenced by the successive iterations of the CMIP project. But all these models still suffer from strong structural errors and systematic biases in their climate projections. It's in this context that the USMILE project has been designed with the idea of replacing components of Earth system models by machine-learned components. And this has been very successful for us so far. So I highlight here in the lower part the general workflow that we've adopted during this work to develop various parameterizations. So it all starts with, of course, targeting a particular quantity, a particular process. In this case, I took as an example the cloud cover. We need then to identify potential input features to our network by using either our knowledge of the process or XAI techniques. So that has been working very well for us. And then, starting from a high-fidelity data set, in this case, it's a high-resolution global simulation. I think that comes from Diamond. So we take this data set, we coarse-grain the data to the target resolution, design our ML model, our network, or whatever technique we use. We train it, and then, of course, we eventually need a proper evaluation, both offline and online, of the model. So we've applied this workflow to various parameterizations. I'm just going to give you a couple of examples here. The first example is a cloud cover parameterization again, but it takes a different form from the one I showed you before. In this case, it takes the form of a simple equation that was learned, that was discovered from the high-resolution data set using symbolic regression. And this has two very big advantages. One of them is that the equation is directly physically interpretable. I highlight here one of the terms in the equation that depends directly on the vertical gradient of the relative humidity, and if you map that term, then you see that it's particularly active in these stratocumulus regions. So we expect that term to have a direct effect on reducing biases in cloud cover in these regions. A second very important advantage is that it contains only 10 free parameters, as opposed to 1,000 or thousands of millions of parameters for a large network. This makes it directly tunable, so we can directly calibrate the model once it's implemented in ICON. So this is what we've done. And we have been able to run 20-year-long AMIP simulations with this retuned hybrid model. So here I show you just a very small sample of the results we obtained. We compare here the total cloud cover biases on the left in the hybrid ICON model and on the right in the baseline model. Both have been retuned. And clearly we see an improvement in the total cloud cover biases over these regions here, stratocumulus regions. So blue means a deficit in cloud cover, which we don't see in the hybrid version of the model. We took that one step further and tried to do some sort of idealized warming experiments by applying a plus 4K SST globally. And although it's hard to say whether the results are good or bad, what we can tell is that the results are going in the right direction. So the model learned something physical, like meaningful physical relationships. Second example that I wanted to show you is a machine learning model for convection. So we took a slightly different approach here, using super parameterized data as our baseline. And Helge Hoyer, who is in the room here today and who did the work, designed a quite complex network to parameterize that, a network that allows us to actually maintain coherent in the vertical column. So convection is a column-based process. And he also introduced a couple of tricks to guarantee that the model is stable online, that it's accurate, and that it's also physically consistent. One of these tricks is to actually allow the model to predict its own error. So we have access during online inference to the error of the ML model, and Helge introduced this clever mixing between the ML parameterization and the conventional one, just to avoid introducing too large errors from the ML side. With this, Helge was able to run so 20-year-long stable AMIP simulations, which is already quite an achievement. And he was able also to show that and demonstrate that the ML model behaves pretty well. So we captured the correct patterns of precipitation over the globe. We saw some improvements in the extremes, also in the precipitation extremes. So if you want to know more about the scheme, you can talk directly to Helge. He has a poster upstairs. These are just a couple of examples of the schemes we developed and implemented. But of course, it doesn't stop there. Here I show you the overall concept for our V0 version of Icon XPP-MLE, so the hybrid Icon version. On the left here, I list the different parameterizations that we are targeting. So in green are those that are already implemented and working. In gray are the ones we are still working on. We have also in there a couple of ML components in the land module of Icon, one for the stomatal conductance, which is implemented, and one for phenology. So this is the baseline for our V0 Icon XPP-MLE model. Just one word to say that we are always trying to keep up to date with the model version that will be used for all the Sim7 contributions, just so that we do not lag behind and we're able to run these simulations when the time comes. Interestingly, just right before coming here, I've been able to, I've tried an experiment where I actually activated most of the ML-based parameterizations we have available in the code. So that includes a cloud cover scheme, a convection scheme, a convective triggering scheme, and the stomatal conductance scheme. And with all of this activated, I ran a 5-year-long AMIP experiment. So I won't go too much into the details here, but we were actually quite happy to see that the results are already very good. The radiative balance at the top of the atmosphere is actually not that bad. Oh, yes, I need to point to the screen here. It doesn't work anymore. And the overall model performance is also very good. So that's what the portrait plot down here is showing you. Oops. Yeah, now it's back. This is my last slide, just to highlight the overall roadmap towards developing operational hybrid Earth system models. So at this stage, we have worked extensively on the first part, so designing individual ML-based parameterizations. We are now at the end of this second stage, implementing them into Icon and evaluating them online. But there is still some work to do. For example, next, once we have all the parameterizations we want in there, we will want to recalibrate the hybrid model. So I won't talk too much about that. Max Bowman, who is here, will give a talk later today on this, so presenting our tuning strategy. And once we are there, the ultimate objective will be to couple the model to the ocean and run CMIP7-like experiments, both AMIP, but also historical and eventually scenario-based. I think that with that I can finish, and yeah, I'm happy to answer your questions. Thanks.
Thanks for time. I think we'll just take one quick question as we transition. Our next speaker is Adisu. Do you have a quick question for Julian?
I was just curious about the, I might not have the words right, but like the symbolic regression where the machine learning is, when you're running the model, then is it the machine learning, is the actual equation being run, or is the machine learning emulator being run, and then it's just telling you this is the equation that it's using?
No, so the equation was learned offline.
Okay.
On the high resolution data set, and then once we have the equation, like implementing it into the code is super easy, and we just run it iteratively online.
Okay, cool, great, thanks.
Yeah, you're welcome.
Thanks. Our next speaker is Adisu Sami, who's a LEAP associate research scientist working here at NCAR. Take it away.
Okay, thank you, Linia. Today I'm going to talk about one of our parameterization that we replaced warm rain microphysics, and specifically talking about how it improves extreme precipitation. Yeah. So first, I would like to thank all my collaborators. So this work is just part of the bigger CSM MLE. Like this is one component that we are trying to replace. So in the CSM MLE, we have different components like radiation, warm rain, convection, different components going to be replaced. But here, what I will try to show is just replacing the warm rain microphysics and study how this is changed, like what is actually changed when we are replacing this parameter. So one of, like, in our workflow, the first thing that we wanted to identify is where do we get the most bias, like in the CSM model. So as you might know from the IPCC report, we know that one of the biggest uncertainties in Earth system models is effect of clouds, especially process related to the rain formation. So higher fidelity rain formation, like beam schemes, can be used. But this kind of scheme, even if they can improve, they are computationally expensive. So the tau ML or the machine learning-based parameterization can improve representation with minimum sacrifice in computation. So the warm rain microphysics is just a component of the microphysics scheme. The microphysics MEG2 scheme is within the club scheme, and the warm rain microphysics is represented by this bulk microphysics equation for the auto conversion and the accretion. So they are represented by this equation. So this is the KK 2000 scheme. So what we did is we just replace this part with ML parameterization. So the question that we wanted to address is, once we replace the ML scheme, do we see improvement in representation of extreme precipitation? And the other thing is what we want to see is what physical mechanisms drive the difference in extreme precipitation compared to the traditional KK 2000 scheme. The other one is we wanted to see how we can tune this so that it can better represent the extreme precipitation. So the first thing, once we insert the ML parameterization, the tau ML, we just see the distribution of the precipitation. So here, what we are seeing is the distribution of precipitation. It is compared with the observation. Here we use the IMERGE and CMORPH as observation, and we use the default parameters here. So there is no tuning at this point. And we notice that there is a little bit of improvement in representation of extreme precipitation. This improvement, as you can see it here, like in the lower panel, what we are seeing is the large scale precipitation, and the other one is a convective precipitation. So the difference mainly comes from the large scale precipitation. So what we noticed is once we plug in, we noticed an improvement in extreme precipitation, and this improvement comes from the large scale precipitation. Then we also see the frequency of light precipitation. So here, what we can see is like the comparison of the the comparison of light precipitation, like this total precipitation, is compared with the IMERGE dataset. And the orange one, which is the tau ml, shows improvement compared to the KK2000. And we noticed that this difference or this reduction in light rain frequency mainly comes from the large scale precipitation. So we didn't see much improvement in the convective precipitation as we expected. The other one is when we look at the spatial distribution of extreme precipitation. So for each grid point, we calculate the extreme precipitation. And when we look at their distribution, we notice that the tau ml, the first one is for the tau ml, then we have KK2000, and this is their difference. So what we noticed is there is spatially, like we can clearly see there is enhancement in extreme precipitation in tau ml compared to KK2000. Mainly, we noticed this over the ocean. Then we wanted to see what is actually changed by looking at the vertical profile of rain mixing ratio and their tendency terms. So here we partitioned the values into their different percentile, like starting from 10 percentile, 15 percentile, and 99 percentile. And we noticed that the main difference is obtained when we have extreme precipitation in the 99 percentile. So the rain rate for the tau ml is higher compared to the KK2000. And we can also look at the tendency terms. We notice that there is a positive tendency terms. So here what we notice is tau ml extreme event maintains substantially higher rain rate compared to the KK2000. I have to move faster. So the other one is we wanted to see the efficiency also, the conversion efficiency, the efficiency of converting whenever there is a cloud condensate to rain rates. So this figure shows how the conversion, the efficiency is different compared to KK2000. So there is enhancement in the conversion efficiency with these two schemes. So the other thing we did is we ran 100 ensemble members, and we wanted to see how the large-scale precipitation varies. So here what we are seeing is the distribution of precipitation. So the orange is with tau ml, and the blue is for the KK2000. So what we noticed is, so these are sorted with domain mean precipitation. So as the domain mean precipitation increase, the difference between the tau ml and KK2000 is it's becoming significant, and there is more enhancement in extreme precipitation with tau ml with higher domain mean precipitation. And this difference mainly comes when we see the correlation. This difference mainly comes from the convection parameterization. The top three convective parameterization is the ZMconf TK add, ZMconf cap limit, and ZMconf DMPTZ. So that means this plays a great role in like dictating the partition. So what we noticed is, I don't have time to explain this, but what we noticed is whenever convective precipitation is like enhanced, or if the parameter is favoring the increase in convective precipitation, the large scale precipitation is decreasing. So they have opposite sign. So that means they are competing for the resource. Whenever there is, when convective precipitation is enhanced, the large scale precipitation is decreasing. And after that, we conduct various simulation to better tune the precipitation extreme. So here what we are showing is a series of experiments, simulations, PPE simulation, trying to improve the representation of extreme precipitation. Here, what we can see it is sequentially, like it tries to improve the representation of extreme precipitation. We use history matching to get a better configuration. And from this configuration, we noticed that we got one of the tuned configuration properly captures the representation of extreme precipitation, which is very close to the emerged distribution. Yeah, so I don't have time. Okay, thank you.
Thank you, Adisu.
Yeah.
For the sake of time, we're going to transition, but catch Adisu in the hall after for questions. Xavier's next.
Okay, good to see everyone here this morning. So here I'm going to be presenting a neural network deep convection scheme that we tested in CAM6, and I'll show you some of those results today. First of all, what data set did we use to actually create a deep convection scheme parameterization? So what we did here is that we used a storm resolving simulation, meaning 4 kilometer horizontal resolution, and that simulation was run for about 40 days, and we retained 30 days for the training. And the way we trained that convection scheme was through a coarse graining approach, meaning we conservatively remapped that high resolution data into coarser resolution data on the CAM6 grid. And then we defined the grid scale and subgrid scale component of tendencies and fluxes. And then we applied a optimization to best fit the data with our neural network. The neural network has four inputs, 2 column vectors, which are temperature and non-precipitating water, as well as land fraction and surface pressure. The land fraction and surface pressure is to account, is to tell the network whether you're over land or ocean, and whether you have mountains or flat land. The output of this network are subgrid scale fluxes and macrophysical tendencies. I'm not going to go into the detail of those, but effectively what you're doing here is that you have when you create such a scheme or any convection scheme, you want to close a energy and moisture budget, and so what we're outputting here are basically the terms that are necessary to close that moisture and energy budget. The way we did this convection scheme is that we outputted fluxes when we could, and that's to ensure that you have column-wise conservation of properties. Hence, we're conserving water and energy in this scheme. The important thing to understand here is that we're keeping as much as possible of CAM6. We're substituting only one scheme, which is the deep convection scheme, the Zhang-Markvalin scheme, which is a diluted plume model scheme. All the other schemes, the club scheme, the cloud macrophysics scheme, and others are fully active. And in order to limit our deep convection scheme to really represent deep convection, we set up 2 criteria. First of all, when you run that scheme, you need to have some form of precipitation. Otherwise, we assume that there is no deep convection and the scheme is turned off. And the other criterion is that we compute a local CAPE, convective available potential energy, which is something that other convection scheme does, including the Zeisenberg-Flain scheme. And if that CAPE is too small, meaning there's not enough instability built up in the column, then our scheme is also turned off. The implementation, I won't go through it, but goes through different stages. You taking the input from CAM6, so the temperature, moisture, and the surface vectors, and the surface scatterers, and you grid that into the same vertical coordinate system as the neural network. Then you produce your output, and then those outputs are gridded back onto the CAM6 grid, and you then produce all the tendencies that you need, and that are then communicated to the rest of CAM6. Here I'm going to show you two setup for CAM6. So we ran 9 years, but I'm only going to show you 8 years average. This one setup is the default CAM6, which is CAM6 with Zeisenberg-Flain, and the other setup is the CAM6 with the neural network convection scheme that I just presented. And we'll compare that with observation. Let's look first at the annual mean climatology for precipitation. So the top panel shows the iMerge, the observation. And then the two bottom panels shows the anomalies of each of those CAM6 setup with respect to iMerge. So blue color means too much rainfall compared to iMerge, and red means not enough rainfall. So the bottom line is that we found we're reasonable agreement, although the biases that we have are somewhat worse than the default CAM. The main reason we think is that we actually did not recalibrate CAM6 when we introduced our convection scheme. Hence, we would not really expect to do much better in terms of climatology, because the default CAM6 has been finely tuned to capture this type of broad scale patterns. Nonetheless, with very little tuning, we do find a reasonable pattern and anomalies that are not that bad either. Now let's look at the zonal mean. So I split the zonal mean into all region and then land only and ocean only. The green line shows the CAM and N, so the neural network, and then red is CAM ZM, blue and is iMerge, and GPCP is magenta. Bottom line is that we overestimate somewhat rainfall over the deep tropics. We believe this is due to an ice cloud issue that needs to be retuned. However, over land, we actually have very good results. Better, I would say, than the default CAM. So that's promising. Now, I think where we really do a lot better are into variability, like subseasonal variability. So what I'm showing you here is the PDF, so the probability distribution function of rainfall split over tropical land and tropical ocean, meaning areas between 30 degrees south and north. As you can see, our scheme does very well compared to iMerge. It reduced substantially the drizzle problem that you have in the default CAM, and also does a lot better for the extremes, which are severely underestimated in CAM6. The diurnal cycle also is something that we're doing better. So the top is the peak hour of rainfall from 0 to 24. In overland or in observation, usually it peaks in the late afternoon. We retrieve that to a large extent in our scheme, while in the default CAM, a well-known bias is that you have a mid-afternoon rainfall peak. So we're also doing much better in that aspect. I'm going to skip that. And then I'm going to maybe conclude with tropical wave spectrum, which is also a very important criterion. to look at. So these are Wheeler-Kiladis plots. Basically, on the left, you have the observation. The cam NN, which is the middle, does better at representing Kelvin waves, which are here. Oops. Oops. Okay. They do better at representing Kelvin waves and Yanai waves. They do miss out on the MJO to some extent, but we did some testing in a couple run, and we find that actually when you couple our cam NN with interactive ocean, we do retrieve the MJOs that you also find in the default cam. But we think that actually the phase speed that we have, the group speed of those MJO are better represented here than in the default cam, but more analysis is needed in order to reassess that. So in summary, we have a deep neural network that represents convection. It seems to do fairly well, especially for precipitation variability and the diurnal cycle, and we look forward to implement that into the couple run and CSM3 also. Thank you.
Great, thanks, Xavier. We don't have time for questions, but we're going to transition now to an online speaker. And while we do that, I just want to highlight that this is our third session on ML for CSM, and it's exciting to see that last year we were seeing all these parameterizations developed offline, and this year almost all of the talks will be parameterizations coupled to a model run online. So I think that's exciting progress to see. Okay, transitioning now to ICE. Yep, go ahead, take it away.
Oh, wonderful, thank you. 1 second. Cool. Thanks, everyone. My name's Geraint Webb. I'm a student working with Cecilia Bitts at the University of Washington. And I'm here today to show some of our latest work on leveraging machine learning to reduce the computational cost of sea ice wave fracture. So I also just want to give a quick quick shout out to my co-authors, Letty and Dave. So first of all, I want to define a few terms. So we know that wave fracture is a tendency within the flow size distribution, this FSD. And so first of all, I want to define a flow for people who are unfamiliar. So a sea ice flow is a frozen piece of seawater. It can vary anywhere from a few feet to several kilometers to 100 kilometers. And it can come in all shapes and different sizes. So the flow size distribution quantifies the probability of observing a flow of a given size over a given domain. And so if you look here from the prognostic flow size distribution from Roach and Horvath in 2018, that's implemented within SICE. On the y-axis, we have a number distribution, and on the x-axis, we have a flow radius, and you can see what the flow size distribution generally does. It represents a lot of very small flows across a hemisphere and not so many very large flows. There's a bit of a tick up here, and this is called truncation, but I'm not really going to get into that today, but we've done a lot of work on this. And so wave fracture is one of many processes that evolve this shape. And so by default, we have 12 different flow size bins, and these are all predetermined. And there are 5 other processes in wave fracture that affect the flow size distribution. So these are, and I'm going to go through these very quickly in the interest of time. These are new ice creation, lateral growth, lateral melt, welding, which is the coagulation of flows, wave fracture, which again I'll get into more in a second, and flow deformation. And so wave fracture occurs when you have waves hitting incident to a sea ice flow, causing the sea ice flow to bend and then ultimately fragment. And the reason that we're so interested in emulating wave fracture over all of these other processes is that wave fracture is very, very expensive. And I hope you'll get to see why this is very soon. So how is wave fracture currently parameterized? We're going to be using the Tremblay and Roach 2026 scheme. It's currently in review. They encourage me to, if anyone's interested, to send it out to give a preprint. So please do feel free to ask. But it's currently just a numeric scheme. And so the way that it works is that we have these 12 different flow size bins ranging from very small flows that may only be a few feet out to a kilometer in radius. And so the scheme solves a 4th order ordinary differential equation. And what it does is it goes through and every time it calculates a strain. And with that strain, it asks a very simple question. Asks, does this flow exceed the critical strain required for fracture? So you could imagine if we had very, very small flows, that would always be, or very, very small waves, with very little energy, that would always be a no. But if you had very large waves with lots of energy, that would always be a yes. There's also a chance where it might be a maybe, and this maybe is dependent on the state of the ice. So if there's lots of cracks, maybe the flow will fragment. Then, if it's a yes, it will exceed this critical strain, or if that maybe becomes a yes, we then calculate how the flow fractures. So for each one of these different bins, the code is going through iteratively and calculating how each individual flow will fragment. And so what this means is that for one flow is representative of all flows in a grid cell. So one 200-meter flow would be representative of all 200-meter flows, say in the Beaufort Sea, in the grid cell in the Beaufort Sea. And so what you can see here is that we then calculate a fracture histogram that then says, where does that area go? So in this case, 60, if you fracture for some random waves of bin 11, 60% of the area, 35% of the area is going to go into bin 6, 25% to 7 and 8, and 15% to bin 5, and so forth. And so this process is iterative, and it's going to keep going around and around. It's going to ask, again, the same question: does the flow exceed the critical strain for fracture? Yes, no, potentially. And then it's going to calculate a fracture histogram for all of these different bins. And so why this is so important to emulate is that resolving flow bending requires a very fine grid, about 4 meters spacing. And in fact, that might even be too coarse. So the largest flows dominate the cost. And in our work, we wanted to model flows that aren't a kilometer in radius, as is the default in CEIS, but are 25 kilometers in radius, so 50 kilometers across. So you can imagine if you have a flow that the very largest flow is a kilometer across, it will be discretized in this fourth order ordinary differential equation with spacings of dx equal to 4. So if you have a 2-kilometer grid, that would be a 500 grid points for this fourth order ordinary differential equation. However, if you want to look at a flow that's 50 kilometers across, 50 kilometers in diameter, and still have dx equals 4, you're now going to have 2,500 grid points. Oh, sorry, not 25, sorry, 12,500 grid points. And so you can see that this very, very quickly can jump up the cost and become a lot more expensive for these equivalent setups. And then if you want to use an even finer grid and resolve the bending even better, or even more thoroughly, or even at a finer scale, with dx equals 2, it's now 100 seconds model day. So you can see it becomes very expensive very quickly when we want to model these very large flows that we've been interested in modeling. And so we're going to try to use an emulator to do that. And so to do this, we're going to build on the work of Leddy Roach and Chris Horvat in 2022, and we're only going to emulate the 6 largest flow size bins. And so what this is going to mean is that we're going to have a separate emulator for each of these 6 different bins. And so the first thing we're going to do is we're going to have a classifier. And so what this classifier is going to do is it's going to take in a wave spectrum, it's going to take in all the wave phases, it's going to take the CI thickness, and because it's going to be for each flow size bin, it's going to have the implicit knowledge of how big each flow size is. And it's going to ask a very simple question: is it going to fracture, or is it not going to fracture, or might it fracture? And it's going to use about 50 inputs with 2 hidden layers with 32 nodes in each layer, and we got around about a 97 to 99% accuracy. And we used about 1 million training samples for each network. And so what we did was we ran the model for about 6 months, and we just took at the time step information about what the strain was calculated to be, what the flow histogram was. Now, if maybe is triggered, we then have to know if it will exceed the critical strain. So we just do a very simple regression. Again, it's a very similar setup. We have the exact same inputs, except this time we only have one output, and this is just going to be the critical strain, or the strain, sorry. And then we can compare and see if it exceeds this critical strain. So if this maybe turns into a yes, we can then do another regression, a third network. So this is 3 separate networks within this emulator of CEIS wave fracture. And this will then take exactly the same inputs, and then we'll calculate a fracture histogram here. And so what you can imagine is for these 6 different bins, for each one we'll have a network for the classifier, we'll have a network for the maybe regression, and then we'll have a network for the fracture histogram regression. So that's 6 different flow bins, 3 networks for each. That's 18 different networks that we can then place within CEIS. So just as an example of what this might look like, in the orange we have the truth, and in the blue we have the prediction. These are just the same examples I showed on the 3rd slide or 4th slide. And so what you can see here is there has been some skill, but obviously these are cherry-picked to look lovely. So I'd like to try to convince you that it works nonetheless. And again, for the 10th bin. So what we do is we then just take this parameterization and throw it in with size 6. We couple it with WaveWatch 3. We're going to use those very, very large flows. So that's the comparison we're going to be making. We're going to do a 5-year run. On the first year, we have the training data, but the remaining of the 4 years are completely separate. And we're going to see what happens and see if it works. And so on the second slide, you'll remember that I showed you the flow size distribution. What it looks like, it's a number distribution plot like this. And so what you can see is that we end up with a very, very good agreement between our control and our emulation. So, which was excellent to see when you integrate across an entire hemisphere. But obviously when you integrate across an entire hemisphere, you might be losing some information. So when we look at this mean flow radius, so this is the average flow for a given grid size, the average flow size, you can see that there's very little difference in these plots. We're looking at Southern Hemisphere September of only the 5th year. And so what you can see is in yellow is very large plots, in blue is very small very small flows, sorry. And then what you can see is there's only very small differences spatially, which was really excellent to see. And then finally, so you can see that for the setup before, for dx equals 2 meters, we had about 101 seconds of model day. And then for the same time period, just to analyze it, we got about, using this machine learning, about 6 seconds of model day, which was fantastic to see. So we managed to maintain fidelity and speed up the model. And so with that, I'll just leave out my conclusions. In the interest of time, I'll take any questions. Thank you very much.
Thanks, John. We have time for one quick question. Well, it's exciting to see the speed up. I know that our CSM modelers will be excited. We'll transition now to Rashid, staying in the ice regime, but moving to land. Rashid Matai will be talking about the development of a ice sheet parameterization.
Oh, how do I?
The laser pointer, you hold that down and point at the screen. It takes a while.
My slides. Oh, okay. Oh. No, I'm. Uh, yeah. Good morning, everyone. I'm Rachit, a postdoc at Columbia, and I'm going to be talking about testing machine-learned basal friction relationships for ice sheet modeling. The goal here is to come up with a non-static, data-driven parameterization for basal frictions. Okay, a little bit of overview about ice sheet modeling and basal sliding in general. So as ice moves downhill, there are like two ways that it moves. Like one is internal deformation, which is ice deforms internally, and the other is the ice block itself, like the slab itself, like slides over the bottom. So in the regimes that we're interested in, especially in like faster moving ice streams, the sliding at the bed is what dominates the flow. And as you can imagine, like friction resists this sliding. And this is like the friction that we are interested in. And now this friction can depend upon a lot of different things, like, if there's like water at the bottom, if there's like sediment, what's the bed roughness, and you can imagine like n number of different things. The important thing to note here is that you can't actually resolve all of these things or like measure everything on like a continent-wide scale. So this is where basal friction relationships come into play. So we essentially like club together the effect of all these things in like one relationship, which acts at the bottom of the ice. So you can imagine that, so if this friction relationship is like low, it means that the ice is going to slide faster. Versus if it's like higher, then it's going to, not slide as fast. It is also important to note that we are clubbing together a lot of different effects, which may or may not be actually acting at the bottom of the ice itself into this relationship. So what does the current practical workflow look like in a simplified way? So currently, like we use satellite observations, which can look at how fast the ice is moving at the top surface, and then we infer what this quote-unquote like friction at the bottom looks like. So this is essentially like an inverse problem. And you see, I've used C to represent basal friction, and I'll use these interchangeably for this, for the intent of this presentation, but they can be a little bit different. So you invert for this basal friction, and then you essentially run the ice sheet model with this fixed basal friction. So the problem with this is that, I mean, it works really well, but it is based on current observations. So what if something changes, right? Like the ice thickness, you can imagine, will change because ice is moving, so the ice thickness over every, say grid point or every local location will change as the ice moves. The water beneath the ice could also change. So you can imagine like n number of reasons why this friction relationship, or rather like the C value, should not remain fixed. So, so what we want to do is like, we want to test a very simple ML closure idea, which is like, can we actually relate this basal friction relationship, I mean, this basal friction coefficient with like some observables, which may or may not be part of the ice sheet modeling state. So these observables could be something as simple as the thickness of the ice, or gravity anomaly, magnetic anomaly, anything that you can think of. And you can also think about this, I mean, you can also think that this would be important in like paleo simulations, because in those simulations you don't have access to, say, like satellite observations. In like deglaciated regions where you no longer have ice, right? So you would, I mean, if something like this works, then you can actually like get back this basal friction relationship. Okay, so a little bit about what we tested. We're confining ourselves to these glaciers in West Antarctic region, specifically the Edmondson sector, and the three glaciers that we're going to focus on are the Pine Island, also known as Pig Glacier, or sorry, Pine Island Glacier, also known as Pig, Thwaites, and the Dodson and Crossan system. And these regions are close to each other, but they are very distinct in certain ways. Now, the workflow is you invert for C using, say, adjoint optimization or something else, whatever you want, and then you train this MLP and try to form a relationship between this inverted C and then like use this basal friction relationship in a forward simulation, or like a regular ice sheet simulation. The idea is that you train on, say, like 2 of these glaciers and then like test it on the third, or like train on one and test it on the other. So essentially you always try to test it on like a holdout region. The idea being that if the relationship that you learned is like truly universal, it should apply everywhere. So what worked and what did not? So before I actually get into this, we considered a lot of different features, quote unquote. Some were geophysics features, which means that they're properties of the bed. So basal, basal roughness, or the slope of the bed, or like magnetic anomalies, gravity anomalies, which represent certain states of the bed, or like ice-based features, which is basically just like ice thickness, or like the slope of the ice, or things like that. And then mixed features basically means that you combine them together. So in all, and we also tested on, like I mentioned before, you train on 2, test on the other. So in all, we tested like 100 different combinations. And here I'm showing only like 2 of them. So on the top right, you see like a model which is trained on like 2 of the glaciers and tested on the entire region. And on the bottom you see a model which is like trained on just like 1 region and like tested, one glacier and like tested on the rest. So what we found out was that geophysics based features only got you to like 53%, on an aggregate towards like the inversion-based velocities. We compare with the inversion-based velocities because those are like the ground truth, like the best our model can do. So essentially, what this means is that, and then like if you use mixed features, you give it more, you give the basal friction relationship the most amount of data, and it does the best. So the interpretation here is that yes, the ML closure is learning something real, but the performance is dependent on like the training region, flow regime, and it doesn't seem like, at least based on the feature sets that we considered, that we were able to capture everything. Okay, so what were the key challenges? So the first challenge was that the reason this failed was some of the regimes were out of distribution. By that I mean that like if you trained on one region, the other region had like feature sets which were like completely out of distribution, and ML obviously like fails in those regions. So that's not a unexpected thing. But the more important thing was like in distribution error. So even in regions where your feature sets like lied in the distribution of the trained data set, we still failed. So this means that it's not just the architecture of the network which is like which is lacking, but it's also that the input variables or the feature sets are like not enough. So what are we looking at? How are we addressing the challenges right now? So we are looking at incorporating like better features, such as those highlighted there, and we're also looking at non-local formulations, such as like graph neural networks, so that we can use non-local features. Okay, I guess I'm like out of time, but that's about it. Thank you.
Thanks. Yeah, we'll transition now to the ocean. Our next speaker is Jacqueline.
Okay, well, thank you. Good morning, everyone, and thank you for the invitation. This work is done in collaboration with scientists from M-Square Alliance and also scientists here at NCAR. So I just wanted to acknowledge that. Okay, so the main objective of the project is to change ocean mixing and see if we can have a better representation of the two most important tropical phenomena, the Marine-Julian Oscillation and El Niño Southern Oscillation, both from a physical perspective, just looking at clouds, air-sea interaction, and how the MJO, as it propagates over the Western Pacific, interacts with different phases of El Niño. So to better understand how these two phenomena interact, we need a good representation of these processes in a coupled model, because these two tropical phenomena are inherently coupled. So there are many ways to do that. One of the ways is by using machine learning to refine poorly constrained physics. So in the model, we usually represent vertical turbulent fluxes as a set of equations. And here I'm just, let me see. Okay, so we have a non-local component that's a downgraded mixing, and we have a non-local term that's, it represents these convective clouds that are of the size of the boundary layer depth. So very simply, this K that you see here, it's a boundary layer diffusivity that's a function of ocean boundary layer depth, turbulent velocity scale, that's kind of a size of like how big eddies are, and then this G shape function, that's a non-dimensional vertical shape function. And in KPP, which is the ocean parameterization that the parameterization we use for in MOM6 in CSM3, a default option is a simple shape that's basically a cubic expression that's shown there. This cubic expression is invariant. We use the same equation for pretty much every grid point in the ocean. So the objective is that by changing this shape function that will be sensitive to atmospheric forcing, we might have a better representation of mixing, which then can lead us to a better representation of ENSO or MJO. Okay, so there has been previous work on using machine learning to refine these constraint physics, and so Sane et al. And these are scientists and collaborators from M-squared lines. They have developed neural networks that are predicting this non-dimensional shape function, but also the vertical scale. And the same scientists and co-authors have equations that instead of using these neural networks that are a bit more expensive, now they can have mathematical expressions that we can easily add to KPP and MOM6. So this is how the implementation looks like. All of these equations are equations that come from machine learning algorithms. And so what I essentially did is just I implemented this in KPP. And the nice thing about this is that it responds to atmospheric forcing. So here I'm just going to show you how it looks like. The black line here is showing the simple shapes. This is a default configuration. And so the blue line is showing a shape function for a grid point close to the equator. And you can see that the shape function now it's moving. So we have more mixing closer to the surface, closer to zero. And I have another shape in red that's showing the shape function for a point during unstable conditions, much over the extratropical regions. So you can imagine having lots of different atmospheric forcings. We can have different shape functions that can then translate to mixing. We're using a set of experiments from the CSM3 version, the latest version. So we have ocean-only simulation, and I have also a fully coupled simulation that I'm running it over 35 years. I'm only analyzing the last 30 years, and I'm going to compare this with observations. So as I said, we've changed the shape function. So instead of having this green-blue line, now we're having this much deeper shape function here. So this is the beginning of the project. So we want to, the main equation is just like use the equations that we gathered from a previous work and see what can go right or what can go wrong. Okay, so looking at mixed layer depth. Here I'm showing you PDFs from monthly climatologies for winter and for summertime. During winter time, we don't really see much of an improvement on the frequency of this of the variability of the mixed layer depth. But nicely enough, during summertime, we see that adding these shape functions, we're getting much deeper mixed layer depths. It's taking us closer to observations. So that's nice. Here I'm showing you a map where I'm highlighting these blue regions where we're seeing an improvement on SST that comes from deepening the mixed layer depth. And in orange, I'm showing locations where we're getting an improvement on SST that comes from shallowing the mixed layer depth. And as I said at the beginning, I'm interested in having a couple model that's able to represent both the MJO and ENSO. And if you look at here, we are seeing a lot of improvement over unstable conditions in the extratropical regions, but I don't really see much change over the Pacific, which is sad. So here, here for me, of course, but here I'm looking at ENSO, and this is just a regression plot of El Niño 3.4 with SSTs everywhere, and as you can see that, yes, we're not doing that bad, but don't get fooled because now I'm going to show you the standard deviation of the Niño 3.4 region for each month. And here in black, I'm showing the observations, and I'm also showing the other set of experiments. And you can see this red line here is the coupled ML version, and we're having a dramatic drop in the standard deviation, especially from June all the way to December, which means that we're basically dampening El Niño signal in the equator. And so, and you know, it's like this is what leading me like what can go wrong. So just looking at the equations, I didn't explain in detail the implementation, but we have this set of equations that depend on Coriolis term and surface buoyancy and wind stress. And so when F is close to 0, very close to the equator, the shape function is peaked, is stuck at 0.1, which is very close to the surface. So this is 5 meters. And so we're essentially limiting the variability of the shape function in regions that are very close to the equator. What this means, at least for this simulation, for these runs here, is a greater shape function here leads to enhanced turbulent mixing. So if I show you here now, just this is a depth longitude diagram. And I'm comparing the couple with a couple MLE version. You can see here, these blue lines mean that we have an enhanced equatorial current that I think, it's hard to prove at this point, but I think it might be related with the fact that we're increasing mixing or turbulent mixing very close to the surface and at the equator, which is leading to a lot more La Nina type conditions. This enhanced equatorial current is also leading to other biases, like a much colder SSD, or a much colder whirlpool region, and a saltier, fresh pool. So these are my conclusions, but as you can see, this is just kind of a proof of concept. We have been able to take other work done on M-square lines and we have implemented this in a much complex model, but there is a lot more work to do. Maybe we need to improve the training data and take different regimes, because these equations discovered were only obtained from a couple of days of a very high resolution and single column simulation. So we might need to expand our training data. And I also want to look into a couple of feedbacks that are really not captured in training. And another thing to notice is that by training a model on just a few days or hours, we're not looking at the compounded or cumulative effects when we add it to a much complex model. So that's another thing I'm keeping in mind. And also how these implementations are interacting with well-known biases in a fully coupled model. With this, I can take questions. Thank you.
Thanks. We don't have time for questions, but we'll transition. There's a half-hour break, so please take all your questions to the speakers during break. We're going to stay in the ocean now for Marta.
Wow. There we go. And works like this. Okay. Hi, my name is Marta. And thank you very much for the opportunity to present my work here. I work on developing the EPPL scheme in MUM6, and I sit at the GFDL. So Jacqueline has already given a really nice introduction. Actually, a lot of my first slides are also very similar to Jacqueline's slides. So I work with the surface ocean boundary layer, and now you already know why you should care for it. From what Jacqueline has already mentioned. So this is how the surface, the atmosphere and the ocean kind of communicate with each other. It's through this boundary layer. And in climate models, boundary layer depth biases can propagate into the entire climate. So we want to represent these the processes in the boundary layer depth right as well as possible. And there is a plethora of ways to
simulate these vertical turbulent fluxes. So on like the lower complexity end, if I can, on the lower complexity end, we have both parameterizations and second moment closure models, which are 1D models where these fluxes are parameterized, and we can go all the way to directly simulating them with large eddy simulations. But this comes with like a larger computational cost. So for our global models, we usually are on the lower end of complexity. Oop. However, with machine learning, we can use another approach, and we can actually emulate these higher order schemes into the parameterizations that we use in global models. So in EPBL, our diffusivity is a product of a shape function, mixed layer depth, and a velocity scale. And as was already mentioned in previous work, the shape function and the velocity scale has been replaced with a neural network. And then this led to an equation discovery that ultimately improved the EPBL scheme. So here you can see that with a neural network component, we can get rid of a bunch of mixed layer depth biases. And this is very encouraging, and also I think Jacqueline's results are encouraging that this can potentially generalize to other models. So the next goal is to take the last part of the diffusivity profile from EPBL, the boundary layer depth, and make a neural network predictor for that. So in EPBL, boundary layer depth is predicted using this quantity called M, or the energy conversion. So this is the conversion of turbulent kinetic energy into potential energy. And currently in the scheme, there is an algebraic equation that takes in the Coriolis frequency, the surface forcing, and the boundary layer depth that can calculate this quantity M. And the boundary layer depth is then found in this iterative way, where first we guess a boundary layer depth, we calculate M from this algebraic equation, we then calculate boundary layer depth, and then we see if they agree. And if they agree, we accept it. So what I've been working on is to basically replace this algebraic equation with a neural net with extra inputs. And the reason we want to do this is because the current algebraic equation assumes a fully equilibrated boundary layer, and it's undefined at the equator. So we think we can do better than this. For this, for the training data, I have run a higher order scheme, idealized simulations with constant Coriolis frequency and surface forcing. And per each case, I get these time series of boundary layer depth and energy conversion. And as you can see, we get this transient response, and then they end up in their equilibrium values. So for predicting the transient boundary layer depth and energy conversion with a duration of simulations of 9 days and temporal resolution of 30 minutes, I get over 1 million training data points and over 80,000 test data points. And just a clarification here, the boundary layer depth in these time series is computed from this higher order scheme criterion, not in this iterative way as this is done in EPBL. So yes, we have this transient response before the system reaches the equilibrium. And right now in EPBL, we can predict M, and we have a unique M per single case, so per single set of surface forcing. However, in order to actually predict that transient response, we need some extra inputs. And the question I have been working with is what extra inputs that we actually need to do this. So I trained a neural network with Coriolis frequency, surface forcing, boundary layer depth, and extra inputs that are the kinetic energy, surface input, and shear squared and n squared at the boundary layer base. And this is my transient predictor. And I compare this one to my equilibrium predictor, which basically mimics what EPBL does currently. And the choice of these inputs is motivated by the fact that I can just take anything I want from these higher order schemes, from the simulations. These inputs must be available and easily to sample for online implementation from the model. And it turns out that, unsurprisingly, shear squared and n squared near the base of the boundary layer are actually necessary to reproduce these oscillations that we see in the energy conversion time series. So the success is that we can actually, compared to the equilibrium predictor, we can get 68% better with the transient predictor with these extra inputs. So we can beat our baseline. Here you can see in black, this is my ground truth. The equilibrium predictor or prediction is in gray, and the transient prediction is in red. So we can beat the baseline. However, there is some discontinuities in the input features in shear squared and n squared that propagate into the prediction. And so this is the problem that I'm kind of working on now, because for online implementation, we want it to be more continuous, hopefully better. So what I'm working on now is basically determining where to sample n squared and shear squared. And I'm doing this by kind of inputting the entire profile into my network and seeing which of the neurons are the most informative. So this is like continuous work, and I'm exactly at 8 minutes. Thank you.
We do have time for questions.
Just trying to make sure I understand. So this is all in MOM6, GFDL version MOM6,
Right.
uncoupled testing. So
Yeah, so this is still offline test.
Offline,
Yes,
yeah,
yes,
yeah.
yes. So online implementation, as I said, so the transience of M has proven kind of difficult to learn. So it's been hard to find a set of inputs that from just current state can predict M in the time series. Probably because there needs to be some history involved to actually accurately predict it. So it's still in offline testing, and once I get to a satisfactory point with this prediction, I want to validate it on realistic cases, because this is just idealized case, and then going into online implementation.
And just comparing your talk with Jacqueline's, and in terms of the training data sets, I didn't follow everything exactly, but it seemed like you have a bigger sample from longer runs. Jacqueline, she was training on just a couple of days, and you're training on longer. Is that right? Or
yes. So I'm kind of doing this the same thing as Akash Sana did with like his training sets for these other components of BBL. Yeah, because these cases are actually really similar to each other because they are idealized. So yeah, I want as many data points as possible because yeah.
Okay, great, thank you. Next we'll transition to Da Fan, who has been developing tools to recalibrate these hybrid models once the parameterizations are implemented. Go ahead, Da.
Thank you. All right, hello everyone. I'm Dafan from Leap Columbia University. Today I'm going to talk about using contrast learning to understand climate model bias and calibrate it towards observations. So in climate models, warm rain microphysics remains a large source of uncertainty. Many cloud processes in the left figures are still poorly understood, and they have to be parameterized using empirical relationships. And Gettleman et al. 2021 developed a machine learning-based microphysics scheme, which efficiently represents cloud processes using machine learning, and it's called TileML here. So we run CAM6 with two different microphysics schemes. One is the TileML, the machine learning-based Bing microphysics scheme, and the other is the KK2000, the default warm rain microphysics scheme. And for each scheme, we use the Latin hypercube sampling to sample physical parameters to generate 100-member parameter ensemble. And in this work, we are interested in total liquid water pass and 4 different radiation fields: long wave, short wave, upward long wave, and net solar flux. So here we show the zonal main climatologies for total liquid water pass and short wave cloud forcing. And we have the TileML PPs in blue, KK2000 in orange, and observation in black, with the shading representing the ensemble spread over observation range. So as you can see, both PPs have significant biases compared to the observations. And we want to calibrate physical parameters to make the climate model outputs towards observations. And the spread and the large spread represents the strong sensitivities to physical parameters. And so a major challenge here in model calibration is how to simultaneously reduce biases in multiple variables across multiple regions. And here we introduce a contrast learning framework, basically an AI framework to enable a relatively balanced calibration across multiple objectives. So for the inputs, we have monthly mean total liquid water pass and the radiation fields from TileML PPE, KK2000 PPE, and observations. Satellite observations. And we use a neural network encoder to project this data into the 128-dimensional shared latent space. Well, the latent space is a low-dimensional compact representation of the input data. And for visualization purpose, we use the principal component analysis to further reduce the dimensionality from 128 to 2 on the right. So in this two-dimensional latent space, each dot represents a single ensemble member focused, and the yellow triangle represents the observation. So you can see TileML and the KK2000 PP form two clusters close to each other, with the observation being slightly closer to TileML. And these features rotate clockwise in this two-dimensional space, showing seasonal variability, and the spread within each cluster represents the variations in physical parameters. And the distance in this latent space may indicate some differences in the physical fields that I'll explore later. So overall, this latent space representation provides a compact, low-dimensional representation for direct comparison between climate model outputs and observations. So here we define the distance in this latent space using the cosine similarity. That is the angular difference in the latent space. And we applied explainable AI to understand the physical features behind this latent space distance. The attribution plots on the right identified regions like this right spot that contribute most to the For example, here we show the attribution maps for the latent space distance between tau ML and observations in the first row and KK2000 versus observation in the second row. So it's kind of telling us which physical features are behind the differences identified by the latent features. And we found strong signals in total liquid water bus and shortwave cloud forcing, especially in regions associated with shallow cumulus and stratocumulus regions, and also the southern hemisphere storm track regions. So these differences contribute to the separation in the latent space, or the model bias learned by this AI framework. And furthermore, we explore the relationship between regional attribution signals and physical parameters. Here we show the regional parameter sensitivities for the distance between tau ML and observations. The x-axis shows the parameters for microphysics, turbulence, convection, and aerosol, while the y-axis shows the regional variables. For example, the first one is the net solar flux over tropical Pacific Ocean. And we found strong regional sensitivities to some parameters. For example, the micro-MG DCS shows strong signals, strong correlation with the attribution signal or the latent space distance over the southern hemisphere storm track ocean and North Pacific Ocean. So from this, we can see the latent space distance encoded the regional parameter sensitivities. And with that, we would like to calibrate the physical parameters using this information. So we train a Gaussian process model to learn how each physical parameter affects the latent space distance, and then use the model to generate 10 calibrated physical parameter size that minimize the distance in the latent space. And with that, with the new parameter size, we run the CAM6 to generate the new calibrated ensemble. So here we show the zonal mean climatology for the original tau ML KK2000 and the calibrated tau ML, which is in white, so, and also observation in black. So you can see the calibrated tau ML shows improvement in almost everything compared to the original tau ML, which is in blue. You can see the better total liquid water pass in the southern mid-latitudes and northern mid-latitudes, and improvements in the shortwave cloud forcing in the tropics, and almost everything, everywhere in long-wave cloud forcing and upward long-wave flux in the tropics. And we also care about extreme precipitation. Here we show the calibrated tau ML, which is in right, has a much better agreement with the iMerge observation compared to the original 100-member tau ML and KK2000 ensemble. And it also helps reduce the drizzle bias. Here we show the drizzle frequency for these PPs and also iMerge data. You can see the calibrated tau ML reduces the drizzle frequency in both mid-latitudes and tropics. So in summary, we use a contrast learning model to reduce feature dimensionality of physical features we would like to tune, and the distance in this latent space captures regional parameter sensitivities, and we would like to tune this tune the model using these sensitivities. And the latent space calibration improves the climatology, extreme precipitation, and drizzle forecast. Yeah, thank you. I'll take any questions.
Okay, we are right at time. Dan has a question. Go ahead.
Real quick, I was just wondering how well posed you found the problem of.
I'm not sure I understand
Well, I guess like in the latent space, there could be ways you could change an emulator that are not spanned by your set of available physical parameters.
We didn't change the emulator. I mean, we didn't change the parameterization during the training. Yeah. So basically, we have the physical parameters fixed for the perturb parameter ensemble, and then we project the cam output into the latent space, and we try to learn the relationship between the perturb parameters and the latent space variations, and use that information to do calibration.
Okay, thank you.
Thank you.
We'll go to break now and be back at 10:30. Thanks, everyone.
Hey everyone, we have a tight schedule, so if you could sit down so we can start right at 10:30, that'd be great.
Oh. No, it's this. No, it doesn't work. Now it doesn't work. It's just not going forward yet. Wait, now it's doing something. No, he's getting it back. Yeah, I don't, I think it was just like frozen or something. That looks like my desktop. Is that my computer?
Okay, everyone, it is 10:30, so if you could sit down, that'd be great. Thank you. Do you hear the cowbell? That's great. Okay, I just want to give a quick reminder to our speakers. These are 10 minutes sections here, so there's 8 minutes for your talk, 2 minutes for questions. If you do go over, we're going to have to move on just for the sake of time. So with that said, I'm just going to get us started off so we have as much time as possible with our first speaker, John Schreck. Whenever his screen slides come up.
That's fine.
Okay, if you're just joining us, we're having a reboot problem, so just bear with us here.
We should get some AI jokes or something.
How does everyone feel about emulators? Good, bad? We got some thumbs down in the back. Oh, thumbs up front.
I mean.
Oh, this emulator speaker says thumbs down. Okay. You do not, Dave, no. Well, John, since you have extra time, do you want to just talk a little bit about credit?
Well, I mean, my first couple of slides are credit, because I realize, well, my title's not up there yet, but not everyone in the room knows what credit is. So, yeah, I mean, okay, so I have a slide for it, but it's up near the front. Credit is a platform that we've been working on here at NCAR. And I'm John Schreck. I'm a machine learning scientist. I'm in CISL, and I'm in the MILES group, which is Machine Integration and Learning in the Earth System, I think. I got the acronym right. DJ Gandhi is the group head. He's sitting over there. And a couple of years ago, once Derecho finally came online, and we had lots of GPUs, we chose to sort of try to get into this emulator game. And it kind of started out with mostly numerical weather prediction. And we've kind of pushed it a little bit beyond that, but at the time we had to learn how to train these neural nets on our infrastructure. And this is not like a single GPU operation. This is like, we have 300 something GPUs on Derecho. So how do you pull all those resources together and then just train a single object, I guess, or a neural net? So a lot of credit in the beginning was basically trying to figure out how to like do scalable AI training. And in a lot of ways, that's what it takes to train an LLM, like ChatGPT or Claude or whatever. So in those ways, it's pretty similar to like how you would do this for the things that you're now using to write your code for you or whatever it is that you might be using AI for. Okay, I think we're almost back. Okay, close. Am I good? Okay, let me just make sure that, okay, it's working. All right, right, so I have to go through these slides pretty quickly and I'm gonna start my clock right now. Right, so AI weather prediction from dream to disruption, and I put a period there. And you can kind of see that, you know, in the last 8 or 9 years, people have been trying to use AI to do numerical weather prediction. And you can see that in the beginning, we were not doing that well relative to, for example, Z500 at a 3-day lead time for the skill on that, okay? So, but around the time that ChatGPT was released, the models and the training pipelines have improved to the point where we are starting to become competitive against IFS, okay? And in many cases, you can see there's like many models now that have sort of joined the fray in the last couple of years, and pretty much all of us are able to kind of edge out IFS on not necessarily every variable, but certainly on a lot of them. So the question I wonder, and a lot of us are looking at right now is, can we do the same thing for climate prediction and not just weather? Okay, so make sure I have this right. Right, and I kind of just wonder, what's the point of really doing this? We are seeing jumps in prediction accuracy that are happening faster than we would normally do with kind of traditional physics-based development. So on the left, you can kind of see AIFS versus IFS performance gains at different lead times. And so it is true that the AI models are able to a little bit outperform what we've had before the AI. The right is probably the main point that I like to drive home, is that you don't need a supercomputer to run a numerical weather prediction model anymore. You just need a laptop. And you don't even really need a GPU, depending on the model that you want to run. So now anybody can do numerical weather prediction, state of the art, on their computer. So here's my little diagram of credit, and I will say this is about 6 months old, out of date. So credit, like I was saying, it's a scalable AI training pipeline built primarily around derecho, but it works on pretty much any HPC. We have data sets, models, and then we have physics constraints, because neural nets don't know what physics are because they're not a thing. And then we also do a lot of post-processing. So you can see model-wise, these are all neural networks that we've incorporated into our stack. Okay, WexFormer is the one that myself and a couple other people have been cooking up, kind of more for NCAR branding more than anything. I also don't want to use Google stuff. And you can see Camulator's in there as well. Camulator is the same thing as WexFormer. It's just trained on different data sets. Okay, so I'll talk a little bit about that in a little while. Where we've been kind of focusing a lot more of our energy lately has been data sets and making sure things are physically constrained. I don't have time to kind of go into like the new details of credit yet, but DJ Gagne and Charlie Becker and a bunch of other people have been putting tons of effort into making sure these models are more reliable and trustworthy as we kind of move towards broader adoption. Okay, I got 5 minutes. So Mesa Clip. So I'm mostly just kind of talking about weather, and I mentioned Camulator, if you even know what that means. Camulator is an emulator that Will Chapman trained using our WexFormer architecture, and he ran a 30 or 40-year CAM simulation, and then he trained a neural net, treating that as truth data. Okay, so kind of using that idea, what he was doing, right, ERA5 is kind of like a soft truth, right? Like it's kind of correct, but it's also kind of wrong in places. But it is certainly different than, like a full CAM run, okay? So, but we have this giant Mesa Clip data set that's been built, basically ran out here at NCAR. Okay, and that's a high resolution, it's 1/4 degree atmosphere land, and it's a 1/10 degree ocean sea ice, and it's fully coupled CESM ensemble. I list the components there. It's CAM5, POP2, CLM4, sea ice 4, so it's physically consistent kind of across like the ESM stack, I guess. Now, the thing that's really different about this Mesa Clip is how it's represented. So Mesa Clip is on spectral element NE120 grid, and you can kind of see that up on the top right. That's not quite 1/4 degree resolution there. It's coarser than that. But as you can see, it's cubed on a sphere, okay, for this particular case. So up until this point, we've only worked with lat-long grids with these neural nets, okay? And we are all aware, those of us who are training these things, that is a limitation, that the grid representation will lower your performance if it is a bad representation. So our aim with Mesa Clip is to train on the native grid, okay, and not projecting that or whatever, transforming that over to lat-long like we've been doing with other stuff. Okay, so ERA5 is, all of us train on lat-long with that, okay? A couple other things, it's a really great data set. I mean, it's huge, it's an ensemble data set, so there's like basically about 1,500 years total, so that's like much, much larger than what all of us have been using the ERA5 data set for the weather models. So hopefully it's a richer data set and we can get a better model for lots of different Earth components. Just real quick, this is a model architecture, the one that I've been working on a lot with other people in the Mesa lab. This is a thing that we call WexFormer. It's kind of like a half vision transformer, half U-net. And the U is just, it kind of makes a shape, like left to right. It kind of makes like a U. And an image will just come in on the left-hand side. And what the vision transformer does is it kind of like chops the image in half, featurizes it, chops it in half again, featurizes it. And it does that down to a bottleneck point, kind of like right where red goes over to blue. And then I kind of like reverse that process with convolutional layers. So I'll start to upsample downscaled kind of representations of whatever your data is. Okay, I mean, there's a lot of other details. The only other thing I really wanted to point out were these beta things, and definitely like there's a 1 and a 2 and a 3 that's not rendering correctly on those betas. In order to transform this deterministic neural net architecture into a generative model, we do stochastic noise injection at different scales in the model. Okay, and that different scales is what played the role in us to actually deliver, well, let me say what they are. So at these junction points, the beta 1, beta 2, beta 3, we basically compress down to these effective resolutions, right? But what we wind up at the end of the day, and this is for the weather model still, and the main plot I want you to look at is just the spread scale right here, right? This is what we were really after here, and it's pretty flat across 15 days. It starts off a little uncalibrated, and then they definitely move towards calibration. And this is for almost all variables in our Wexformer architecture. And I did not go in and kind of hand tune the noise. If I did, I can probably get it calibrated right off the get-go. So we did the same thing for Camulator, and it works. Okay, this is a 30-day ensemble. These are 100-member ensembles with Camulator that we do, and using exactly the same technique, the stochastic noise injection, we can get a calibrated Camulator model as well. Now, I'm not doing anything with this because we actually have a broken decoder that Will Chapman has fixed, and we're going to regenerate all this stuff as soon as version 2 Camulator is ready. Okay, so what do we really need to do Mesa Clip? Well, I noted that we don't want to use a lat-long grid anymore, so we're going to actually develop a new encoder structure. So all the way over here on the left, you see this x at time t. That's just like a state of the atmosphere if we're doing an atmosphere model. That's in the spectral element grid here on the left-hand side. So it's basically just like a big giant vector. What I then do is I will transform that onto 6 cube spheres faces. Okay? And then at each corner of the cube spheres, I will run what's called an attention mechanism across the axis, okay? Where the 3 faces come and meet at a point, okay? And that's basically haloing, if people are familiar with that technique. And the reason why we want to do that is because we need the attention to be continuous across the boundary layers, okay? And we don't want to have to do hacky things that everyone else in this community is doing to make their models more realistic. I threw in a couple other innovations that were from Pangu, Aurora, and the SFNO model. They're not super important here. This is still the same Wexformer architecture. It just now ingests a spectral element cube sphere representation. Okay? So that means no more lat weighting in our loss function, none of this hacky stuff that everyone's trying to do to get this to work. Okay? So it's not totally validated yet. And the main thing that we need to do is be really worried about our data. So this is actually just something, I just pulled out a whole bunch of land variables. I'm definitely running out of time here. Some of these look pretty clean, like soil water, 10 centimeters, you can see up here. That one I can kind of pre-process. I can subtract the mean, divide by sigma, and turn it into a unitless quantity. But some of the other quantities, like this leaf area index, you'll note that there's like a hard spike at 0, and then kind of like a more regular looking distribution. So this variable over here is sort of singular, whereas this one's kind of quasi-binary. So how we're going to pre-process this data is really going to matter a lot based on how well you want this model to actually perform. Okay, and I got one more slide here. Okay, oh boy, that really got messed up. Okay, so these are all, like I said, we have all components and we can couple things together and do whatever we want. So I've just been getting ready to train these models at scale. I've not trained any of them yet, and I've only z-scored all of the variables. And there's hundreds and hundreds of variables that we're looking at here and ingesting into these models. And you can't even see it, it's running off the slide here, but we've scoped out basically all the components, different, mixtures of land and ice or whatever. And I mean, I've been doing this for a little while, so I can just kind of spot check the numbers, and they all look pretty good. And this is not doing a smart data transformation yet. This is just doing I won't say the dumb thing, I will just say the thing that you think to do first until you look at your data again. But it really looks pretty strong. And the thing that I'm calling next is the new model, cube sphere versus a lat-long representation. And I can already tell you, it's like blowing past the other one. So we're pretty happy. I don't have a conclusion slide, so it's just a black slide. But that's where we are on Credit Mesa Clip. I can't possibly train like 15 models that take a month each with my GPU allocation. So if anybody wants to get in on this with me, feel free to let me know.
Thanks, Don. We're going to have to move to our next speaker, Shreyas.
Hey everyone, thanks for having me. So I'll be talking a little bit about this AI-driven emulation of stratospheric dynamics, actually kind of sharing some of the themes that Jeffrey was talking about. So I guess this is kind of redundant at this point, but why would we like to emulate climate models? One, as we said, speed, so we can run hundreds of years per day on relatively accessible hardware, which Jeffrey also mentioned. And also create large ensembles, many member ensembles to separate force response from internal variability. And then I think the most important and what we're trying to focus on is make it open source, differentiable as Duncan mentioned, and also build the link and couple with the microphysics, radiation, and ocean. And also, as we said, there's been explosion in non-supercomputing compute, and people have access to GPUs. So we'd really like to make something accessible to anyone with access to a GPU. So, I'd just like to give us a quick idea of what we're trying to think about this multi-scale modeling framework. Basically, the idea is to create various emulators for different parts of the scale. So for example, here I'll be talking about 8-WACM, which is our emulator for the climate scale or the atmospheric scale dynamics. Also, we're trying to train emulators for microphysics components. So yesterday we heard some talks about Tomas, MAM, and Karma, these basic microphysics modules, and we like to emulate aerosol nucleation, growth, and size distribution for us, particularly in sulfate questions. And then we kind of proposing this framework in which we are able to emulate individual components and then also swap out components. So say you're interested in how Karma responds or specific types of microphysics modules respond, you can swap these out similarly with CSM. So we're particularly interested in the stratosphere. So we've laid out a few ideas of what a stratospheric emulator should get right. One is stability. Obviously, for climate scale applications, we want indefinite drift-free rollouts under fixed and evolving forcings. The QBO, the quasi-biennial oscillation, which is a spontaneous 28-month period, a tropical wind oscillation. The Brewer-Dobson circulation, and also we expect that the age of air, we like to get that right, which is a kind of metric that we want to understand for how transport fidelity works. So we've trained this model on this particular training data. So the source is CESM2 WACM6 high top configuration from historical prescribed STs. We're using the 6-hourly output and then sort of 70 layers with a very dense up to the in the stratosphere. And then we've kind of trained on 1970 to 2014, and then we're seeing how the model performs into the future. Some details about what our model actually is architecture. So we're basing this off this Paradis architecture. So kind of I'll kind of walk through what's nice about this architecture, but we're at a 1 degree resolution, about 40 million parameters. Here we're using 20 levels extending to the stratosphere. And the model is basically trained to predict the next state in a state vector forced by SSTs and solar radiation. And some interesting things about this model is that we are having these kind of physically inspired components. So there's an advection block and a diffusion block, and then there's also this reaction block. And our kind of hope is that we're able to train this end-to-end on CSM output, and then confine things like chemistry and other reactions to this reaction block, whereas preserving the advection and diffusion, the large-scale transport dynamics in these first two blocks. It's also decouplable, meaning we can turn off the reaction and just kind of get the dynamics only. Exactly. So what are actually what's going into our state vector? The classic things: geopotential temperature, UV, vertical velocity, specific humidity. We're also using nitrous N2O as a long-range chemical tracer, roughly inert, and then it's also forced by things like surface and mean sea level pressure, SSTs, and things like that. Specifically here, we've chosen a high level representation into the stratosphere and into the tropopause also. How do we train this thing? We basically train to first predict a single time step. What I'm showing here is the validation loss, as basically how well the model is performing as a function of how much we train it. So this first step is this massive descent as it learns to get the single step prediction right. And then as we ask it to train further and further time steps, okay, we feed the model back its own input, there's a huge loss. That's the kind of a huge jump in the loss, which is this FS equal 2 transition. And then once again, it eventually plateaus. As we ask the model to predict further and further timeout, it's kind of plateauing. So this is kind of we're kind of teaching the model how to predict further and further time steps. We're also training with a conservation loss. Various groups have experimented with hard conservation blocks, including Camulator, versus a conservation loss in which we encourage the model to conserve energy, moisture, and mass. Here, this is a conservation loss, but we're also looking into hard conservation too. So just general high-level results. These are still early. We're still working on some other models too. So first is a couple of variables. What is forecast error in short time scales? So roughly it's good, but also it doesn't blow up. So as we might expect for a climate scale model, we want indefinite rollout. So it's saturating below climatology for 28 days lead time. And also we get indefinite rollouts, right? So here I'm showing you conservation diagnostics, mass, water, and energy for 5-year rollouts. So relatively good conservation despite this no explicit conservation of mass and energy. The following things I'll be showing are from a 5-year rollout, average for climatology. So here I'm showing zonal mean temperature. So here the ground truth or CSM output is on the left, the emulator output is in the middle, and then the error is on the right. So roughly it's doing quite a good job. We reproduce the cold point tropopause, albeit slightly colder in our AI-driven emulator. And some of the cold extremes are a bit overshot, but generally we find pretty good agreement. Same kind of similar thing for zonal mean, zonal wind. Large-scale circulation recovered both seasons, subtropical jets, and various kind of dynamics we hope to expect. There's some small overshoots consistent with the temperature bias as well. Kind of one thing that I had mentioned, this quasi-biennial oscillation. So we looked at the equatorial zonal mean, U for to see if the QBO emerges spontaneously. And we kind of see that they're switching in the upper stratosphere, but it doesn't quite propagate downwards to the tropopause, which we currently suspect is a consequence of not having good tropopause layer representation. So this is once again kind of preliminary results. We're trying to improve the models as we go. But what are we kind of interested in using this for? So I guess I'll give a quick spiel in the next slide. But we want to basically look at stratospheric aerosol injection here. But really the real question is we want to make lots of scenarios accessible to lots of people. So we want to be able to sweep injection magnitude or basically any kinds of external forcing scenarios. Once again, large ensembles. And then also see how this kind of performs out of sample. And kind of in a bigger picture idea, we want to kind of couple these two, aid Wacom that we've created and microphysics to see how well does SAI forcing and how well does the overall open source models perform. Just quickly, we're from Reflective. What is the overall goal of this? We want to create these fast, open, reproducible tools to systematically explore the uncertainties in this space, but also give people tools to overall increase throughput, model throughput, and things like that. Sure, thanks.
Awesome, thanks for staying on time. We have time for a question.
I have a question as to your goals. Why do you not have the polar vortex in the list of stratospheric features that you want to simulate with the emulator?
Yeah. So great question. So far, I think it's pretty early. The first models that we've trained the stratosphere is under-dispersed for various training reasons. So the current models that we're working on actively, are currently training, have a better stratospheric loss representation, and they're currently. So basically, this model that we're currently trained didn't have the correct representation, but we're working on improving it currently. So.
Cool. Any last quick question? Okay, we'll move on to our next speaker. Thank you.
Hi, everyone. I'm Aiden Janney. I just started as a Scientist 1 at NCAR. I'm on the Crocodile project, which is focused on regional ocean modeling tools, and then I've been really lucky to work with a bunch of folks in NCAR Miles group, which produces credit, which John just talked about. This is talking about some work from my senior thesis at CU Boulder that I worked on with Dan Amarain and Anish Subramanian. I'll note too, like this is still very much in development, so I'm gonna just kind of talk about the process a little bit and then some initial results. We've already heard a little bit about emulation, so I can zoom past that a little bit. What I'll note is people have started applying this to global ocean models. Notably in last year, Samudra came out. This is based on OM4, which uses MOM6. Which is now the ocean model that we're using here at NCAR. It's able to roll out 100 years in an hour and a half on one GPU. Some crazy performance. It's really skillful. Still struggles with things like external forcings, but really promising for ocean science. And this is just kind of an example of like the basic workflow, right? Like we have this robot in the middle that just works our ocean state forward in time by one time step. So just talking about the development process, this project was focused on like kind of doing the full stack. So thinking about, right, regional ocean modeling is very flexible. We want to go from any region the data generation, then do the ML training, and then have something to predict and have a model that we can use to do some science. So for the data generation, I focused on the Caribbean. It's based on this 1/12th degree model of the Caribbean that Giovanni Sejo Ellis worked on here at NCAR and CU Boulder. And part of the reason is because the Caribbean, this model is established, but another really big advantage is that there's a lot of complexity in this region that can really stress test these emulators. These model variables that we focused on are based on Samudra, and so there's definitely a lot of flexibility here, but it's just gonna be sea surface height, temperature, salinity, and velocities. And then we have some inputs from some external forcings. I'll note like all the training data was from an uncoupled ocean-only simulation. So we used JR55 for the atmospheric forcing, Glories for the boundary conditions, and then importantly in the Caribbean, runoff is really important because of the Amazon and some other outflows in the area, and so we also have GLOFAST for that data set. And then we generated 20 years of output brand new from 2000 to 2019. I used WexFormer, which John already talked a little bit about. I'll note how I prepare the data a little bit, right? He noted this normalization question, and this is definitely still outstanding. How do we prepare this data to kind of tell the model something about maybe like physical tendencies and what we want it to see in the data? Typically this is done globally, but here we tried this pointwise normalization to try and capture like all of these different behaviors across the depths and scales of the ocean. And then single step training, mostly because it was a really big domain. This is gonna move to multi-step. This was just kind of like the first testing phase, and multi-step training is much better working into the future. And then notably, there's not really a standard for boundary conditions. So to start, we do something kind of messy and we just kind of smush it all together into one image for the model to see. In the future, I think this is something to really improve, right? The boundary conditions have a really big influence on forcing inflow to the model, for the numerical model. And then they actually have a pretty minimal influence for outflow from the model. And the emulator doesn't have any knowledge of that, right? And so how can we like incorporate that into the architecture? And then I'll note 15 years of training data and 5 years of validation data was the split that I used. So just some results in experiment. I'll talk about like, this was my workflow. First I tried just like throwing everything at it with full depth emulation. It exploded. I'm happy to share figures with that, but I'm gonna move on to talking about just upper ocean emulation and then some steps that I took there. So just literally thinking about the top 15 levels. This was a pretty high resolution model vertically, and so that's only 35 meters. So it's pretty homogeneous in terms of the dynamics of the ocean, especially when you consider like the entire scope of the ocean. But it's also smaller data, which means our training can improve, smooths out the loss. So we're sacrificing some really important dynamics of the ocean, but we're still like getting this really useful test on how emulators are going to handle this type of system. So this was just the first pass, right? Like all of this preparation that I talked about before, the envelope, the shading here is going to be one standard deviation, and then we're just looking at mean sea surface temperature and sea surface salinity. It seems to capture the mean signal for temperature really, really well. Seems to, you know, have slightly higher variability. The emulator's in orange. For salinity, it really starts to drift away. I mean, this makes sense. There's a lot of really strong competing salinity signals in the Caribbean, which is why we chose this region, but it's definitely something that we expected it to struggle with. It's also hard to see, but you can see that the variability for the salinity is actually massively overpredicted. This lines up with some like pretty insane RMSE values where you see the really high variability. So it's definitely like predicting unphysical behavior here. So here is another like kind of like first pass, what John described as maybe like not the best thing, but the first thing you try, and it's going to be clamping. So this is a little bit agnostic to the loss and the training of the model, which is why it's a little bad. You can think about it like you're going to just like slice off part of your loss landscape, kind of amputate your model, right? And so as part of that, at first, I tried doing clamping during training and inference, found out it did some weird stuff, and then moved to only doing clamping during inference when we're really seeing these like non-physical values build up. This first slide is going to show clamping during training, just because I think it's really interesting. Right, so we're affecting the loss landscape, and we can see like the model is still following maybe seasonal signals for temperature, but for both temperature and salinity, it's suddenly jumped into these like dramatically different regimes of behavior, but it's found some stability, some equilibrium there. So just something really interesting to explore in the future. But don't only clamping during inference, so letting the model train normally and then just constraining those physical values when it's like rolling out for 5 years at a time, right? Or longer. We see really good results. So now the variability is much more constrained. We still capture this mean SST signal. Salinity is still giving a lot of trouble, and we can see it actually seems a little bit out of phase. I have some more figures that aren't in this presentation that show kind of like how the spatial coherence of these signals compare to the numerical model with some interesting results, right? Like some signals signals are captured well, others are not. But I think another really interesting result was the power spectral density of the model. So this is just looking at surface kinetic energy. This is like a pretty useful diagnostic for the ocean because we have this really powerful scaling law for how like complexity decays over scales. On the right, you see a couple different timestamps. The emulator is still in orange, the numerical model's in blue. On the left is just like how that's evolving over time. And we can see like it starts out with a very similar profile, and then over time like finds its own new regime. I still haven't tested how physically reasonable this additional complexity is, and of course we don't want this additional complexity, but it's really promising that it's getting the correct behavior across scales, and I think it really speaks to the power and flexibility of these like convolutional neural networks, this Wexformer approach. So what worked? We have a stable emulator of the upper ocean. It captures mean SST and variability really well. Of SST, salinity is still in progress. I think really exciting is now there's just this pipeline, right? I was able to leverage a lot of tools at NCAR to now go from any region, try and train an emulator. There's no guarantee it will work, but it's going to be some exciting science that we can do with it. Here's just some pretty animations. Ignore the color bars. That's just like GIF generations. But we can see like some really physically reasonable patterns. Definitely, there's still some suspect behavior in the models, and you can see like some really interesting like striations in the salinity, and also we'll see that in the vorticity in this next plot. So some non-physical effects, but it's exciting that the emulator can capture this behavior well. So where to go next? There's a lot of steps in the future that I want to explore. I think this data processing step is really, really important, especially for the ocean, because we have behavior at dramatically different scales, both spatially and in time. And then like thinking about how OBCs and runoff are interpreted, all forcings really. And then now working with John on this global emulation piece with MesaClip, moving to MOM, and then thinking about regional and global coupled emulation with CSM, MOM, and now MPAS as we're looking to incorporate that into the ecosystem. So yeah, reach out to me with questions, and more work will be done soon. So.
Great job, you stayed on time. We have time for a question.
I'd be interested in your thoughts about why you can't do the deep ocean. Is it just because the deep ocean is too slow and so you don't have enough sample size?
Yeah, I think that's definitely the primary issue, like the primary factor there. I think it almost seems like a little bit of a coupling problem, which we've discussed, is like maybe trying to separate out the upper ocean and the deep ocean into like two separate parts of the model that you're training on separately and maybe have different timescales for. I think it comes back to this how we're presenting the data to the model to learn on. Because when you normalize to like get these unitless quantities that are really good for learning, you inherently are missing out on some ideas of like the tendencies and the timescales of the deep ocean. And it's also kind of a sampling error problem as well. So something that we definitely want to explore, and I think machine learning is like well suited to like kind of poke at, and we'll see what happens. Thanks. So, yeah.
Great, thanks Aiden. We're gonna move on to our next speaker, Kyle.
Sorry, let's go back. Hi, I'm Inkai Kyle from Research Applications Laboratory at NSF NCAR, and here I'll talk about the work that applies AI-based dynamical downscaling to CESM2 large ensemble dataset. And then here is the motivation. So dynamical downscaling provides valuable high-resolution regional information to support many downstream applications, but then running it across large ensembles and for many decades is computationally expensive. To put numbers on it, here for a typical regional setup with 4 kilometer grid spacing, commonly used atmospheric variables, and hourly output frequency, a pre-trained AI model in its inference mode will need about 2 GPU hours to complete the entire year of results. But then for an equivalent Wolf configuration, it might take up to 500,000 CPU core hours. So considering the time cost, the energy consumption and footprint, there is a orders of magnitude difference. So then our idea here is that we develop an AI-based dynamical downscaling model under present-day conditions using ERA5 and a 4-kilometer regional analysis data like Canvas 404, and then we apply this model to CESM and produce downscaling outputs. During this process, we care about 2 main questions. Number 1, can the model generalize to future climate regimes? And number 2, can the model downscale and ensemble without collapsing its ensemble spread? And both questions are critical to consider whether this idea is useful or not when applied to CESM predictions. And then we will conduct experiments to answer these 2 questions. And here's about the kind of the technical detail of these AI-based downscaling model. So it comes with 2 components. The first part is a kind of a swing transformer-based limited area model. This part is autoregressive. It takes the previous time step output as a current step inputs, and then it runs autoregressively, similar to how numerical model would integrate over time, which also means that it's not a snapshot-based statistical downscaling, but actually has the ability to evolve over time and produce prognostic outputs. And then the second half is a unit-based post-processing model to produce even more variables, including precipitation. And then we train this kind of AI design with 4-kilometer Canvas 404 as targets, and then a quarter degree 3-hourly ERA5 as the low resolution boundary forcing, and we train it for almost 40 years since 1980. And we have the boundary forcing input designs to be flexible. We have applied it either 3-hourly or 6-hourly boundary forcing, fed it into the hourly updates. After training, we apply this model directly to CESM, which means it's kind of a zero-shot inference because during the entire training process, CESM-related information will not be given to the AI model. And by the way, the region of interest is defined in the bottom right side of the domain, which covers the southern part of the Great Plain and part of the southeastern Kaunas. When the model training is completed, we had a present-day evaluation to make sure that it is working correctly. And for this part, we ran the model for water years 2021 to the end of 2024. 4 years in total, we have the domain averaged root mean square error, or RMSE, summarized in the figure on the right side. And here there are a few things to talk about. Number 1, the model is multi-year stable. Its RMSE has a seasonal cycle, but there is no exponential increase. There is no physical drift for all these 4 years or 35,000 consecutive hourly steps. And then we can also confirm that the model is skillful with its error on par with forecasting-oriented AI models on their day 2 or day 3 lead time performance. And then you can see multiple lines in the figure, and that's because we tested the model not only using ERA5, but also GFS analysis fields. And we do this to replace ERA5 and then use this as a boundary forcing, and we found that the AI model exhibit no downgrades in terms of their downscaling performance, which means the AI model, although trained using ERA5, does not overfit to the ERA5. Finally, we found that our AI model can resolve high-resolution weather information. For this part, we examined multiple downscaling cases. Here, for example, is an extratropical cyclone case from which the AI model output is on the left side of the column. And here we can see that the AI model can reconstruct the baroclinic region of this frontal cyclone system well with a cold front characterized by the sharp temperature gradient, as well as the frontal convergence and frontal precip on the correct location. And then for the landing of a tropical cyclone downscaling case, here the AI model kind of decayed the cyclone after landing a bit too quick, but overall it still has the ability to reconstruct the circulation pattern and the moisture distribution and maybe at least part of the tropical cyclone rain band in its downscaling outputs. And all these present-day evaluation pointing to the conclusion that our model is at least working correctly and is worth trying CESM data for the next step. And then we conducted 2 sets of 30-year downscaling experiments, one covering the 1980 to 2010 periods under the CMAP6 condition, and the other half covering the 2070 to 2100 under the future climate emission scenario with the 2-meter air temperature here calculated as domain average. With red and yellow lines coming from the AI model and blue line coming from the CESM forcing. And here there are 2 major things. Number one, the model can produce stable rollouts for 30 years with clean repeatable annual cycle. And the small graph here showing the diurnal cycle, which is also well reconstructed, and there's no drift in all these 30 years, which is very different from forecasting-oriented AI models, which only need to survive for the next 15 days. And in our case, we support multi-decadal runs. And our model is also able to get the warming signal correct with this domain average temperature increase for the 2 periods being 3 degree Kelvin, very close to what's reported from the CESM, that is 3.8 degree Kelvin. And in terms of the warming spatial patterns, we can see that our model can reproduce the amplified warming signal of about 5 degree Kelvin in the northern side of the domain. The only caveat here is that it underestimated warming signal over the Gulf. The AI model produces green color corresponding to 2 degree Kelvin, which is below the 3 degree Kelvin from the CESM forcing. But overall, I think the conclusion still holds that this AI model trained using present area analysis has the ability to be applied to CESM predictions for both historical and future climate scenarios. We also applied the model to downscale CESM large ensemble 10-member case. And here we applied AI model to these members individually, and we have the domain average of 2-meter air temperature summarized as orange colored lines in the middle. And the small graph here is kind of a zoom in for the first few days of this dynamical downscaling run. And here we can see that the AI members can diverge from a shared initialization within a few days, which means the model can respond to a member-specific trajectory without kind of regressing everything to the mean state. And then we also compare the AI model downscaled ensemble spread versus the CESM ensemble spread on the bottom right histogram. And here we can see that all the data points located around the identical reference line indicating that there is no ensemble spread collapse. With the ensemble spread being preserved, we found that the model is also able to add mesoscale information. Here at the bottom left side, we have the energy spectrum from the ensemble mean 2-meter air temperature, and the orange line is computed from the AI model output. And here we can see that for the 10 to 100 kilometer wavelength band, the model is able to add this mesoscale energy back that's not available from the CESM. And here the slope of these energy spectral lines also follow the K-3 and K-5 by thirds slopes very well. So overall, we think the AI model, when downscaling applying to the CESM ensemble, it can preserve the ensemble spread, meanwhile adding mesoscale details to it. And then here comes the conclusion. So here we have an AI downscaling model trained on the present area analysis that can be generalized to CESM lens 2 with a few performance highlights. Number one, the model can produce 30-year hourly rollouts with no unphysical drift, and it works for both present day and future emission scenarios. And the second, the model can capture the warming signal correctly and can capture the warming spatial pattern correctly. And number three, when applied to an ensemble, the model can respond to a member-specific trajectory, preserving the ensemble spread, meanwhile adding mesoscale information to it. And all these benefits are packed within an AI model that only takes a few GPU hours to produce results. In the next step, we're trying to move towards probabilistic downscaling by applying generative or diffusion model-based approach to generate more convective variability. For this work, we have a paper that will arrive soon, and we also have a preprint version available online. And with that, thank you for having me.
Hi, very nice talk. I was wondering what happens, curious about the boundaries. So you're training on a 25-kilometer downscaling to 4-kilometer, and then you are rolling out on 1 degree. Do you find that you have to inject energy at the boundaries, or do you find that a lot of the higher wave number energy has to be generated by the emulator itself?
We found this from the emulator itself. We tested boundary forcing from 1/4 degree ERA5, 1 degree CSM, and many other data sets. We just interpolate them to the 4-kilometer domain, and then the resulting downscaled energy spectrum is basically on the same level. So the AI model has the ability to kind of produce a consistent energy level in its outputs, regardless of the boundary grid spacings.
Thank you.
Awesome, thank you. We're going to need to move to our next speaker, Melody.
Awkward silence. It's just waiting for the slides. Oh yeah, hi, good morning. Thank you for having me here. So today I will be talking about a physics-informed machine learning architecture for climate dynamics and prediction. And then I will use an ENSO prediction as an example to illustrate this framework. So most of the architectures are implemented by Fred, a CS graduate student at UCLA, so many thanks to Fred. So to start, we know that recently the data-driven global weather models have shown great promising skills in the short to medium range forecast. But sometimes these learning representations in the AI models can be hard to interpret. And then these large AI models has trainable parameters, often to millions or hundreds of millions of them. And then this becomes important when we are looking at the realm of the climate predicting scales, where we only have limited records in the observational data. And then the models will turn to overfitting and then to show the long-term drift or the numerical instabilities. So here, instead of using a full black box AI models, we present a physics-informed neuro-ODE framework and with the general format written here. So the basic idea is that we start from a simple physics model written in simple sets of PD and ODEs, and then such as the wave activity, barotropic QG model, or the recharge oscillator for ENSO. And then there will be some high-dimensional nonlinear components that will be learned by neural residuals. And then both components will be integrated forward to represent the climate state evolutions. And so here I will use ENSO as an example. This work was inspired by the extended recharge oscillator at Zhao et al. And Nature paper. So basically they show that by including the cross-basin interactions into the recharge oscillator, they are able to produce a prediction scale of ENSO pretty much better than most of the global climate models. So here they first have two linear ODEs to describe the ENSO, the recharge oscillator behavior. And then to account for the asymmetry of ENSO, they use a pretty idealized quadratic terms here. And then for the basin interactions, they introduced 8 additional ODEs to describe the time evolutions of all these climate modes. And then the interactions between the ENSO mode and non-ENSO mode are purely linear. And then they also have idealized simple nonlinear terms for the IOD mode. So from here, you can see what is missing. So basically, there are no nonlinear interactions between the ENSO mode and the other climate modes. And there's also no nonlinear interactions between the cross-basin, different modes cross-basins. So here to address these issues, we introduce a neural extended recharge oscillator. So here again, the first turn in the left-hand side is basically a linear turn. It represents the linear recharge oscillator behavior, as well as the linear interactions between ENSO mode and other modes. And then to account for the annual and semi-annual cycles, we also implement these informations into this linear operator. And then for the nonlinear interactions between all different climate modes, here we implemented 4 different AI architectures to understand it. That include 2 sparse graphs, neuro-ODE, attention-based model, and MLP. So here we have a much less trainable parameters in the realm of hundreds to about 2,000, so it can just train in a couple of CPU hours. And then so basically by minimizing the loss functions every time step, we can eventually learn the structures of both linear and nonlinear operators. So here we use both reanalysis data and the CESM large ensemble to train our model, and the training and validation split is on the top. So here we have 2 different training protocols. So first, in a single stage training, the model is purely trained on the reanalysis data and validated on it. And then to expose the model to a wide range of variabilities, we also use the CESM2 transfer learning protocol. So basically, the model is pre-trained on the CESM2 lens and then fine-tuned on the reanalysis data. So here, let's look at the single stage training results. Here I am plotting the out-of-sample test for the Nino 3.4 on MSE across all different lead times. So the black dashed line here is the XRO baseline, and all the solid color lines are different model variants. So basically, we see that across all 21 lead months that we consistently outperform these XRO baseline. And then more specifically, if we look at the 12 months IMSE reductions, we are achieving about a 13.2% better than the XRO baseline. And then if we compare the transfer learning with no CSM transfer learning results, we see some models have improvements on this strategy, but some are not. So for the models, the MLP and Neuro ODE, they have no improvement. And then we think this is because both architectures has the fully connected networks that might learn some more specific nonlinearities that is only for CSM2 only. It does not really represent it in the reanalysis data. And so then we also performed a stochastic hindcast at 6 months lead time for our models. So as you can see, we achieve a pretty reasonable prediction skills. And with that, was also reasonable ensemble spread. And then let's see our learn structures of this linear coupling operator. So basically, the L is this huge 10 by 10 matrix. So if we only look at the couple 4 panels, that is basically the recharge oscillators. And then it pretty much learned pretty well the seasonal vary relationships between linear flow and the warm water volume. Here we can also see these heat content will lead to the development of the El Nino. And then, for example, if we look at how the ENSO interact with the IOB mode, we also see that the El Nino-induced heatings can basically enhance the tendency of the IOB, which is also documented in many of literatures. And then the last, we have all these nonlinear learned couplings between modes. Here, for example, if we look at the nonlinear interactions between ENSO modes, which is quite well known as the because of the oceanic nonlinear dynamical heatings, which leads to the scaleness of both the subsurface temperature distribution as well as the SSE skewness. And then we also have the nonlinear interactions between ENSO modes as other modes like the IOD and SIOD, which is also quite well documented in the literatures. And then in terms of the ENSO mode and the equatorial Atlantic modes, and then we can also see these are represented by the changes in the deep convections, early Walker circulations. And in terms of the couplings between the different non-ENSO modes, here we also see a strong connections between the Indian Basin modes and also the Atlantic variabilities, which is also documented in lots of literatures, incorporating with the waves dynamics as well as changes in the Walker circulation. In the meantime, this model also learned some quite interesting behaviors that I don't fully understand. For example, it learned quite strong nonlinear interactions between the North Pacific meridional mode and South Pacific meridional mode, which I have no idea why it's there, but maybe it's due to MPO and SPO, or the cross-equatorial wind fluxes due to the interhemispheric energetic differences, but I'm not quite sure. And it also has a quite interesting relationship between the South Pacific meridional mode and the South Atlantic subtropical dipole. And I found some non-ENSO related literatures, but basically they found that the deep convections, such as MJO in the Indo-Pacific warming, may enhance the deep convection and then trigger the Pacific South American wave stream patterns and eventually cause blocking or high temperature anomalies in the South Atlantic. But yeah, so that's pretty much the contents I have today. So the take-home message is that we have implemented a pretty simple physics-based AI model. It can be trained very easily, and it's physically interpretable. And it will also show in the ages of AI advances, models and physical theory is still very important, just like the recharge oscillator implemented many decades ago. Yeah, thank you.
We have time for one really quick question.
Thanks for your talk. I like that you pointed out the difference across the trainable parameters for each of the models, and you kind of alluded to this with the fully connected neural network results. Have you thought about, do you think actually making the number of trainable parameters more similar across those different models would change your results, or do you think it's close enough that?
Well, yeah, so we intentionally make the attention and the graph model to be as sparse as possible because we only have like monthly data to train, so it's pretty tiny data sets. So if you match the training parameters, then you will need like more data. And then we also show that an attention-based model as well as these sparse graph are actually performing pretty well in a sense. So yeah, thank you.
Wonderful, thank you. Our next speaker is Danny.
Hello everyone, I'm Danny and currently I'm a second year postdoc at Princeton University. And in this presentation, I will be talking about some results about a relatively new pathway for mitigating the climate model biases through learning from the data assimilation increments. We know that due to the limitation of the computational powers, usually we only have the coarse resolution climate models where we cannot explicitly resolve all the critical physical processes, such as the convection in the atmosphere and the waves in the ocean. And because of this, we do need the parameterization, which is a proxy of those physical processes. However, those parameterizations are also a major source of the model biases. Taking the multi-model ensemble mean sea temperature, for example, as shown in this figure, studies have shown that the CIMIP-6 model still show the long-standing systematic biases, including the cold biases in the northern hemisphere, such as the cold blob in the North Atlantic. And studies consider this to be part of the misrepresentation of the mesoscale eddies there. And also there's the warm seas of temperature in the western coast of South America and Africa, as well as in the Southern Ocean, which might be related to the misrepresentation of the cloud-related physics. And usually it is very hard to identify a single process that can account for those biases, because usually the model biases, they come from the multiple sources and sometimes even unidentified. And so why not we change some perspective to view those model biases in a compound perspective. And this is where we can learn from the data assimilation. And here is just some schematic diagram of how the data assimilation is working. And the gray dots, they represent the analysis state. And the red curve here is the observational state, while the gray curve here is the model forecast. And here the black arrows are just the data assimilation increments that's pushing your model forecast towards the observations. And if we have an unbiased model, then usually those black arrows, which represent the data assimilation increments, they should be randomly positive or negative. And with the long-term average, it should be approximately 0. However, usually we always have the biased models, and that's why we have those systematically positive or negative data assimilation increments. And here is an example of the GFDL Spear model. When we average the data assimilation increments for the CESM temperature over the 12-year period, we do see there's the systematic and the large-scale, as well as finer-scale patterns of those positive or negative data assimilation increments. So the question here is, how can we learn from those data assimilation increments, and whether or not we can derive some online bias correction schemes out from those data assimilation increments? And one successful practice utilizing those data assimilation increments is through the climatological corrections. So this is the ocean tendency adjustment method that has already been used in the GFDL Spear seasonal forecast. And it is basically like computing the climatological 3D corrections from the data assimilation increments for the ocean temperature and ocean salinity. By saying 3-dimensional, I mean the longitude, latitude, and across the depths. And by deriving such By computing the monthly climatology of such 3D corrections, you can further interpolate it into the daily corrections and apply online to correct the model biases. And in the previous study, they've shown that such climatological corrections can reduce the biases related to the ancel in the Nino 3 and Nino 4 region. Taking this figure, for example, there are three figures that's without such there are three figures that is with such climatological corrections, and the last one is without such climatological corrections. And obviously, we can see without such corrections, there is this cold biases developed in the subsurface of the Nino 3 region corresponding to the thermocline there being too shallow. While with such climatological corrections derived from the data assimilation increments, we can significantly reduce the cold drift in the Nino 3 region. And to take one step forward, we can now derive some machine learning based corrections out from those data assimilation increments. So this time they can be state dependent rather than those climatological corrections, which are state independent. And here we utilize the 12-year daily data assimilation outputs as the training data. And in our pre-run data assimilation, we do have 30 members. However, because we have redundant data, so we only subsample from the 5 ensemble members each year. And for the validation data, it is 1 ensemble member for a different year, and the testing data is another ensemble member for 2015. And for the training data, as well as the validation data, we focus on those Argo assimilated columns. Oh, I forgot to mention that our machine learning architecture is column-wise, so we focus more on those local vertical structures than the horizontal structures, because we, from the preliminary results, we identified that the vertical structure is the older one biases that can be indicated from the DA increments. The reason we focus on the Argo assimilated columns in the training is because it has more realistic vertical structures to represent those errors, while for the testing data, we focus on all the available ocean columns to test whether or not our derived correction can be generalized across all ocean status. And also we convert the vertical coordinates based on the depths to a sigma coordinate relative to the mixed layer so that we can have this uniform format for all the ocean columns. And then we, based on our physical understanding, we chose the mixed layer depths, the Coriolis parameter, and the 4 vertical profiles, including the vertical gradient of the temperature, salinity, the current shear, as well as the vertical profile of the horizontal potential density gradient. And then we utilize those inputs and throw it into our machine learning model, which consists of an encoder, attention mechanism, multilayer perceptron, and a decoder. And finally, we can derive the vertical profile of the DA increments predicted by our ML model and compare it with the DA output to backward propagate and optimize the weights of the machine learning model. And here is the result of our trained machine learning model in the offline framework. So the top panel is the annual mean pattern, and the bottom panel is just a daily snapshot. On the left is the truth, and on the right, this is predicted by our machine learning model, and we can see the good correspondence. And systematically evaluated by the correlation coefficient, we do see that, so here the figure E, it has the sigma depth as the vertical coordinate and the correlation coefficient as the x axis. And we can see indeed within 1 mixed layer depth, the prediction scale of our ML model is very high, while gradually it is decaying. So it is inferring that we are indeed capturing some vertical mixing related biases. And then we just implement this scheme online to the GFDL Spear model, and this is an evaluation of the 10-year mixed layer depth climatology. Figure A shows the control simulation without any corrections. Figure B shows the climatological corrections, which is our baseline, and figure C is using our machine learning corrections. And very obviously, the machine learning simulation is a winner. And the reason is because learning from the data, it indeed grasps the correct physical mechanisms, which is related to the submesoscale eddy restratification. And traditionally, the parameterization of this process utilize these variables highlighted by the red circle. And our machine learning model is correctly taking up these correlations, these relationships as shown by the attention weights of a latent feature derived from the horizontal density gradient. And it is looking at the correct timing, correct seasonality, correct locations to produce a better representation of those mesoscale eddy processes so that the mixed layer depth climatology can be improved. So in the summary, we can this offers a promising new pathway that is learning from the DA increment to correct the model biases without identifying any single process misrepresentation of the model errors. And I'll stop here.
Thanks, Danny. We have to move on to our next speaker, Max.
Hi, everyone. I'm Max Baumann. I'm a PhD student in Veronica Eyring's group. And today I will present, wait a second. There you go. Today I will present the ongoing efforts on automatic tuning and parameter uncertainty quantification of IconXP. And I want to just take a moment here to thank all of my co-authors and collaborators, especially Linnea and Katie, for hosting me here this summer. All right, so why do we need these automatic tuning pipelines? So first of all, as you probably all know, parametric uncertainty contributes significantly to overall model uncertainty in climate model projections, and we would like to systematically reduce this. And second of all, and this point has been touched upon by also Julien this morning, and Da and Adisu, that the retuning is a crucial step in the workflow of developing data-driven parameterizations, and especially implementing these in hybrid models. And to show this, I would like to use this example from a colleague of ours, Arthur Grundner, at the German Aerospace Center. So Arthur basically created this data-driven cloud cover parameterization using equation discovery. And Julien showed the equation for this morning. And basically, he trained and tested this parameterization offline, and then the results looked quite good. When he implemented it to the climate model, actually the results initially didn't look so great. So he came up with a fast, efficient tuning method to basically improve the results, utilizing a lot of short day-long simulations. And as you can see here, for a few climate metrics, actually these short day-long simulations already improved the results by quite a bit. And then in the last step, he basically extended those tuning simulations to week or month-long simulations. And as you can see, the results look much better than in the beginning. So this pipeline works especially well for the atmosphere, since it's characterized by fast responding processes, and therefore it has short memory. And I would like to present to you this pipeline, as well as some of the adaptations that I made to it. And in the second part of the talk, I would like to talk about the quantification and reduction of land model parametric uncertainty with a focus on land-atmosphere interactions. And for this pipeline, for this system, we have like slower responding processes and also therefore longer memory, and we need a different kind of pipeline. So we'll try to compress all of this in one talk without speeding up too much and sounding like a robotic Iron Man. So here's like the model that we use. This is IconXP. XP stands for Extended Predictions and Projections. We use it in RTP4 configuration, so that's roughly 160 kilometer resolution, in AMIP style. And then the atmosphere tuning workflow looks like as follows. So we start with an initial 2-year simulation. The first year is just used to spin up, and in the second year we use it to output some restart files at the beginning of each season. And those restart files are then used to basically as initial conditions for some tuning runs. But we first start with just our default parameter configuration. We run some simulations for each month, and then basically use the automatic tuning pipeline to post-process the output, calculate the loss with respect to observations, sum the loss over the metrics that we're interested in, and then we feed the parameter configuration as well as the loss value to an optimizer, and the optimizer will then provide a new parameter configuration. So what this visually looks like, I just want to mention here that we use, in this study, the downhill simplex algorithm, but it can in principle be replaced by any other gradient-free optimization method. This is also known as Nelder-Mead. Or you can use any emulator-assisted tuning approaches. So basically, we provide the initial parameter, default parameter values to Nelder-Mead. It does some sensitivity analysis, and it runs ICANN directly for all of these parameter configurations. Then the tuning pipeline will compute the loss, and this loss is then fed back into the optimizer, which will come up with a new parameter configuration to try. And so it will systematically reduce the loss, and in the end we will end up with an optimal parameter set for day-long simulations. And what we then do is basically we repeat this whole step, and we feed the optimal parameter set for day-long simulations back into the beginning of the pipeline, but then we extend the simulations to week-long. We go through this whole process again, and then we end up with an optimal parameter set for week-long simulations, and we repeat the step once more for month-long simulations. So as you can see, the shorter simulations inform the longer ones. And here's an example of the results. So I first want to mention that I use adaptive multi-observational bounds to account for natural variability in the system. And I use these observational data sets to calculate these observational bounds. And as you can see in the figure at the top right, the short tuning simulations inform the longer tuning simulations. And you can clearly see this. So the figure shows the effect of the parameter optimization on the long wave cloud radiative effect. And you can see that the shaded areas are the observational ranges, and in the beginning the metric is pretty far out of the observational bounds, but it's being iteratively pushed towards the range, towards the observational range. Then we take that optimal parameter set that we find for the day-long simulations, and we basically feed that back into the whole optimization process for week-long simulations, which then informs the month-long simulations afterwards. Once we're happy with our tuned parameters, we basically use those parameters to create a simulation of about 25 years that we can use for evaluation of our tuned model. And for this, we use the CESM vol tool. And I won't have time to show all of the analysis, but you can find that using the QR code. And I just put here an example plot from the CESM vol tool showing the top of the atmosphere net radiation budget for both the default member as well as the tuned member. All right, so now I want to, if I have time, shift quickly towards the quantification and reduction of land model parametric uncertainty, focusing on land-atmosphere interaction specifically. So this workflow is inspired by a study from Katie in 2020. Basically it consists of 3 steps. We start with pre-selecting a certain amount of parameters, in this case around 30, based on expert judgment and previous model tuning studies. Then we use those pre-selected parameters to conduct a sensitivity analysis, in this case a one-at-a-time sensitivity analysis, which basically means that we take each parameter once at a time, we perturb it to a high value, run a simulation, low value, and another simulation. And then we analyze the effect of the parameters based on the global effect that they have, the absolute effect, as well as using some spatial pattern correlations. With this, we can make a ranking of the most influential parameters, and let's say the top 10 or roughly top 10, we use then for history matching. And history matching is a framework that uses perturbed parameter ensembles as well as Gaussian process emulators to iteratively rule out implausible regions of the parameter space. Here I will show some, just 2 slides with some results of the sensitivity analysis. So we selected 29 parameters, pre-selected them. We run the one-at-a-time sensitivity test. The parameters come from the modules that you can see on the top right of the land model. These are the metrics that we're interested in, so mainly the fast biogeophysical processes focusing on land-atmosphere interactions. And I won't go into too many details, but I would like to draw your attention to the last row, which is the Golem dataset, which is created by Nesinin from Paul Diermeier's group. She gave a talk on Monday. I won't go into too many details, but to my understanding, this is really the first observational data set that we can use to constrain land-atmosphere coupling in climate models. So just shortly the effects, the parameter effects. So here in the plot you can see all of the parameters that we've been perturbing on the y-axis, and then the metrics that we're interested in on the x-axis. And the color shows like the importance of the parameters. So the more yellow it is, the higher the importance, the more pronounced the effect. And as you can see, most of the metrics are really driven by just a handful of parameters. But we're not only interested in the global parameter effect, the absolute effect, but also at the spatial pattern correlations. So here I basically plot on the x-axis the importance and on the y-axis the spatial uniqueness, because we want to have parameters that also have a unique pattern around the globe. And so we really are interested in the parameters that fall along this diagonal. So I just will wrap up here. This is the current status of the work. Now we're going to do some history matching waves to iteratively improve the emulator performance and rule out implausible parameter regions. And I will just put these summary blocks here on the slide so that you can have a look at it. Thank you very much.
Thanks, Max. We're going to have to move on to the next speaker. Leo?
Hey, there it is. Cool. All right. Thank you. My name is Leo Balser. I am a graduate student at the University of Wisconsin-Madison. Oh, we have gone forward. Beautiful. Spoiler alert. All right. This is a very rough overview of some preliminary results from a study I'm working on with Dan Weimont and my advisor, Hannah Zanowski, at the University of Wisconsin-Madison. This is k-means clustering as a tool for categorizing Arctic sea ice decline within our suite of Earth system models. So with that, we understand that the rapid retreat of Arctic sea ice is a robust signal of our changing climate, and however, that is represented pretty differently across our current generation of climate models. Specifically with CMIP6, we tend to underestimate the sensitivity of sea ice area to a degree of global warming. With that as well, there are also known biases with all of our models in terms of sea ice thickness across the Arctic too, and those biases are spatially heterogeneous as well from model to model. Furthermore, traditional methods of statistically categorizing models by their performance is a non-trivial task that many have devoted a lot of time to. So with that, very first order question is, what other tools do we have at our disposal that we can use to categorize the decline of Arctic sea ice? And so with that, this is where I'll be introducing the culprit of our talk today. This is k-means clustering. It is a popular, simple, and computationally inexpensive machine learning technique that is used to group large data sets into clusters of similarity. And so it goes according to this algorithm here, where you choose a number of clusters according to some scoring metric. You initialize the centroids, or those red X's on the plot to the right. Those will act as metrics for grouping the data itself. You'll assign each data point to its nearest centroid, and then you'll update the centroids by taking the mean of all of those assigned data points in relation to that one, and then you'll update the location of that centroid. Repeat that over and over and over again until you have select groupings of data within your space. The key point to all of this is that, again, k-means clustering is useful for reducing large quantities of data down to a subset of similar characteristics. So that's exactly what we'll be doing today with some September sea ice concentration data across CMIP6. Specifically, we'll be applying clustering to decadal trend maps of sea ice concentration taken from between 1980 and 2015. And this is the host of CMIP6 models we'll be looking at today. They're chosen for both the diversity of their constructions and for their offering of a broad range of different ensemble members that we can look at. For the sake of timing as well, we're not going to be talking about the large ensemble today. There's a few steps to treating the data prior to feeding it through the algorithm. The first of which is that we regridded all of these trend maps to a common half-degree resolution grid, and then we constructed a landmask from that multi-model mean to make sure that the model's native geometries, specifically at the boundaries from the ice, the sea ice and land, don't influence clustering results. And then we also weight each grid cell by the square root of cosine of latitude to make sure that we're not biasing towards grid cells closer to the poles. And so this is an example of choosing the optimal amount of clusters here. In red is the elbow method. Blue is our silhouette score. Silhouette score tends to be a bit more robust than the elbow method. But high values at lower numbers of clusters is a pretty good indicator that our data is not very well separated. And I think if we look at data flattened spatially, that tends to make sense, right? Over 295 members that will be feeding through this, flattened down, that's about 17 million points of data that are all distributed between -4 and 3% per year. So not a whole lot of separation. So for our purposes today, let's just try k equals 3 and see what we get. So this is what it looks like in implementation. There is a known package for this in Python, scikit-learn. We set up our number of clusters, we initialize the algorithm itself, and then we pass our flattened, unlabeled CMIP6 data through that algorithm. And then the raw output comes in the form of a list of labels. And so these labels indicate which centroid each individual member was assigned to. And working backwards, we can also figure out where those assignments relate to the models that we first passed in. And so we can take that and turn it into a bar plot, and that kind of gave us our first surprise with this, in that it sorted those unlabeled trend maps of sea ice concentration trends back into their original models, save for EC Earth 3, which had about a 40-60 split between the second two centroids. That kind of led us to two questions. Why isn't there more overlap in those assigned clusters? And why are certain models grouped together? For example, why are CESM2 and IPSIL the ones that are contained to the first centroid? To dig towards an answer, we can plot those centroids. And so these are what the algorithm picked as the three most common spatial patterns of historical September sea ice loss in the Arctic. The first one is a pronounced loss in the central Arctic, which reflects, well, I won't spoil that. The second is, much less sea ice loss in kind of that annular shape around the marginal seas. And then the third is that same annular shape, but with a much more pronounced trend. And so taking that previous bar plot and now just showing the models that were assigned those clusters, we see that the CMIP6 version of CESM2 and IPSIL were sorted to cluster 1, and then clusters 2 and 3 have their models. And so today we'll just be focusing on that first cluster for the sake of time. So trying to figure out why that was the case, why these two were grouped together. First things first, let's look at the literature and see what are their mean states and what are their climate sensitivities that could be influencing that decadal sea ice trend. And, as has been shown by many previous studies, these two models have very similar mean states and climate sensitivities in the Arctic. And moreover, this has been shown to result from different sources of biases in their respective constructions that led to similar signatures of amplified warming and sea ice melt in their Arctic. And so with that, this isn't a particularly new, not a new insight by any means. This is all stuff that has been found before, but I do think it's encouraging that a simple machine learning algorithm was able to pick up on these sources of model biases and group the models together accordingly. And so to summarize, we can say that k-means clustering is an inexpensive and a highly explainable method for organizing our large data sets into a set number of clusters of similarity. And moreover, passing unlabeled CMIP6 sea ice concentration trend members through that algorithm sorted the output very closely back into their original models. which, groupings were based on, or seemed to be based on having similar mean states, climate sensitivities, and underlying biases. With that, it could also be a useful tool for looking into future intercomparison efforts, especially as we inch closer to our CMIP7 DEC experiments. So with that, thank you very much.
We have time for a question.
That was really cool. It's a really interesting methodology for classifying points. I was curious, when you showed the plot before where it's like you're flattening all these points and seems like really hard to pick apart these clusters, is there a precedent for like adding n more dimensions to kind of like blow up your data set more and separate out these clusters, maybe?
It could definitely be done. I'll be very honest, this was the result of a class project that I did for a class that Dan was teaching on, statistical methods and climate analysis. So it's not something I've looked into necessarily, but I don't see why you couldn't try to discretize your data a bit more prior to feeding it in.
Cool. Yeah, really cool work. Thank you.
Thanks. Appreciate it.
Awesome. Thanks, Leo. We're going to move on to our last speaker, Sky. And while Sky is coming up, we're running about 5 minutes behind. I'm hoping they're running longer so we can get lunch first. But I just want a reminder to recycle your aluminum or aluminium cans, depending on how you say it. And then we also have a selfie station that you can take photos at, and make sure you tag CGD and CESM in them. So, great.
Cool. Thank you. Thank you to you all for sticking around. I did practice this to be 6 minutes instead, so we should be good. But I'm going to be talking about how we use machine learning to quantify the role of internal variability for this application. I should say first, thank you to all my collaborators. This was a very big effort across many expertise, and I appreciate all their input. Okay. So to start us off, we're looking broadly at this problem of Arctic amplification, where the Arctic is warming faster than the globe. We're referring to the near surface air temperature trend compared to the global mean. And we can quantify this as a ratio, as you see there. So this is most commonly used and what I'll be using when I refer to AA. This is unitless. And what's really interesting from the observational perspective about AA is you see this really strong acceleration in the observed trends of the Arctic from 1980 to 2022. So this is the period that we will also be looking at, compared to the global mean, which is in more faded colors back behind. I also want to point out that AA is a robust, known response to any climate forcing, as it's driven by local feedbacks and polar heat transport changes. But the implications and drivers behind AA still are very hard to quantify and mechanize, particularly on a seasonal scale. So that brings us to why we're looking at the springtime. Wow, this loses a lot of color. So this is the seasonal cycle of Arctic amplification, again from 1980 to 2022. The box plots are various CMIP6 quantile statistics, and then the observations are in red. You probably first noticed this very obvious, if it'll go. Maybe it won't go. Okay. Okay, well, there's a very big difference in the springtime, which is why I'm focusing on that. Maybe if it shows up, the mean observed AA in the spring for observations is 4.2, and the multi-model mean is only about 2.7. Oh my gosh. Okay, we'll just walk through this all together now. So the observed spring surface air trend in the Arctic, so just looking at the numerator of our ratio, does lie within the CMIP6 intermodal spread, suggesting it could be due to internal variability, among many other suggestions thrown out for this difference. And building on the work of a previous grad student in my group, Aidan Sweeney, he reconciled the difference in annual mean AA. So let's see if I can, So he's looking at this problem here. With a machine learning algorithm, we're building on this for the seasonal problem of the springtime now. So just to walk us through, all of our observations are from these 4 surface air temperature data sets. We also have 3 sea level pressure data sets we're using. And all of our models come from 12 large ensembles, so including the CMIP6 suite, as well as the smooth biomass burning version of CSM2 and E3SM version 2. So large ensemble is anything with 10 or more ensemble members, and we create this extended sampling space over here by combining the historical with some future scenario, given what was provided. And from this, we can generate tons and tons of 43-year SAT and SLP trend maps from simulations, as well as the simulated externally and internally generated trends. So these are going to be our predictors in our machine learning algorithm. As this is harnessing ML, I thought I'd walk through how we do this. So we're using a convolutional neural network, which, as you all know, is a very powerful tool for image classification and has become increasingly used for geospatial data. So here, in our case, we're using SAT and SLP trend maps as our predictors. Again, P number 43-year periods from this extended sampling space. Then our predictands are quite simply just the internal and external SAT trends, so very simple matrix. And we want our CNN to learn the relationship between the predictors and the predictands. We do a leave one out cross-validation with all of our models. So our CNN at any one time is trained on 11 models and tested on the 12th one that's left out. Of the 11 that we're training on, we select 10 random ensemble members, so we don't weight it towards any one particular model physics. And then again, our test is going to be predictions of the internally and externally generated trends of every member of the left out model for 1980 to 2022, so we can look at comparisons. The last step is to just simply give the CNN the observed SAT and SLP trend maps. The novelty here being the CNN doesn't know what's simulation and what's observation, so hopefully it's giving us a very good estimate of the real world trends of internal variability and external forcing. So this is what the results are. There's a lot to take in, but the Arctic results are on the top and the globals on the bottom, as we need to calculate both values for our ratio. We have our internal predictions in the left column, external in the middle, and then the sum is on the right. We don't predict the sum. This is just a nice post-model check that we get to use, so we're not predicting any outrageous values. The closer the dots are to the one-to-one line, the better our model is performing, and you can see it's doing pretty well. We did a lot of really strenuous tests to make sure we got this result. And again, there's so much you can do with this, including looking at how different models perform, but we're just going to be using two numbers, and that's going to be the estimated mean observed internal Arctic trend, so the mean of those 4 vertical black lines. That's our estimations from our CNN for observations, and that for the globe. And we're simply going to remove these from the actual trends of the Arctic and the globe for the spring mean of 1980-2022 and calculate an observed for spring AA, so like an apples to apples comparison with the multi-model mean. So when you do this, you get 2.7, which is the value of the multi-model mean. So at least for the springtime in the Arctic, internal variability is driving that difference that we saw. It gets a little interesting when we break it down on the monthly scale. So this is just showing you what's happening between observations and the multi-model mean for surface air temperature trends. Observations have a lot more regional variability going on. There's cooling in North America, and there's warming particularly across continental Siberia, with a peak in April in particular. Whereas the multi-model mean is generally more uniform, so you would expect this from the forced response. And we repeated this CNN method with each of the different months to really understand what might be going on at this scale. So here I'm just showing you those observed trends as well as the multi-model mean trends for comparison, and then what we get from the CNN, so just that final mean observed estimation. We also did this with a more linear machine learning method of partial least squares. We did this with a dynamical adjustment, which only occurs in observed space. There's no simulation data going on here. And we also did this with PI nudged runs. So these are wind nudged a CSM2 ensemble made by Ash Gilbert, if you saw their talk yesterday. So thank you, Ash, for the data. But the goal for the PI nudge runs was just to understand the role of winds in the Arctic climate. And what you see here, so many things. The first one being that internal variability accounts for about 40% of the observed April SAT trend. So quite a large amount of the trend is driven by internal variability. There's very good agreement between the CNN and the PI nudge methods for these months. So that really links our internally driven warming to wind-driven warming. And finally, I want to point out that our more nonlinear or physical methods tend to attribute slightly larger trends to internal variability than linear methods. So this was alluded to earlier, but using methods that can capture nonlinearities is super important. Okay, with that, I'll leave my takeaways here and let you all go to lunch. Thank you.
I'm not going to let you go to lunch because we have time for a question if anyone is interested.
Yeah, thanks for your talk. And maybe I missed this, but when you were showing the internal versus external scatter plots, the external plots had some kind of interesting line behavior in the results. Could you talk about what's causing that?
Yeah, good catch. I did talk about it in like 20 seconds. So for the models, when you calculate the external trends for a large ensemble, that's going to be the same value for all of your ensemble members, as we're just taking the ensemble mean as the external forcing. But our CNN actually predicts slightly different values, which is where you start to see that spread amongst the values. So they're constrained by the, our calculation of it, but then their CNN has a little bit of spread. Yeah, good question.
Great. Well, thank you. And let's thank our speakers one more time, and then you can all go to lunch.
All right, we're going to go ahead and get started. Welcome, everybody, to the BGC Working Group session. My name's Kristen Crumhart, and I am one of the BGC Working Group co-chairs, along with Abby Swan and Gretchen Capel-Alex, who unfortunately are not here today. We have a great session of talks, a lot of Ocean BGC this time, and I just wanted to remind everybody of the code of conduct, which isn't up there, but it's basically just be respectful and nice. For this session, each speaker has 18 minutes or 18-minute time slot. So keep it to about 15 minutes and then have a few minutes for questions. And then online participants can ask their questions with the Slido. Let's see. Our first speaker is Shannon Wang from Xiamen University in China, and she'll be talking about the impacts of ocean acidification on marine ecosystems. You could advance with this. You can point this is the laser pointer, and you point it on the screen. Sorry.
Okay, great. Thank you. Good afternoon, everyone. Thanks for having me here. And today I'm going to talk about the impacts of ocean acidification, mainly on phytoplankton. The reason why we want to study that because phytoplankton is really important. It's the backbone of our marine ecosystems. And even though the biomass, phytoplankton accounts only about 1% of the total biomass, but it produces half of the organic matters and really play a big role in ocean carbon cycle and regulate climate through the biological carbon pump, and also regulates the cycling of key nutrients and key elements in the ocean. In previous studies suggested the phytoplankton or marine ecosystem are under multiple stressors, including warming and stratification and acidification. Some climate projections suggest will research on how warming and climate change may affect the diversity or evenness of the community, as well as how the stratification and nutrient condition warming may affect phytoplankton. There have been some study on the impacts of acidification on phytoplankton, but the combined effect of acidification and warming on phytoplankton are less studied. And that's because in the past, the impacts of acidification usually studied using cultural experiments in mesocosms. But with laboratory cultural experiments, they usually use one string or two variables, varying one or two variables at most. And also, most of the Earth system model ignore the impact of acidification on phytoplankton. So for that reason, we're trying to incorporate the oceanification impacts based on laboratory results in situ experiments data into the model and see the impact of acidification. Okay, so for this work, we sort of modifying the marble structure a little bit. We have our own version of the code. We expand the phytoplankton into 8 functional groups. First of all, we expand the PICO phytoplankton groups, PICO and nano phytoplankton groups based on the work from Rob Lecture, and where we expand small phytoplankton groups into Prochlorococcus, Synococcus, and Picoeucharis, and also other nano phytoplankton groups. Also, we expand the nitrogen fixer from one nitrogen fixer represented by trichodesmin into 2 nitrogen fixers, which are Crocosphila and trichodesmin. Crocosphila is one type of nitrogen fixer, is the unicellular nitrogen fixer, which can play important role in mid to low latitude, in that they account for almost a third of the nitrogen fixation there. And also we incorporate coccolithos based on the work done by Kristen. And all the parameters are tuned mostly based on the size of phytoplankton sizes and also with laboratory results. And here I'm just quickly showing the simulated results of these phytoplankton groups in the distribution. So it seems this version of code works okay to capture the general pattern of different phytoplankton groups. And then for the oceanification effects, we only considered oceanification effects mainly based on cultural experience results from our collaborators. So traditionally, people do the culture based on nutrient replete conditions. They consider nutrient acidification as the only stressor for phytoplankton. And my colleagues also have quite some experiment results based on this nutrient replete condition. But recent years, they also expand the cultural experiments to consider the nutrient limitation condition. So basically, they have cultural experiments under iron or phosphorus or nutrient limited conditions and see how phytoplankton may respond to acidification under nutrient limited conditions. And so for our study, we also tested two sets of acidification factors. So the way how we incorporate those acidification factors based on this linear assumption. So in general, the cultural experiments only have two levels of carbon dioxide concentration. So we have to do this linear assumption, assuming the response of phytoplankton to acidification is proportional to the changes of the hydrogen ion concentration. And then, so one is in nutrient replete assumption, we have incorporated into the equations calculating the growth rate, quota, and as well as nitrogen fixation. And then in the second set of coefficients, we first determine the limitation condition and then incorporate those acidification factors accordingly. Here I'm presenting three groups of simulation. The first group of simulation used the GCase, the GRA55 forced ocean ice coupled cases, and to represent the present day physics. And then the second, the third groups of experiments we use the SSP scenarios. So first of all, I'm going to show the difference between when we use the acidification factor, the coefficient based on nutrient replete condition, as well as the ones with the considering the influence of nutrient limitation. So as you can see, under the assumption of that acidification is not affected by the nutrient concentration, we see only diatom and picoaceries show significant changes here. But when we consider the nutrient limitation condition, we see much significant changes in the biomass of different phytoplankton groups, especially the smaller sizes, the Prochlorococcus and Synechococcus, we see almost double the biomass. And we can also see with this acidification factor considering the nutrient limitation, we see much stronger heterogeneity in the spatial pattern of MPP and POC export. As you can see, the overall net primary production stay almost unchanged under the condition, the assumption of that nutrient limitation do not affect the acidification impact. But with this, the second set of parameters, we see a significant changes in MPP and POC export. Also, the dominant phytoplankton species also changed here from diatom dominant in this mid-latitude to the smaller Prochlorococcus and Synechococcus dominant station scenario. So it seems if we extrapolate the impact of acidification on global scale using the parameter gained from culture experiments, then with neutron replete condition, it's likely we get a totally different answer than in the real ocean, where we often get neutron limiting conditions here. Also, I'm showing you some detail in the second set of parameter setting where we consider the neutron limitation. And as you can see in this set of simulation, the oceanification factor is drawn here, and you can see as when R is limited, the Prochlorococcus and Synechococcus, the growth of those two groups is promoted by acidification significantly likely due to the CCN, the carbon concentrating mechanism, but Piccoiocaris is surprised by under the nitrogen limitation condition, and due to both the neutron limitation condition change as well as the acidification factor here, we see the dominant species change significantly from Piccoiocaris dominant groups into the smaller Prochlorococcus and Synechococcus dominant groups. Also, I want to point out significant changes here in the Trichodesmin and Crocus phyla. So actually, in cultural experiments, both groups respond negatively to acidification. So basically, as you can see here, both groups, the growth and nitrogen fixation rate respond negatively to acidification under iron and phosphorus limitation condition. But when we have them combined together and simulate, since the Trichodesmin responds more negatively to acidification, this group decrease, the growth of Trichodesmin decreased significantly, as well as the nitrogen fixation from this group decreased significantly, in which decrease the nitrogen availability to other phytoplankton groups, give more competitive advantage to Crocus phyla, which actually lead to the growth of Crocus phyla. So this is totally different from the result we expect from cultural experiments. And then for the next, I'm going to present the second group of simulation where we have the control simulation using SSP 3.7.0 from 2015 to 2100, and compared to the one with acidification effects, considering the influence of neutron limitation. As you can see, if we only consider the warming effects, then probably we have a very weak increase in the net primary production, as well as a minor decrease in the export production. But when we combine the effects of warming and acidification, we actually see this tipping point in the net primary production. Cause of this turning point, and we see is likely caused by these three phytoplankton functional groups, the Synechococcus, diatoms, and Piccoiocaris. And we see significant decrease in diatoms, and as well as the long-term decrease trend in Piccoiocaris. Then we also see this increase in this Synechococcus. And we try to analyze those. We found the main change happened in the main latitude and also the subarctic, North Pacific. In different regions, the mechanism driving this turning point may be a little bit different, but overall is the combined effect of oceanification and nutrient availability. And then we try to compare the interactive effects of warming and acidification. So to do that, we calculate this using the scenario project scenario from 1991 to 2100, and compared to the 21st in 2030, and then calculate as the in the control case, we consider that's the overall effect of warming. And then in the oceanification simulation, That's the total effect of warming and oceanification. We compare that to the G-case simulation. Of course, we don't expect the G-case simulation can compare directly or identically to this present day or the no warming condition, but at least it can give us a hint of this interactive effect. As you can see in the table on the right, in several parameter values change significantly. For example, the net perimeter production from Prochlorococcus and Synechococcus, as well as diatoms. For example, when we consider present-day scenario where we only consider acidification effects without changes in climate system, then we see the diatom biomass actually has minor increase, but when we have both warming and acidification, we actually see a decrease. Also, we see a big increase in both smaller size phytoplankton groups. And then another big change will be the nitrogen fixation rate. Under present day, the GK simulation, we see almost a quarter of decrease in the nitrogen fixation annually, but the decrease gets much smaller in this combined effect. And we try to analyze, we take this nitrogen fixation difference as an example to look at the difference here, and we compare this the value where we consider the oceanification in the future and to oceanification in present day. We see the magenta colors as where we see a positive impact of combined effect. And those areas are very similar to the area where you see a stronger, or you see the phosphorus limitation condition. And based on the acidification coefficients, you see a stronger suppression from on trichodesmin nitrogen fixation under iron limitation compared to the phosphorus limitation. So it means in the future, the phosphorus limitation gets stronger, which actually benefits trichodesmin in terms of their responses to the acidification effects. Then we quickly compared how phytoplankton may respond differently to different climate scenarios. And those were, we did 3 short scenario simulations comparing the last 10 years of these 3 scenarios, which is the SSP 1 and 3 and 5. And as you can see, under this low emission scenario, the diversity or the Shannon index almost unchanged. But this index gets, the changes in Shannon index gets stronger, especially under this high emission scenario, which means the evenness and diversity could decrease significantly under this high emission scenario when we consider acidification. But the difference here, like this plot here shows the comparison between the simulation with climate change and acidification. So this indicates the importance of considering acidification in future projections. And then also I want to quickly show the response of phytoplankton or the biological cycle to different scenarios. As you can see, the blue colors indicate the net perimeter production and also the POC flux to different scenario, emission scenarios. Without considering acidification, the response quite monotonically based on the emission level, but when we consider the acidification effects, we see a big jump in the high emission scenario. And also we see a significant decrease in the E ratio. It means the export efficiency decreased significantly, even though we see an increase in the overall net perimeter production and also the export production with acidification. That means this the shift in the community structure. So I'm going to leave my conclusion here and take questions if I still have some time.
Time for one quick question, if there is one. We can move on. Yeah. Thanks, Shannon. Okay, next up we have Riyanka Roy Chowdhury from INCAR, and she will be talking about some experiments with ocean or iron fertilization in CESM.
Hi.
This will advance the slides, this go back, and this is the laser pointer, and you pointed at this.
This is for change the slide.
No, this one, the big one, and then I'll go back in case you need to go back. And then I'll try to like signal to you when you have one.
Okay, hi. Today I am going to discuss about the regional ocean iron fertilization response to different phytoplankton types and their response to the carbon feedback as well. And this work not. So why we need carbon dioxide removal? Hence, we all know that rising atmospheric CO2 and their consequences has been well documented. They have implications on the ocean acidification and also the global circulation changes, and also the definitely have impacts on the ecosystem. So the right panel, the figure shows that the IPCC reports, if we also removed our emission, we cannot maintain the 1.5 degrees centigrade temperature, and we can, to reach the net zero emission by the year 2050, we need CDR. And there are different types of CDR approaches. For this work, we will discuss the FE fertilization. Sorry. So this is the ocean, hence we know the ocean has more capacity to take the anthropogenic CO2, nearly 25 to 30% CO2 absorbed by the ocean itself, and mainly the many CDR approaches that can also reduce the ocean acidification. There are actually two types of CDR. This is gross CDR, that is the atmospheric CO2 drawdown by the ocean, and the net CDR. Net CDR is how much carbon dioxide is out of the atmosphere. And for the net CDR, it is also important how deep and how long we are doing the carbon sequestration. And this is the experiment locations where the observation has been done previously. So this is my experiment. For this work, we have used the forced ocean sea ice model, low resolution 1 degree, and for all the regions we have added 0.02 mole square meter per year Fe to alleviate iron limitation. And the experiment has been done from the year 1990 to 2021 using GRA 55 forcing. And here the regional boundary defined by the nutrient criteria. And for the Southern Ocean south and north location, the density lines, the isopycnal line 27.1 that divide the Southern Ocean south and north location. This is the response for carbon cycle. So the left panel, it shows the carbon uptake efficiency to the fertilized region only to see the local impact. And the middle panel, same carbon uptake efficiency calculated to the global ocean. So both the cases we have seen the Southern Ocean is more efficient compared to the other regions. And compared to Southern Ocean North and South, Southern Ocean South is more efficient. And the right side panel is the carbon uptake response for YF region and the other regions. So the hatched bar is the other region, and the solid bar is the fertilized ocean. And we have seen that Southern Ocean North location, it is Southern Ocean North, it is the in region and out region, they are showing similar response, whereas the Southern Ocean South is showing almost double response in terms of carbon uptake in this result. So hence, carbon uptake efficiency is more in the Southern Ocean, South and North. So the rest of the analysis will discuss only the Southern Ocean focused. So this is the results for POC flux, NPP, and the export ratio, as well as the DIC drawdown. We have seen for the similar for the left bar is for the in region, for the fertilized cell only, and the right hatched bar is the out region. So we have seen both the cases, the export and NPP has increased, though we have seen Southern Ocean North, some out region also responds while we include iron in this location. And the right side is the DIC drawdown. We have seen for the Southern Ocean South shows more DIC drawdown, that is nearly negative 1.8 petagram per year. So this is the phytoplankton functional type contribution to total carbon fixation. So we have seen the iron fertilization experiment, the Southern Ocean North mostly dominated by coccolithophore production, whereas the Southern Ocean South shows mostly the diatom production. And both the cases we can see the small phytoplankton decreases. And this is the primary production spatial map for 3 functional type. We have seen that mostly Southern Ocean, here the left panel is Southern Ocean North and the right is Southern Ocean South. So Southern Ocean North mostly diatom dominated, and Southern Ocean North is coccolithophore. And we have seen some of the response outside of the box in the Southern Ocean cases, that maybe when we do the experiment, some of the Fe leaching can possible through advection. That is why we are getting some outside responses. So hence we have seen that diatom productivity is more in the Southern Ocean South locations. So the other parameters also shows the response, like hence diatom needs silica for their growth. So diatom silica limitation term decreases, as well as the Si2C stoichiometric ratios also changes, it reduced. Also, we have seen some amount of NO3 drawdown in the Southern Ocean South sector. So basically in the Southern Ocean South, it is biological carbon pump is dominating, and that leads to the DIC drawdown that we have seen previous picture. Here I want to show some preliminary results, how the inorganic carbonate chemistry responds. So upper panel is for the Southern Ocean North, and the lower panel is for the Southern Ocean South. Hence, we have seen in the Southern Ocean North the coccolithophore production, and for that we have seen some consumption of alkalinity. So alkalinity drops we have seen in the spatial map, and both the cases like DIC and the PCO2 is showing the reduction, but it is more, the magnitude is more higher in the Southern Ocean South response. So it may be the Southern Ocean North is not, biological pump is not only dominating, the carbonate counter pump is also reacting. That's why some of the offset of biological pump gain we can see from here. And this is the anomaly map, how the alkalinity and DIC is going from the deeper depth. We have seen most of the response in the intermediate water, and we can also see the upper panel, some negative alkalinity. That's a signature of alkalinity reduction we have seen in the Southern Ocean North panel, but that is not that prominent in the Southern Ocean South section. And both the cases we have seen like DIC DIC anomaly is increasing in the intermediate depth, but the magnitude is more higher in the case of Southern Ocean South experiment. It is -2 +20, but in Southern Ocean North it's -2 +15. And we have seen some signatures in the deeper depth as well, and DIC distribution follow the isopycnal lines and the water mass of Antarctic intermediate water and bottom water. But the bottom water things we cannot explain. Some signals are there because this run is only for 30 years. We cannot say anything about that. And these are the preliminary results. And in my future work, I want to do the same things using the couple model run and also the high-risk simulation. And I also want to include the offline feisty response due to fish response due to FE fertilization experiment to see how the fish size and different fish classes changes and how their response are different in different region. So these are the main key findings for this experiment. So basically the same experiment we are doing and same amount of iron we are added to Southern Ocean South and North sector, but their response is different because of their regional biogeochemistry. Southern Ocean South is dominated by diatom production, where biological pump is only dominating, and that leads to more CO2 uptake. Whereas Southern Ocean North, hence it is biological production as well as carbonate cycle is also plays a role. We get some of the mixed response in the Southern Ocean North. And thank you.
Thanks, Rianka. Great talk. Are there any questions for Rianka?
Aloha. Yes, I had one question. Could some of the negative consequences of iron fertilization be, briefly mentioned?
You mentioned the slide, please.
Asking about some of the negative consequences, like the nutrient rubbing.
Okay.
Oh, no, wait, no, I don't know. Sorry, we're just trying to figure out what slide to show, but I think maybe just talk about the nutrient rubbing.
Oh, okay. So we're thinking due to the production of diatoms, some amount of nutrient is required for their growth. And when like silica become limiting nutrients in this region, that also some of the nutrients, it is moving to other locations.
The reason why I ask is because this iron solution has been proposed and tested many decades ago, and a number of negative consequences were identified. So I was just curious if you're going to take those into account.
You mean like the nutrient robbing to other locations?
Exactly.
Well, those are taken account in the model. We do see some of that.
Our collaborators, the GFDL model, there also shows a similar pattern in this nitrate drawdown, but our model shows the magnitude is more, it's -10. There is 7 millimole per cubic meter.
Thank you.
Thanks, Veronica. Okay, next up we have Rui Zhen from the University of Washington, and she'll be talking about ocean alkalinity enhancement experiments. So let's do advance. Point the laser at this screen. Not that one, this one. Or it'll wake up. I think it takes a while.
Okay, but this one, oh,
That's advancing.
Oh, yeah.
Here.
but
There.
this is advancing.
That's advanced. This should work for the laser pointer. I don't know if it will.
I don't know. But,
There it goes.
oh, okay. It works. It works. Okay. Okay, let me time myself. Good afternoon, everyone. My name is Rui. I'm a postdoc at CECOS from the University of Washington. Today, I will be talking about biogeochemical feedbacks in ocean alkalinity enhancement and how we investigate them using two global ocean biogeochemical model configurations, MOM6 Marble and MOM6 Cobalt. This work is a collaborative effort involving colleagues at NOAA, NCAR, and several industry partners. This figure shows the basic idea behind ocean alkalinity enhancement, or OAE. The concept here is relatively straightforward. By adding alkalinity into seawater, typically through dissolved alkaline minerals, we kind of shift the ocean's carbonate chemistry. As alkalinity increases, seawater can take up more carbon dioxide from the atmosphere. That carbon dioxide is then converted into bicarbonate and carbonate ions, which are more stable forms of dissolved inorganic carbon and can remain in the ocean for long periods of time. In principle, this leads to additional atmospheric carbon dioxide removal. However, the real ocean is much more complex than that. The effectiveness of OAE depends on physical processes such as mixing and LC gas exchange, as well as chemical processes like mineral dissolution. Biological responses can also play an important role here. For example, changes in calcification can alter how much carbon is ultimately stored in the ocean. Understanding these biogeochemical feedbacks is critical for evaluating the long-term carbon removal potential of OAE, and that's our focus of this study. So, one of the big uncertainties we are dealing with is when we try to evaluate OAE effectiveness, how do calcifying organisms actually respond to higher alkalinity? When we add alkalinity to seawater, we are changing the saturation state, the omega for aragonite and calcite. And the system becomes less sensitive to small changes in carbonate chemistry. Now, calcifying plankton can respond to this in a few different ways. They can ramp up or slow down their calcification rates. They might shift their calcium carbonate to organic carbon production ratios. Or they could change how much particulate carbon gets exported and remineralized at depths. And here's why this matters. All of these pathways feed directly into alkalinity regeneration and carbon storage, so they can either boost or undercut the long-term additionality of MCDR. And what makes this even trickier is that different models represent these ecological processes differently. So biological feedbacks aren't just noise in the system. They can actually become first-order controls on how much additional carbon that OAE can sequester. And here's another tricky thing we have to deal with. Calcifiers could actually become carbon limited on the heavy OAE perturbation. That's actually something we are seeing in our preliminary MOM6 marble runs. There's a decrease in coccoluciferous of the vesicles of friends, and I'll show you that result later. That job is tied to the carbon limitation effect from OAE. That's what we think it could be. And this could potentially affect other plankton too, but coccoluciferous are right now what we have in the model. So to evaluate how calcification feedbacks influence OAE additionality at scale, we needed to design some realistic alkalinity enhancement scenarios, not just idealized experiments. And we didn't do this in a vacuum. We have worked closely with our industry partners. We held a scenario workshop that generated a lot of valuable input, and we have also collected survey responses from them. All of that feedback kind of give us the numbers you see here. What's important is that these scenarios are grounded in real-world constraints, logistical limitations, regulatory considerations, and also geopolitical feasibility. So they reflect what large-scale OAE deployments might actually look like in practice. Now, after some initial trials, we have narrowed down our focus to this particular deployment case. The target here is 5 gigatons of carbon dioxide removal per year, which translates to about 2.066 teramoles of alkalinity added annually at each site. And in both scenarios, alkalinity is distributed across 100 global sites. These sites were selected based on oceanographic suitability, but also real-world deployment constraints, so things like infrastructure, regulations, and accessibility. I don't know if you have noticed that background image on the previous slide. That's actually one of our industrial partner sites near Perth, Australia, and you can also see it here on the map. It doesn't work. Oh, sorry. Around here, if I remember it correctly. For the modeling side, we take the total alkalinity additions and convert them into site-specific fluxes, which are then implemented as river-type forcing. These fluxes get ramped up over a 20-year period starting in 1958. The higher alkalinity fluxes you see in the boxes here, those correspond to the specific model grid cells where the forcing is applied. Oh, and one more technical note. We are using an ocean sea ice simulations for SPY-GIA reanalysis. And for this study, we are using the MOM6 ocean model coupled with 2 different biogeochemical frameworks, cobalt and marble. Now, these 2 models actually share a lot of strengths in common. Both are well-validated global biogeochemical models. Both have multi-size plankton food webs, flexible ecosystem dynamics, and very variable, like the changing stoichiometry, which makes them particularly well-suited for what we are trying to do here. But they also differ in some important ways. Cobalt, this is a framework used in GFDL's ESM4, doesn't have explicit calcifiers. Instead, they are embedded within existing functional groups. Calcification in cobalt depends on some carbonate saturation state, and it uses explicit detritus export with oxygen and temperature-dependent remineralization. Marble, on the other hand, developed at NCAR for CESM3, actually includes an explicit coccoluciferous functional type. And in marble, calcification responds directly to water carbon dioxide, not saturation state. It also handles export and remineralization differently. using length scale formulations. So the reason why we are running both, we kind of want to use these two frameworks to bracket the ecosystem uncertainty in OAE additionality to see how much the biological representation matters for our studies. So here's our experimental design. We have set up 4 cases as our tier 1 simulations. First, the control. No MCDR intervention, standard calcification formulation. This gives us our baseline for carbon and alkalinity cycling. Basically, what the ocean does on its own. Second, alkalinity addition. Here, I apply the riverine total alkalinity perturbation we talked about earlier, but and this is the key here. Calcification behavior stays unchanged, so this run isolates the direct carbon chemistry and its response to OAE without any biological complications. And the third one, calcification sensitivity case. In this case, I alter the calcification saturation state relationship, but I don't add any alkalinity. The goal here is to see how uncertainties in biological calcification alone can shift the background carbon system, even without OAE. And fourth, the last one, we combine the two, altered calcification plus alkalinity addition. This is where it gets really interesting here, because now we can evaluate the interaction of effects. Do biological feedbacks amplify the carbon removal, or do they undercut it? One important caveat here, all of these simulations are ocean sea ice only, whether it's MOM6 marble or MOM6 cobalt, so there's no atmospheric feedback loop here. The atmosphere doesn't respond to what the ocean is doing. And one more note, in our first round of simulations, I'm using an enhanced calcification case where more calcium carbonate is produced for the same omega value. So we are starting by exploring the upper end of the calcification response. Okay, let's look at some preliminary results from ESM3 MOM6 marble. These figures show the difference between the alkalinity addition run and the control run. You can clearly see the added alkalinity spreading from the coast and increasing alkalinity concentrations along the coastal regions. We picked 2 coastal regions to show. And one feature that makes marble unique is its explicit representation of coccolithophores, which allows us to directly study how OAE affects coccolithophore bromes. In the figure on the right, we are looking at the North Atlantic, specifically the change in coccolithophore net primary production between our OAE run and control run. You can see that in areas where the added alkalinity has spread, there's a mix of responses. The warm colors, the red color, show increased productivity, but notice the blue patches. Those represent areas where productivity actually decreased. We think this is likely due to carbon limitation, where the shift in carbonate chemistry actually reduced the carbon dioxide value, like for the photosynthesis processes. And here we show the global distribution of the difference in carbon dioxide uptake between our OAE simulation and the control run at the end of year 3. As expected, OAE enhances carbon uptake in and around the deployment regions, demonstrating positive CDR additionality. We see a similar response in cobalt, which I'll show you in the next section for cobalt. Now, you may notice that although we see an overall increase in ALC carbon dioxide uptake, there are some patches showing a slight decrease. These tend to be areas where you normally expect a lot of gas exchange into the ocean. In my global figure for cobalt, I used an annually averaged values to plot this, so we don't see this pattern as clearly, but it does show up in monthly snapshots for marble. One hypothesis is that this could be related to balancing effects, but we are not sure. It's something we want to dig into more into for our future work. And this figure shows the first 5 years of the simulations for ocean carbon uptake, carbon export, calcium production in the upper 100 meters, and NPP. One thing to keep in mind is that there's still some model drift during this period, so we may focus more on the later years in future analysis. The most obvious signal is in the upper left panel, where ocean carbon uptake increases after alkalinity is added. The changes in carbon export, calcite production, and NPP are much more subtle, and it might be difficult for you to see at this scale, but they are present and distinguishable from the control run, I promise. And here, I have repeated the analysis using cobalt outputs from my end. We see the same issue with model drifting, but the overall patterns are similar to those from marble. OAE clearly increases ocean carbon uptake, and in cobalt, it's even more apparent that calcium carbonate production also increases. Carbon export ranges are similar in both models, for marble and for cobalt, but the ranges for others display some differences. And this figure provides a more detailed look at the 5-year cobalt simulations. The upper left panel shows ocean carbon uptake, which is the same quantity I just showed earlier. The upper right panel shows the difference in global carbon dioxide flux between the OAE and control runs. The bottom panels focus on the cumulative response. On the left, you can see the divergence in cumulative ocean carbon dioxide uptake over time, and on the right, the cumulative carbon uptake attributable to OAE. The gap between the two simulations grows steadily throughout our experiment. By end of 1962, the OAE case had accumulated nearly 2 PGC of additional carbon uptake compared to our control simulation. Okay. So next, I'd like to show some results from our calcification sensitivity experiments. In the upper row, you can see the global distribution of carbon uptake for the control run, the OAE run, and the difference between them, all under baseline calcification conditions. The bottom row shows the same set of plots, but for the high calcification scenario. This allows us to compare how a stronger calcification response influences the carbon uptake signal associated with OAE. If you look at the last column, the difference plots, you will notice something important. The top figure shows only increased uptake as we'd expect from OAE, but in the bottom figure, we start to see some areas of decreased uptake. This suggests that enhanced calcification partially offsets the benefits of alkalinity addition. And here I place the two different figures side by side and created a third panel showing the difference between these two different plots. This last panel shows that higher calcification decreases the efficiency of OAE. I'm putting this into numbers at the end of year 1. This is the cumulative carbon dioxide uptake difference for these two comparisons. Key takeaway is our high calcification case can reduce OAE-driven carbon dioxide uptake by about 50.6%. This work is still ongoing, but here are some of my implications and next steps. Multimodal comparisons are essential. We have to do this. And MLRV frameworks should account for biological feedbacks. We should know the importance of site selection because regions with weak calcification response could offer more robust additionality. And next steps, we have a lot to do. So with that, I'd like to take any questions at any time.
We are just about out of time. That was the 18 minutes. So if you have any questions for Rui, just follow up with her during the break. Does that work?
Sure.
Okay, next up we have Courtney Payne from the University of Colorado, and she's going to be talking about marine cloud brightening experiments in the Arctic.
Much for your attention, and thanks as well to my co-authors on this project, without whom this work really would not have been possible. Also apologies if you've already heard large parts of this earlier. So increasingly with climate change, we're considering certain climate interventions, such as these, different strategies for modifying solar radiation. So these kind of climate interventions largely involve altering the reflection of shortwave radiation or the transmission of long-wave radiation, and thus fundamentally changing the kind of energy in the Earth system. And one branch of these is changing the reflectivity of marine clouds, marine cloud brightening. And when we typically think about implementing something like this, it involves taking a tremendous number of boats and moving them around the world's oceans, using them to spray sea salt aerosols into the lower parts of the atmosphere. And then those sea salt aerosols would change the brightness of the clouds and enhance the amount of reflection, the amount of sunlight that's reflected out of the Earth system. In this project, we want to investigate whether marine cloud brightening could be used to change the amount of sea ice that's retained in the Arctic. And we also want to understand the downstream consequences of that. If we do enhance sea ice area in the Arctic, how might that impact things like the marine ecosystem? So this set of experiments relies on CESM2 simulations that are under a moderate warming scenario. And the couple modifications to CESM include parameterizations that improve the representation of Arctic sea ice and that involve a more complex marine ecosystem, although there unfortunately are no sea ice algae. And these simulations also were used to run an offline fish model called Feisty. Feisty is a fish model that takes inputs of certain mesozooplankton characteristics, POC flux to the sediments and temperature, and uses those inputs to calculate changes in the biomass of 3 different fish functional types: forage fish, large pelagic fish, which in the Arctic can kind of be thought of as the marine mammals at the top of the food web, and then demersal fish like cod. And demersal fish also feed off of benthic invertebrates, which is kind of used as one of the internal things that Feisty is calculating. So this experimental setup, we used 5 different baseline simulations, and we evaluate those between 1920 and 2070. And then we also ran 6 different marine cloud brightening perturbations for 2035 to 2070 that differ in strategy and magnitude. So we use 2 different cloud seeding strategies. The first is kind of a brute force strategy where we seed clouds in every grid cell north of 67 degrees north all summer long, so May through September. The second is more implementable in the Earth system. We would still only seed clouds north of 67 degrees north, but we exclude land and also places where the sea ice is pretty consolidated. So this involves changing the mask that we seed these clouds in at each time step. And with these different experiments, we increase the summertime cloud droplet number from about 50 across the Arctic to 100, 200, or 400 So a pretty large scale impacts. Okay, so the first question is, how does this influence sea ice area? That's the goal of this project. So hopefully, I guess, these simulations should have some big impacts on sea ice area. So I've plotted here from those baseline simulations the change in annual sea ice area from 2000 to 2070. And we can see that over this period where climate change is acting, we can see a big decline in sea ice area. With these different perturbations, you'll see that under almost all perturbations, sea ice area increases outside of the kind of envelope of the baseline simulations as well. So we've succeeded, questioned over, let's move on. With this project, we wanted to investigate a little bit more the downstream consequences of something like this on the Earth system. So my colleague, David Clement-Sewell, wanted to first understand how these simulations, these perturbations might be affecting the annual cycle of different snow and sea ice characteristics in the Northern Hemisphere. So he's plotted here Northern Hemisphere ice area, ice volume, and snow volume, and done it, the seasonal cycle of these characteristics between 1920 in the light green and 2040s in the darker green colors. And you'll see that there's a really strong seasonal cycle to all these characteristics in the Arctic. You can also see that there's a big change over time with climate change. And yeah, consequently big reductions in these characteristics over the time series. When we look at some of these lower magnitude perturbations, you can see that they tend to return the ice state to historical-ish conditions, things that were expected in the early parts of the 20th century. However, you can notice that with some of the higher magnitude perturbations, the 200 and 400 summer perturbations, they typically shift the snow and ice state into conditions that are unprecedented in recent history. So, for example, for this, you can see in this, in July and August that snow concentration should be pretty close to zero, but in 200 and 400 summer perturbations, there's actually the formation of this perennial snowpack on top of the sea ice. And perhaps not surprisingly, that has some pretty big implications for light in the surface of the ocean. So here I've plotted that July snow depth against July shortwave radiation, and you can see that as snow depth has diminished over the kind of historic period, represented by these smears in light green to dark green as we go forward in time, there's been an increase in shortwave radiation. However, a lot of these perturbations in the 2040s kind of pop us outside of that historic envelope. We see that individual years of all of the summer perturbations, as well as some of the more extensive dynamic mask perturbations, kind of put us in this new climate state where we have substantially more light, or less light in the surface ocean. So I'll focus in on these 200 summer perturbations for this next slide. And I wanted to look at how they compared to the baseline simulations. And as you can see here, Arctic phytoplankton NPP is reduced by a pretty large amount. It's about 26% lower across the Arctic as a whole, and that in turn drives what we found from these offline feisty runs, a 31% decline in total fish biomass. And as you can see in the central Arctic, these changes are not spatially heterogeneous or homogeneous. They are really focused in on the central Arctic, where there's declines of more than 50% in both of these, in both phytoplankton productivity and fish biomass. So I wanted to understand a little bit more of the consequences of these big perturbations on fish biomass, and do it in a way that was kind of relevant to potential fishery managers who might be overseeing the Arctic under these perturbations. And one of the most kind of fishery relevant ways of, sorry, I think I'm not seeing any advancement of the slides right now. Like out of battery or something? Oh, that's advanced a lot. I'm sorry. Okay. Yeah, one of the ways that fisheries are typically managed is by understanding changes within large marine ecosystems. So there are 66 large marine ecosystems globally, but about 20 in the Arctic and in subarctic seas. And as you can see from this plot where I've shown fish biomass as calculated by Feisty averaged for each of these large marine ecosystems, generally there's higher fish biomass in the subarctic, more modest fish biomass in the shelves, and then lower biomass in the central Arctic. Another way that we can kind of think about changes within these large marine ecosystems is, or that we might want to think about them as changes to within the fish functional types that matter the most in each region. So in the central Arctic, forage fish tend to dominate. In the kind of eastern Arctic shelves, as well as in some shallow subarctic seas, demersal fish, which feed again in the benthos, tend to dominate. And then in these kind of western Arctic shelves and in many subarctic Pacific seas, we see that a mixture of forage and large pelagic fish dominate. We also see that in these really subarctic shallow coastal LMEs that fish populations are pretty mixed, so all three groups matter. So in order to understand how these changes were affecting different LMEs differently, I first started off by normalizing fish biomass in each year and for each perturbation to the 1920 to 1970 mean, which I've shown with the black line here. And then I wanted to identify which perturbations resulted in conditions outside the historic state, which I think of as being plus or minus 2 standard deviations, and that's represented by the black dashed lines. And also which perturbations result in conditions outside of the contemporaneous state. So in some of these large marine ecosystems, fish biomass has changed really substantially as a consequence of climate change over the 1920 to 2070 period. And so I wanted to see where these perturbations put us relative to both the historic and the contemporaneous periods. So I then grouped large marine ecosystems into a couple different categories based on their responses to these. So first we'll look at the central Arctic large marine ecosystems. So these have very low fish biomass and very low current fish catch, only 100 tons, which is, you'll see, orders of magnitude below other LMEs that I'll present today. These are also places where forage fish tend to dominate. And as we can see from this kind of contemporaneous line, it's also a place where there have been huge changes in fish biomass over the early parts of the 21st century. So there's 50% more fish living here by the 2040s than there was in the 1920s. And we see that with all these perturbations, you can see that there's a really rapid kind of change in fish biomass as a consequence of these perturbations, and that for forage fish biomass, which I've plotted here, we get biomass that's really outside of both the historic and contemporaneous states for most of these perturbations. And I should just note that while the current fish catch is really low, this is a pretty, parts of this are relatively important to certain indigenous communities. So it's not without consequences that there would be some big changes in these places. So the Western Arctic has low fish biomass, but modest current fish catch, about 600,000 tons of fish are caught here each year. And forage fish and large pelagic fish tend to dominate. And when we look at these perturbations and their impact on fish biomass, we see that only the strongest perturbations push pelagic fish biomass out of the historic and contemporaneous states. So this is a slightly more modest effect. In the Eastern Arctic, there's modest fish biomass in Feisty and pretty high current fish catch, about 1 million tons of fish are caught here per year. And demersal fish tend to dominate on these shelves. And in these large marine ecosystems, only the strongest perturbations result in demersal fish biomass that's outside of the contemporaneous state. But you'll see that for the most part, it remains within that historic kind of envelope. So it really is kind of pushing these large marine ecosystems back to their historic fish biomass levels. And then for the subarctic LMEs, these areas have very high fish biomass, very high current fish catch. Over 12 million tons of fish are caught here per year. They represent some of the most important fisheries in the world. They are typically dominated by forage and large pelagic fish or mixed fish communities. And fortunately, these perturbations do not have significant changes, result in significant changes relative to either the historic or contemporaneous total fish biomass. So I think overall this work demonstrates to us that Arctic marine cloud brightening can result in increased sea ice area, but that these higher magnitude perturbations can generate sea ice and snow states that are unprecedented in the 20th century. We also show that increased summer snow reduces light in the surface ocean that drive these large declines in Arctic phytoplankton, and that can result in fish biomass that's much lower than has been observed in the 20th and 21st centuries in some large marine ecosystems in the Arctic, but that large marine ecosystems with the greatest current fish catch show minimal response to perturbations. Thank you so much for your attention. I take any questions.
Thank you, Courtney. Do we have any questions? All right, thanks, Courtney. So next up, we have Priyanka Banjari, I think from Dartmouth College, and she'll be talking about the potential of spraying clay minerals on the surface ocean for removing CO2 from the atmosphere.
Good afternoon. I'll today discuss another approach towards marine-based carbon dioxide removal strategy, that is via spraying clay on the surface of the ocean. Specifically, since clay is an important component of mineral dust and has comparatively higher levels of soluble iron, we have carried out dust fertilization experiment using CESM model, whereby we seek to combine the effect of iron fertilization as well as ballasting effect of dust to understand how it impacts the ocean biological carbon pump. Also, in the second half of the talk, I will introduce a new heterotrophic bacteria component that we have implemented in CSM model with an aim to improve the carbon and nutrient cycling in the model. Why dust? Now, although several artificial iron fertilization experiments have detected an increase in surface productivity following iron fertilization, only one experiment conducted in the Southern Ocean have detected increase in deep ocean organic carbon fluxes. In contrast, sediment traps have consistently detected multiple cases of increase in deep ocean organic carbon fluxes following natural iron fertilization by dust events as well as from other lithogenic sources. There are several ways in which dust can lead to increased carbon sequestration. One of the most important ways is by supplying essential nutrients like iron and phosphate, which leads to increase in primary productivity and organic carbon fixation, its subsequent flux to deeper ocean. Depending on the phytoplankton species composition, we get various biominerals associated with organic carbon fluxes, such as opal and calcium carbonate, and this can play an important role in shielding the organic carbon from remineralization losses. Another direct pathway is via dust incorporation into organic aggregates, which make these organic aggregates heavier and make them sink faster. A third pathway is through dust fueling bacterial production, which leads to generation of TEP, that is transparent exopolymer particles. These are just sticky gel-like substances which helps to clump together organic matters and minerals and make them more dense and helps to sink organic matter faster. We have carried out few series of experiments at Dartmouth College to understand how dust and bacterial activity can impact carbon fluxes, whereby we have added various levels of clay to seawater and have looked at the response. So you can see that following clay addition, there's an increase in generation of TEP, shown by the vertical columns marked T1, T2, to T5, T6. And this is mainly through bacteria-mediated pathway. We also find that through this pathway, once zooplankton starts feasting on a diet of algae combined with various levels of clay, we see increase in settling velocity of zooplankton fecal pellets in the ocean. This is a recording of sinking of zooplankton fecal pellets following clay addition. And what we see is that the sinking velocity of zooplankton fecal pellets is not dependent on the diameter of the pellet size, but rather on the quantity of clay that is added to the water, and it makes the fecal pellets heavier and helps them to sink faster. Now, to understand what is the large-scale implication of this type of pathway, we have carried out a series of dust fertilization experiments using CESM2, whereby we have added iron-bearing fine dust across several sites in the global oceans. These sites are shown by the black rectangles. And these encompass the California current system, the upwelling region of the California current system, northeastern, northwestern Pacific, and northeastern, northwestern Atlantic. The red boxes show the regions where we plan to carry out some of these experiments in future. We have spun up the model for 305 years and carried out 3 ensemble runs, which we have branched off from year 286 to 87 and 88. We have injected dust for only the first year of the branch simulation and have followed the response for 36 months. And this time corresponds to the spring bloom time. Basically, our aim is to understand if we are to carry out short-term experiments in regions that are accessible from land, what can we expect to see? And these regions might not give us the most perfect, best results, but still we want to understand how these regions will respond to short-term experiments. Here you can see that this dust spraying experiments have been carried out across a wide range of biogeochemical regimes. The top panel compare CSM parameters with various observations. The colored circles indicate mixed layer depth from CSM, and the vertical panels to the left indicate nitrate concentration, and to the right indicate chlorophyll concentration. In general, what we see is that CSM is overestimating the depth of the mixed layer. It underestimates nitrate concentration at surface and overestimates chlorophyll. Specifically, CSM is underestimating nitrate concentration over northern Pacific, and previous studies have attributed this to slow ventilation over the northern Pacific, leading to deep water nutrient trapping. The bottom panel shows the responses to dust addition. The green columns are the peak chlorophyll response following dust addition, and we see maximum response over the northern Pacific region. Notice that although in CSM, both Atlantic Ocean and northern Pacific Ocean have more or less similar levels of nitrate, we see much higher level of response over northern Pacific compared to Atlantic Ocean. This is because North Pacific also has higher levels of silicate phosphate and lower levels of iron compared to Atlantic, which triggers much higher level of chlorophyll response. The least response is seen over Northern California upwelling system, which has the lowest level of nitrates. Along with this peak chlorophyll response, we see increase in ocean CO2 uptake, shown by the colored circles, and also increase in particulate organic carbon flux at 120 meters. Here we can see how nitrate depletion evolves following dust addition over various patches, and I'm showing the result for Northeast Pacific, where we see maximum response. And the result is encouraging in a way that we do not see surface nitrate depletion spreading over much larger regions through advection. But it also remains to be seen if we carry out this type of experiments over longer time, or we have multiple pulses of dust addition, how this type of patches will evolve. Okay. Now that we have seen that dust addition leads to significant increases in surface productivity, we would like to understand whether this translates to deep ocean organic carbon flux. To this end, we have calculated transfer efficiency, which in simple terms refer to fraction of POC flux at 150 meter that reaches 1500 meter depth. Basically, greater the transfer efficiency, more carbon is reaching deeper depth and is escaping remineralization losses. In this panel, you can see the black curves indicate response of transfer efficiency following dust addition, and these have been standardized by dividing by the standard deviation. So based on various regions, we see a wide range of response of transfer efficiency, and to understand what drives this response, we have carried out a multiple linear regression where we have predicted transfer efficiency using the flux of particulate organic carbon, silicate calcium carbonate dust, and also change in oxygen concentration at mid-depth. Overall, the key results that emerge are, first, transfer efficiency reduces following dust addition due to increase in particulate organic carbon flux along with increase in opal flux due to diatom blooms. This is because as we have higher productivity, especially associated with diatom blooms, we have higher rates of respiration and remineralization, which leads to reduced transfer efficiency. This tendency is opposed by fluxes of calcium carbonate and dust, which tends to increase transfer efficiency. In general, over the Pacific Ocean, where we have higher levels of diatom response, transfer efficiency is controlled much more by opal flux, whereas over the northern Atlantic, where we have much more calcium carbonate response, transfer efficiency is controlled by calcium carbonate fluxes. Okay. In this slide, the blue curve shows cumulative particulate organic carbon flux over time, and the red curves show cumulative air-to-sea CO2 uptake over time. Now, notice the gap between these two curves. This gap implies that a surface level dissolved inorganic carbon deficit that is left because of phytoplankton bloom is not being replenished by drawdown of atmospheric carbon dioxide, but rather it is being replenished by ocean circulation. That is, this refers to internal reorganization of dissolved inorganic carbon within the ocean due to circulation, which tends to fill this gap in inorganic carbon at surface level. If you focus on the most panel, lower right panel, this curves show ratio of cumulative CO2 uptake by cumulative POC flux. And we can see that this ratio stabilizes after about 8 to 10 months. What these ratios indicates are the regions where we have carbon dioxide drawdown from the atmosphere versus carbon dioxide versus DIC deficit in the surface being replenished by ocean circulation. And we see that depending on various sites, carbon dioxide, the inorganic carbon deficit in the surface ocean can be replenished by ocean circulation, and this percentage can vary between 20 to 60%. For example, over Northeast Atlantic, the pink curve, which has the lowest efficiency, we see that in this region, the southward flowing Greenland current brings high levels of dissolved inorganic carbon, and this leads to DIC deficit being replenished from the ocean rather than from atmosphere. Now that we've seen there are some effects of dust on ocean carbon uptake, we would like to get an initial understanding of how durable is this uptake. So to this end, we have calculated net particulate organic carbon remineralization and have assessed how durable it is by calculating unventilated fraction of water. We have calculated unventilated fraction of water by considering IH, that is the ideal age of water. In simple term, this refers to the time since a water parcel was last in touch with the surface. And so ventilated fraction of water refers to more recent water, whereas unventilated fraction refers to much more older water. What we find is that over the northern Pacific, particulate organic carbon remineralization takes place to a large fraction over water that is unventilated and old water. And so the chance of this carbon to escape from this old water at deeper depth reduces. In contrast, over the Atlantic Ocean, we see that overall the change in particulate organic carbon remineralization compared with respect to dust spraying is less, and much of it is at shallower depths with more recently ventilated water, indicating it has a propensity of outgassing out from the atmosphere, outgassing out to the atmosphere. Okay. With this, I'll come to the second part of my talk, where we have been working on implementing heterotrophic bacteria in CSM model. Bacteria is an important component of the ocean which controls particulate organic carbon fluxes, and it dominates the ocean in terms of diversity, abundance, and in terms of processing primary productivity. It can process up to 50% of primary productivity. To this end, we have implemented a single class of bacteria within CSM, which combines the activities of both free-living and particle-associated bacteria. We have tracked carbon, iron, nitrogen, and phosphorus within the biomass. Bacteria growth takes place by uptake of dissolved substrates, and bacteria intercepts particle flux. Now, since CSM does not explicitly account for particulate organic carbon concentration, we have calculated a dimensionless particulate matter interception flux, which is, in simple terms, proportional to the bacterial biomass. Bacteria loss takes place through grazing, mortality, respiration, and by assimilation into zooplankton. I'll show some initial results from this bacteria incorporation. The shading here shows bacteria carbon concentration over the surface ocean, and the colored circles are the various observations. We see that in general, our bacteria implementation is able to reproduce the overall distribution of bacteria in the global ocean. For example, we see higher values over equatorial Pacific, northern Atlantic, and the subtropical front. But our implementation does miss some of the highest values of bacteria carbon concentration. If we consider bacteria carbon below 20 microgram per liter, which constitutes about 80% of observations, about 1,000 data points, we see a correlation between our bacteria and observation is about 0.45, which is highly significant. So this gives us some confidence in our ability to implement bacteria and its large-scale distribution. Here, I'm showing bacteria dissolved organic carbon uptake at the surface ocean. And you can see that it shows a broad range of distribution over where bacteria is taking up organic carbon over large areas. Basically, this represents a combination of two factors. One, bacteria DOC uptake is high over high productive region. And second, it is also high over regions of oligotrophic regions, which have highly stratified water where DOC can accumulate over longer term period. So we see a broader region over which bacteria can take up DOC. In contrast, bacteria POC interception is only limited to highly productive regions of the world ocean, that is the northern mid-latitudes and the equatorial upwelling regions. Finally, we would like to understand how this implementation of heterotrophic bacteria is impacting surface nutrient concentration. For this, we have looked at the biases of silicate, phosphate, and nitrate at surface level. The left panel shows a result from a long duration coupled simulation for the present day. And the other two panels show results of bacteria, results from biases from control run without bacteria and a simulation where we include bacteria. Now, first, without bacteria, we do see some correspondence between the biases seen by our simulations and simulations of a long duration coupled run carried out by Long et al. For example, we see similarity in the pattern of biases over Northern Pacific, Northern Atlantic, and Southern Ocean. Once we incorporate bacteria, we see a marked reduction in the biases of all these nutrients. Now, also it is important to recognize that some of these biases that were seen before comes from circulation, for example, specifically over the Southern Ocean, where sluggish circulation has been associated with nutrient trapping and underestimation of the nutrients, which is not reproduced by our short-scale simulations. But overall, we see that bacteria balance between nutrient uptake and recycling does lead to some improvement. In summary, we see that dust fertilization shows the strongest response over the Northern Pacific, where it is also more durable. Also, although this leads to a reduction in the transfer efficiency over this region, we have implemented free living and particle-associated bacteria and CSM. Overall, it's able to capture the broader pattern, and we do see a significant reduction in nutrient biases. We have a long way to go to understand how to carry out parameter tuning to get further improvements to this result. Thank you.
So much, Priyanka. I'm really curious to hear more about your bacteria implementation. Does anybody have any quick questions before the break? Okay, maybe we'll just go to break. You can ask any questions to Priyanka then. Thank you. Be back in half hour. Yeah, half hour. Let's thank all our speakers. Yeah. Okay, welcome back to the second half of the BGC Working Group session. So first up, we have Christopher Wren from the University of Hawaii speaking virtually. Go ahead, Christopher.
Aloha, my name is Christopher Wren, and I would like to thank all of the previous presenters. I'm going to share with you a proposed diatom research project that I recently came up with using CESM model. Adaptation and response of diatoms in the Labrador Seas, late 20th versus early 21st centuries. Because of the integrated nature of the physical and biological processes in biogeochemistry, I will discuss some physical and biological aspects relevant to this project. Outline. I will give an overview, discuss motivations, why diatoms, why the Labrador Sea, challenges, goals, diatom adaptation.
Christopher, we're hearing an echo in the room.
Plan of action B.
Sorry, we're hearing an echo.
This study seeks to assess the response of the keystone algal group of diatoms and other phytoplankton.
Can you hear me?
In the Labrador Sea, rising ocean temperatures. It will examine how diatom populations. Excuse me, I'm going to turn my volume off. I'm getting a pretty serious feedback here. Okay. It will examine how diatom populations in the Labrador Sea have changed between the late 20th and early 21st centuries in response to rising ocean temperatures by comparing cool and warm periods. The main idea is to determine as far as possible whether degradation or adaptations to rising sea surface temperatures best characterizes the changes in the community composition of these high latitude coastal ecosystems. It seeks to do this by comparing simulated ecosystem responses using CESM2 Marble and satellite ocean color data for two subsets of two ocean phases, a cool 1979 to 1984 and a warm 1999 to 2004 phase of the Labrador Sea during each year's respective spring blooms. The goal is to assess the ability of the model to satisfactorily simulate spring blooms and compare with ocean color satellite data to get a sense of how this high latitude phytoplankton community composition has changed as the ocean temperature has risen. This project seeks to improve our understanding and ability to predict changes in phytoplankton community composition and coastal ocean ecosystems under climate forcing. Motivations. As one of the world's few sites of deepwater formation, the Labrador Sea and its associated subpolar gyre contribute to maintaining the present-day global climate epoch known as the Holocene. A key motivation for investigating climate-induced changes in the phytoplankton community composition between the late 20th and early 21st centuries is the availability of sufficient ocean color satellite data extending back to the early 1980s. Biogeochemistry and marine ecosystem simulations offer an additional constraint in addition to the physically constrained atmospheric and oceanic dynamics of CESM2. Running Marble hindcasts of POP2 or MOM6 will allow for the model performance to be assessed by comparing simulated output with ocean color satellite data. In the figure on the right-hand side, a deep convective region that forms Labrador seawater in the Labrador Sea is located between Greenland and Labrador and demarcated by thick black contour lines. Within the triangular region, within two blue lines, is the location of the Labrador Sea. The strength and size of the deep water formation varies annually as shown. Why diatoms? Diatoms are single-celled microalgae that live inside ornate silicaceous glass houses or frustules. They're a foundational keystone algal group that sustains highly productive subarctic and Antarctic marine food webs. Diatoms account for about 40% of marine and 20% of the global primary production. Spring blooms of diatoms are major contributors to global carbon export and are critical to the drawdown of carbon from the surface to the deep ocean via the biological carbon pump. Because of their high nutritional value, diatoms in the Labrador Sea can sustain up to 5 subarctic trophic levels. Diatoms feed calanoid copepods, which in turn are eaten by foraging fish, eaten by Atlantic cod, which in turn provide food for various seabirds and mammals, such as harp seals, polar bears, and humpback whales. In the upper figure on the right-hand side, an often dominant species of diatom is shown in its colonial form. In the lower figure, Modus chlorophyll satellite color ocean data is shown. Some way off the West Greenland coast, you can see one day of the spring bloom from May 1st, 2013 in red. Why the Labrador Sea? The formation of Labrador seawater plays a significant role in deep water formation and ocean ventilation and makes up about 36% of the upper North Atlantic deep water. The Labrador Sea's ability to maintain 5 trophic levels is a result of the mixing of cold, nutrient-rich Labrador current water with warmer North American current water, making it one of the world's most productive marine ecosystems. The complex interaction of currents within the central subpolar gyre is challenging to accurately simulate because of the need to resolve mesoscale eddies and submesoscale currents. On the upper right, outlining the subpolar gyre, are shown the various currents that converge in the Labrador Sea. The East Greenland current travels around Cape Farewell on the southern tip of Greenland and becomes the West Greenland current, part of which turns and heads south and is known as the Labrador current. Farther from the Greenland coast can be seen the Erminger current, which forms from part of the North Atlantic current. The lower figure depicts convective simulations of the deep water forming region in the Labrador Sea. As the resolution increases, the area of the convective patch decreases. In the submesoscale 1.7 kilometer and 1 kilometer simulations, the convective volume decreases by approximately 50%. These submesoscale simulations identify and improve upon a known bias, a too-deep mixed layer. Ocean depth profile. This figure reveals the depth of the Labrador Sea, which is over 3,000 meters deep, with a very computationally extensive spin-up to equilibrate. Challenges. 1. The spin-up problem. Long simulation times are required to bring the deep ocean biogeochemical tracers into dynamic equilibrium. There are 2 possible solutions: the matrix-free Newton-Krylov method, which can reduce spin-up time by 2 orders of magnitude, and the Anderson or sequence acceleration, which can reduce spin-up by about 1 order of magnitude. The slope of the blue line on the left-hand side is steeper than the slope of the red line on the right-hand side, showing the potential advantage of using the Newton-Krylov method. Challenges. 2. Simulated mixed layer depth in the Labrador Sea is too deep. In the enlarged summertime bias shown on the right, CSM2 simulates a too deep mixed layer in the Labrador Sea of about 100 meters. However, the mixed layer depth in the Labrador Sea is spatially and temporally highly variable seasonally, interannually, and decadally. In the central Labrador Sea, the mixed layer depth can vary from a minimum of 10 to 50 meters to a maximum of 1,500 to over 2,000 meters, and boundary currents along the coast are more heavily stratified due to the influence of submesoscale eddies and Erminger rings. There are 2 physical processes that can negatively affect simulations of the mixed layer depth: atmospheric heat flux biases and lack of submesoscale processes. Goals. From straightforward to challenging. To compare cool and warm period satellite ocean color data. To compare simulated changes in the phytoplankton community composition between a cool and a warm period using pre-equilibrated marble forced with JRA 55 and CESM FOCSI to avoid the spin-up problem. To compare model output with integrated and quality-controlled ocean color satellite data to assess performance of CESM2 marble. Finally, by combining offline coupling of CESM2 marble with next-generation sequencing, insights into the adaptation of the diatom community under climate forcing may be obtained. Climate change-induced shifts in the phytoplankton community composition, dominated not by diatoms but by flagellates, such as Phyocystis pauschetti, means that the marine food web in the Labrador Sea could shift away from the more productive shorter chains to less productive longer microbial loop processes. As a result, there will be significantly less carbon export to the deep ocean. In the upper figure, one of the primary competitors of Labrador Sea diatoms is shown in blue, Phyocystis. As the Labrador Sea has warmed, these flagellates have become increasingly dominant. Diatom adaptation, preliminaries. Diatoms are among the most rapidly evolving eukaryotes in marine ecosystems. This is largely due to their short generation times. They may undergo multiple divisions per day. Their genomes are remarkably flexible, a result of secondary endosymbiotic evolution. When a heterotrophic eukaryote engulfed a red alga and later integrated into a plastid shown in figure 4. While diatoms are eukaryotes, they can engage in horizontal gene transfer, a way to rapidly exchange genetic material. The ability to adapt and tolerate higher temperatures of up to 1 degree C has been observed in a species of diatom in the Baltic Sea, located in approximately the same latitude as the Labrador Sea, Skeletonema marinoi. Due to their metabolic plasticity, diatom adaptation may be modeled by integrating CESM2 marble with the new genomic sequencing. The figure on the right shows a compact sequence of events that gave rise to diatoms through secondary endosymbiotic evolution. Plan of action A. Compare and analyze ocean color satellite data. Obtain compiled and carefully integrated chlorophyll A datasets for spring and summer seasons of the Arctic and subpolar oceans. The available data include coastal water color scanner, data obtained from Nimbus 7, the Nimbus 7 satellite, which captured ocean color data for the cold period from 1978 to 1986. This first ocean color satellite data provide a baseline for standing stocks and biomass of phytoplankton for the early 1980s, located near the inception of the accelerated sea ice melt period, which began in the 1990s. The CYFS from 1998 to 2010, Modus Aqua has data from 2003 to 2016, and PACE OCI has data from 2024 to the present, though the data has not yet been validated. 2. Compare the cold and warm periods of the satellite data and assess quantitative changes as far as possible, and assess how similar they are qualitatively and quantitatively. Note, there is a satellite gap from 1987 to 1997. Plan of action B. Compare the color ocean satellite data with CESM2 marble output. The biogeochemistry component of CESM2 allows for a flexible interfacing with the ocean circulation model, POP2 MOM6, to minimize the high computational cost. Of spin-up, use pre-equilibrated marble historical restart files in POSI. This is my first attempt to create a flowchart for performing simulations using CESM2 marble, so I'm not sure if they are correct. A. Use pre-equilibrated historical simulations, hindcasts of CESM's forced ocean sea ice for low and high resolution runs. B. Initialize from pre-equilibrated marble restart files to minimize the spin-up problem. C. Only simulate the upper ocean to reduce computational costs required to spin up the deep Labrador Sea to equilibration. D. Run standard multi-year repeating cycles of atmospheric forcing using the state-of-the-art Japanese reanalysis product, GRA55, to drive ocean sea ice modes and establish an approximate steady state in the upper ocean. E. Monitor the diatom phytoplankton functional type by initializing the momentum, heat, and freshwater fluxes using JRA55. F. track diatom biomass productivity and ecosystem stressors using the standard CESM2 biochemistry ComSet G1850 Echo or GIAF, which couples POP2 or MOM6 to model. Using the above procedures, 2 6-year low 1 degree horizontal resolution runs of the upper laboratory C would require approximately 25 to 50,000 core hours, whereas high resolution 0.1 degree runs would need from 1.2 to 1.5 million core hours. Thank you for your attention. Any questions?
Thank you, Christopher. Does anybody have any questions? I have one. How would you talked about how adaptation in diatoms can occur over fast timescales. Do you have any idea how you might parameterize that in Marble?
Let me try this. I read a paper by Gilbertson who specifically talked about trying to integrate next generation sequencing into global coupled models. And so I can't really speak much more to it than that, how to parameterize it. But that's kind of would be a further stage in the project.
Okay, thank you so much.
Thank you for the question.
Okay, next up we have Charlie Coven, who will be speaking about a comparison of regional climate changes under net zero and net negative emissions.
I'm sorry, could you repeat that?
Oh, sorry, we're just moving on to the next speaker now.
Oh, sorry. I have this feedback, which makes it hard to listen.
Okay, no worries.
I'm going to turn the volume up now.
Great, thanks. Yeah, so I'll be talking about a comparison of regional changes under some idealized experiments. And I first want to start off by thanking all this long list of people is using the flat 10 MIP simulation. So a lot of people from a lot of Earth system modeling centers around the world. Okay, so the basic question I want to ask is, so we're in a world in which we are currently failing to keep global warming below 1.5 degrees C, which is our most ambitious climate target. Who knows what's going to happen in the future, but there'll be, there's sort of a desire to know, like, okay, well, if we pass a given climate target, then what? Is it just like, it's just the rearview mirror, we don't think about it anymore, or are there ways to get back to it? And as I talked about on my talk on Monday, the Transit Climate Response Scheme of CO2 emissions implies that, like, if we get to net negative emissions, then therefore global mean surface temperature should reverse. But the whole TCRE framework only applies to the global mean surface temperature, and there's obviously a lot more to climate change than global mean surface temperature. And so the goal here is to ask, so typically when people talk about carbon dioxide removal or trying to exceed and then get back to a given temperature level, then this question of, well, obviously there is more to global climate than global mean surface temperature, but and so it'll certainly be different than before we went before we we're at that warming level to begin with, right? If you're at a warming level and then you exceed it and then get back to it, certainly things will be different. But the relevant question isn't, or that's part of the question, right? Is how do things compare to what they were like beforehand? But the sort of more relevant counterfactual is, well, what if we had actually stopped warming at that point and then still allowed time to occur? Because there's two different things that happen under an exceedance and return, which is one is that you exceed and return, and the other is that the time happens. And so you need to kind of separate out the time part from the exceedance and return part. And so the goal here is to use these flat 10 MIP simulations in which we either exceed and then return following this green line versus a situation where we stop at a given global warming level under the blue line and then compare to the point where the green and blue lines re-intersect 100 years later. And that way you can separate out the sort of the unforced time response under zero emissions from the forced exceedance and return response that also happens over the same time period. Okay, And so just to walk through some of these responses. So first of all, on the top row are the temperature trajectories of each of these models under these various conditions. So the key thing is that the TCRE proportionality that I talked about on Monday holds that under each of these three cases, global temperatures for that model are roughly proportional to the cumulative CO2 emissions in those things. And the bottom shows is the change in precip. And the key thing here is that the precip is basically following the first order is following temperature. The models that warm the most also have the biggest change in precip, and it has a similar shape. But it's not exactly following. And so if we actually compare if we plot the two of them against each other, in sort of like Helden-Soden space of change of precip as a percent versus the change in temperature in degrees C, what you see is that under this, the black line is the flat 10 experiment where transient warming the whole time. So you can see there's the kind of this slope that you'd see somewhere between like 1.5% and 2% per degree C slope that you'd expect. Whereas under net zero, under these blue lines, you see this kind of offset. And then in the green lines, which is the carbon dioxide removal after net zero, its offset has been effectively the same slope, but it has kind of the same offset that you see under flat 10 MIP. That after net zero, the precipitation just continues to increase. And so there's the key is that over time you get this change in the relationship between precipitation and warming, with higher precipitation for a given temperature after net zero than during the transient increase. Okay, so and all the models show this, right? All 10 of these show they have different slopes, slightly different offsets, but they also qualitatively the exact same response. So it's a very robust feature of the climate system. Okay, so what's going on here? Basically, it follows just like from the basic theory of that for the same reason why the zero emissions commitment is approximately zero. So the reason why the zero emissions commitment is approximately zero, which I was talking about on Monday, is that over time you get this shift, right? But prior on the left-hand side, you can think of the atmosphere as having kind of two heat sinks, right? The deep ocean during the transient warming, the deep ocean is cold, and so the atmosphere is trying to warm up the deep ocean, and so the atmosphere is losing a lot of heat into the ocean, and it's also losing a fair amount of heat into the atmosphere. After net zero, the CO2 concentrations are going to decrease, so the atmosphere becomes radiatively more transparent, but also the deep ocean is warming up. So the atmosphere loses less heat to the deep ocean, but because the deep ocean is warming up, but because the atmosphere is more radiatively transparent, it's and the key thing is the temperature is effectively the same, and so it's losing more energy to space. And because the precipitation is limited by the amount of energy you can lose to space, the two sort of follow each other. That you have to have more precipitation because that's what delivers the energy to the upper atmosphere that then allows the radiative energy to space. So the key thing is that like the reason why the temperature, the precipitation is going to be higher for a given temperature after net zero is exactly the same reason why the zero emissions commitment is approximately zero. It's this shift in the energy balance from the atmosphere, from losing energy to the deep ocean to losing more energy to space, and it's going to be accompanied by increased precipitation. Okay, so that's sort of like, that's the global mean precipitation. What about some of these regional responses? So here are showing maps of regional responses of the temperature, or global responses, but regionally differentiated. On the left, the zero emissions response. So basically, year 200 of the zero emissions minus the point at which the two trajectories diverge. In the middle is the exceedance and return response of the same year minus also the point at which they diverge. And on the right is the difference between the two of them. And some models show like a relatively similar response. And I say the hatching is basically places that are not statistically significant based on 1,000 realizations of just random, picking two random 2-decade periods during the control run and differencing them. And so anything that doesn't fall between that falls between the 5th and 95th percentiles of that, I'm hatching out here. And so some models like CESM show kind of a similar response. And actually, this is the response that I was expecting, is that because if you exceed and return, you're going to have lower CO2 concentrations than under zero emissions at that point, that you'd kind of expect to see more like a stronger ZEC response under this exceedance and return. And so you'd see sort of a qualitatively similar pattern. So, and in some cases that you do see that, although on the right-hand side, the magnitudes are large enough that they're kind of, you can see them on the same color bar as each of these regional changes under either net zero or exceedance and return. Other models do something completely different, right? So the GFDL model, you get warming at high latitudes and low latitudes under zero emissions. You get cooling under high latitudes and under exceedance and return. And so the difference is, this mass cooling, right? So If you actually look at all of them, again, there's just very little consistency across the models and the nature of the response. Some models warm in the high latitude, some cool in the high latitude, some some have hemispherically asymmetric warming, some don't. There's basically no agreement across the models in the nature of the response to either of these things. And if you look at and again, sort of unsurprisingly, if you look at the ensemble mean of this, what you see is that there's almost no agreement, right? There's some suggestion that maybe you get a warming under zero emissions on the North Atlantic, and maybe some warming in the Southern Ocean, and the difference between the two of them is maybe a bit more. Under exceedance and return, you get maybe a little bit more warming under over the Southern Ocean, a little bit more cooling in the equatorial Pacific. But it's basically the models are all just doing their own thing and telling totally different stories. Okay, but what's interesting is that if you plot for any given model the exceedance and return response versus the zero emissions response for each of the grid cells, what you see is that for the most part, there's a decent correlation, and the ensemble median correlation here is about 0.5, even if you just take the one-to-one line and don't do a regression. So it's actually a pretty similar regression between, or R-squared between a linear regression and the one-to-one line. So what that says is that about half of the variance that would happen if we exceed a global warming level and then return to it is also going to happen just over time under net zero emissions. That there is going to be some additional regional temperature change. We don't know what that is, and about half of it would happen even if we didn't exceed and return, just by under zero emissions, holding things constant. All right, so for precipitation, the story is even less clear. There's less agreement, but both for a given model across the cases and across models. So, for example, here's CESM showing under zero emissions, showing a reduction in precipitation in the southern Pacific, in sort of a hemispheric asymmetry, slightly more precipitation in the northern tropical Pacific. Under exceedance and return is the opposite, where you get cooling in the northern tropical Pacific, and less precipitation in the northern tropical Pacific, more precipitation in the southern tropical Pacific. In the western Pacific, the model does agree that there's kind of a reduction in precipitation in both cases. And so, this is, sort of strongly divergent pattern in the difference between these two cases. UKSM, on the other hand, also has a totally different thing, but the opposite hemispheric sign of an increase under zero emissions in precipitation in the southern hemisphere and a decrease under exceedance and return so there's basically even less agreement. And I'm not going to show you the giant all the models against each other because again there's just very little pattern. And the key thing is, there's maybe some suggestion that this increase in precipitation, we know that there's going to be an increase in precipitation globally, and maybe it's going to be, at least under exceedance and return, going to be centered over the southern Pacific, or at least the southern hemisphere, under exceedance and return relative to zero emissions, but it's not at all clear. Okay, so then the question is, okay, so is this just like the signal noise here is not great? We've only got a single ensemble members for this. It's a subtle signal we're trying to pick out. And so, how different are any of these responses from just random variation in the PI control room? So if you just compare the variance, and here I'm showing for the precipitation, just the total global variance in grid cell level temperature. So the histogram shows that just a bunch of random two-decade period differences from the PI control run, and then the vertical lines are each of these experiments. And kind of what I expected was that the exceedance and return response would be off to the right in each of these cases, and in some cases that is. In other cases, it's not. In other cases, it's actually the zero emissions response is the most different from what you'd expect to see based on just noise. And in some cases, it's actually the difference between the two, which doesn't make any sense to me at all. So point is that there's just a high degree of noise here, and there's really very little that we can say about what any of these regional temperature changes or precipitation changes might look like under either net zero, or in particular, the difference between net zero and this exceedance and return, and therefore the consequences of failing to keep global warming below a certain level and then trying to return to it. Okay, so the conclusions. So stabilizing or reversing global mean surface temperature does not mean stabilizing or reversing global precipitation or regional temperature or precipitation. the global mean precip will be systematically higher. The one thing we can say for sure is the global mean precipitation will be systematically higher for a given temperature after zero emissions than before. For the same energetic reason that the global zero emissions commitment is approximately near zero, because of the shift in the energetic balance of the atmosphere from instead of losing energy to the ocean to losing energy to space. CESMs show really wide diversity in the responses of regional climate under both these experiments. But for regional temperature change, at least, about half of the regional variance under this exceedance and return would also happen under zero emissions. And for regional precipitation changes, the difference between the two responses is larger, but it's also less clear what those changes would be or whether they would even be any more or less different between this exceedance and return versus under zero emissions. So I'll stop there.
Thanks, Charlie. Does anybody have any questions? We have plenty of time for questions.
You characterize the sort of the difference between the sort of the climate change you're getting from, getting to the peak value versus the differences you're getting between the two different pathways on the way back, like just to put it in the context of whether this is something that people are going to.
And I've specifically chosen points that should have the same global mean surface temperature or same global mean surface temperature, right? So yeah, I guess that's a good question, right? So how big are these changes versus the forced response? They're all small compared to the forced response, right? The forced response is the major thing, right? And the point is these points are specifically chosen to have what should be approximately the same global mean surface temperature. And the change in global mean surface temperature is going to sort of dominate most things. But beyond that, we know things are different. We know in particular the relationship between temperature and precip is definitely going to change over time. But beyond that, there's very little we can say.
This is always great to see. I'm wondering about AMOC, and like we see this slowdown in AMOC in a lot of our simulations, and that sort of like the heat transport's associated with that, and then the non-recovery of AMOC.
Yeah.
That's sort of I guess more an energetic thing, but much more of a sort of a circulation thing.
Yeah, and I didn't get into this here. Some of the models show that, right? I think that's what's going on with the GFDL. Why you see the warming under net zero and the cooling under. The cooling under net zero and the warming under exceedance and return is that the exceedance and return is associated with the re-strengthening of the AMOC, right? So I think, but I haven't gotten into that yet. Yeah.
Curious, with the multi-decadal variability that made it hard to disentangle the signal from the noise. Some of those histograms were really wide.
Yeah.
Do you think it's like the carbon cycle is adding more multi-decadal variability?
Yeah, I'm not sure. Yeah, that's a good question. I've noticed that as well, and I don't. Yeah, the implication would be that there's drift in the PI control, right? And
adding some new oscillation or something.
Yeah, it's a good question.
Okay.
It's the CNRM model that shows the widest histogram in the PI control. Yeah.
Cool.
So I need to look into that some more.
Thanks.
Yep.
Okay. Thanks, Charlie. Next up, we have Holly Olivares, who is a NOAA UCAR postdoc, global change postdoc. Yes. And she'll be talking about source or sink solar radiation management and ocean carbon uptake. Laser pointer, you have to point it when it works. It's kind of there. Okay, then this is to advance. Okay, thank you.
Hello. Thank you for staying. I know this is a quiet group, but it's also the end of the day, right? Day 3. So Cartoon Me says hello as well. So as Kristen mentioned, I'm a NOAA Climate and Global Change postdoc here at UCAR. And my mentor is Natalie Freeman at NOAA's Physical Sciences Lab. And here, Cartoon Me is looking at future carbon uptake consequences if we decide to dim the sun. And as I'm sure you'll agree, we've got to consider the consequences before we take any action. And the intention behind solar radiation management, as you've heard today already, is to limit the amount of solar radiation reaching Earth's surface while society finds the means to cut CO2 emissions and scrub CO2 from the atmosphere to achieve a more stable climate. And so today I'm going to present on a proposed strategy, stratospheric aerosol injection, which is in the modeling stage. And I want to say, as I continue to say, there's not a lot of research that's been done yet from oceanographers and biogeochemists. And so we welcome you into the fold, because my concern is that we aren't going to have the published research to show possible harmful consequences. And the ocean is not the little guy in this scenario. So that's that. And so feel free to reach out anytime and we can talk more about that. You probably by day 3 have heard about SAI, so I won't get too much into it, but I found it interesting. It would be about 5 to 6 million tons per year of sulfur dioxide being injected into, above the weather into the stratosphere from airplanes. And I'm using the ARISE simulations that are in CESM 2. I've spelled out how we got to the acronym, but I won't read it. Also always want to say that the climate interventions that are being considered right now are not a replacement for the elimination of burning fossil fuels, and that SAI, or stratospheric aerosol injection, is not the solution and definitely not a long-term solution, and I think that we're all in agreement about that. But if mitigation happens too slowly, then this research is under the category of risk reduction. And so the idea is that solar radiation intervention would be a temporary measure to reduce the risk while we're ramping up CO2 removal. And this figure is coming from Zarnetsky et al. In 2021, with time on the x-axis, temperature change on the y-axis. The red curve is representing high emissions, the black curve representing cutting emissions, and the blue arrows represent solar radiation management, or SRM. A temperature target is along the blue horizontal line, and the gray curve is for CO2 removal. And the area under the gray curve that's shaded in red signifies overall risk in this manuscript for ecological systems. So if we cut emissions, which is the black line, and we deploy SAI, the idea is that it could temporarily shave the peak of the most severe temperatures. Those are the blue arrows on this figure, while a large-scale system of carbon dioxide removal is built, and ultimately for the long term, cutting emissions and CO2 removal would bring us back down to that defined temperature target. And so I want to mention again, even if we do intervene, or I guess not again, I will be saying it several times, even if we do intervene, the concentration of CO2 in the atmosphere is unaffected. And so really nothing replaces the ending of burning fossil fuels. And I say it again and again because I've been in this community now for about 2 years, in this research community, and a lot of messaging from the public is, oh, somebody found a fix, so we don't have to change what we're doing, and that's absolutely not the case. And so I think it's really important that we continue to convey that message when we're having even informal conversations about climate interventions. Okay. Oh, I went too far. Go back. No? Okay, so now I'm gonna show you, I was going to show you where the injection points are. They're all along one latitude in the Pacific Ocean, and location matters, as in everything. So maybe my slide will show up at some point. But here I want to show sea surface temperature. It's something that we can all identify with. This is from 2015 to 2100, and temperatures in degrees Celsius on the y-axis. The blue lines that span the graph represent CMIP 6 SSP 2-4.5 scenario, which is the middle of the road scenario, meaning emissions continue to climb and they decline mid-century. I also call them, and then the blue lines are representing, I got myself confused. The blue lines are representing SSP 2-4.5. I also call that the if we do nothing simulation, so you'll hear me say that too. The red lines, which run from 2035 and wrap up in 2069, are for SAI, or stratospheric aerosol injection. Excuse me. And they're working to maintain a desired temperature near 1.5 degrees Celsius above pre-industrial value. There are 10 ensemble members for each simulation that are identical, with the exception of the intervention not being included in the blue curves. And the thin lines represent unique responses to both scenarios and include natural climate variability. And the thick red and blue lines are the mean of those ensemble members. And there's 2 studies ahead of mine that I was able to find agreement with what I'm showing here, so I feel good about that. And so the possibility of lowering global mean temperature as well as sea surface temperatures like we see here is part of why researchers continue to study this intervention, if possible, that if dimming the sun could reduce the risk of extreme events and tipping points. And so I'm using these simulations to study the impacts on ocean biogeochemistry, specifically the ocean as a carbon sink. So to orient you as to what we understand about air-to-sea CO2 flux, I'll get it. I wanted to show a trends map for 1982 through 2015. I created this in CESM2 as well, but it is in agreement with multiple observational products that are out there worldwide. So feeling good about the model being able to recreate that. So here the combination of blues and reds show us the ocean is not a one-way sponge. Some regions absorb CO2, which are shown in blue, and then there's other areas that are upwelling deep water and releasing CO2 into the atmosphere, and those are shown in red. And so a few key principles to know about air-to-sea CO2 flux are that the ocean's ability to pull CO2 from the air is what keeps our planet habitable. The ocean absorbs roughly 25 to 30% of man-made carbon emissions, and this process acts as a massive climate buffer, slowing global warming, but it simultaneously also fundamentally alters the marine chemistry, causing ocean acidification. And then next, flux is driven by both temperature-based and biogeochemical and physical components. And scientists track how that trend has been changing over time, and so that's what I'm showing here. So this kind of helps us get oriented as I show what the future has in store according to CESM2 under SAI. It's like skipping 2 at a time. Oh, we're going the wrong way. There's all my slides. Okay, we can go home. Let's try it again. No, it's skipping past 1. Okay. Well, basically what I was going to say was, as I go through my results, more carbon into the ocean means more acidic waters, which is a bad thing. And less carbon in the ocean means more carbon in the atmosphere, which means continued global warming, which is a bad thing. So we've got some issues that we're going to be working on, and I'm glad that you're all here so that we can keep having these conversations. Okay, so looking again at the same figure that I showed earlier, we see with the red line, there's an immediate response in the model once the injections begin in the year 2035. That red line is not messing around. And again, that's why this intervention is getting attention. So there's a positive. Let's look at what else happens under this. And so then we look at the CO2 flux, which I'm going to put in the bottom half of this slide. Sorry, I think my brain is a little mushy too at this point. So the bottom half of this slide is now showing air-to-sea CO2 flux. The units are in petagrams of carbon per year, and I've placed an arrow to remind us all that larger negative values means carbon going into the ocean. And so the entire blue curve represents a carbon sink. They're all negative values. And the red curve also shows an overall carbon sink for the duration of the intervention. So that answers my big question that we will remain a carbon sink, which is a good thing. And then in calculating the cumulative change over the injection period, SAI increases the global ocean sink by by 0.09 petagrams of carbon, which is pretty tiny considering that currently the ocean takes up 2 to 3 petagrams of carbon per year. And then I also want to mention the blue curve in the lower panel for the period of 2070 through 2100. My impression of what this is that the flux's response to the sea surface decrease kind of boosts the flux trend initially, but once the emissions dip down in the simulations mid-century, the uptake decreases here where you see that curve rising. Flux is driven by the partial pressure of CO2 in the atmosphere. So I want to point out again, reducing emissions is really the key here, if there's one takeaway. And today I'm only showing sea surface temperature and flux, but please remember temperature is not the only driver of flux in the ocean. And so going forward, I'll be looking at both thermal and non-thermal possible drivers of the response for SAI. So now that we've seen a global time series, let's look at the response as a spatial distribution. Yep. So the map on the left represents sea surface temperature's response to SAI if we do the intervention. The map in the middle represents the if we do nothing simulations during the same time period. And these are the ensemble means of the final injection year minus the first injection year. I think that's important to point out, and we'll probably have a discussion about it. The grays in the color bar represent a decrease, and the reds represent an increase. And then the map on the far right is the difference of the map on the left minus the map in the middle. So this is an obvious response, as we saw in the time series, that there's a dampening of the warming of the SSTs due to anthropogenic climate change. That's why the middle one is so red, right? So now let's look at flux. So here, this is in the same format as the last slide, but the purples are representing either increased uptake or decreased outgassing, depending on location, and the greens represent decreased uptake or increased outgassing. And I know I'm saying a lot of either ors, but that's what we're dealing with flux. And once we start to get to know what typically happens regionally, then we can identify which is which in terms of increases and decreases. So for the map on the far right, we see something very different than SST. We see a mix. And so that, of course, leads me to want to look more regionally. So I'm going to start with the Equatorial Pacific, the ENSO region, and specifically the Nino 3.4 box. So I've placed a box over the map on the left and then printed out a time series to represent what's happening in that box. So and then also wanted to mention, I think I failed to, that the shading for both of the colors of the lines in the time series is representing one standard deviation from the ensemble mean. So looking at things this way, we see that most of the SST variability during the injection period falls close to the variability for the blue curve in the region. And this matters because Nino 3.4 is part of a climate index with incredible influence on global weather and climate. So then let's look at flux. Now in the lower half of the slide for the same region. So the time series shows an overall decrease of outgassing in the region, whether we do SAI or not. The SAI shading also shows increased variability over the if we do nothing shading. And this means a lot to me as I decide if I want to home in more on perhaps the last decade of the simulated intervention for in-depth analysis, or maybe a different decade. If I look at the 2040s or the 2050s, I'm going to be telling a different story. And so that's one question I have for those of you that have been looking at these simulations is a good way to look at these that kind of makes sense in the way of storytelling. So then I want to look at the subpolar North Atlantic region. Also caught my eye when I looked at the global map. So starting with sea surface temperature, we see that now familiar decrease in temperature and an even steeper decrease in the region if we do SAI. And then looking at flux, in the bottom half of the slide, we see a decrease of carbon going into the ocean, whether we do SAI or not. So in summary, I know I'm kind of doing a high level over this, but also it's the end of the third day. But I'm happy to keep talking about it. I'll be presenting this at the Gordon Conference next week, which is on climate geoengineering. and expect to get a lot of really good feedback there as well. And I think so far my message is location matters and injection location matters. When I first started doing this work, I noticed a lot more response in the Pacific, which is where the injection points are, and I know that there are others that have already published papers talking about location matters, so that's definitely going to be in my awareness as well. And then just to emphasize the ocean's ability to pull CO2 from the air keeps our planet habitable. That's why this matters. Under SAI, the atmospheric CO2 concentration does not change. Please remember to include this if and when you hear people hinting that something like SAI means we don't need policy or social norms change. With or without the intervention, the global ocean remains a carbon sink. This is a relief. But it does not mitigate ocean acidification, and this is a critical process that we've got to address. And then regional responses will be my focus going forward. And then, as I mentioned earlier, I plan to perform a decomposition of thermal versus non-thermal drivers, and I plan to quantify the cumulative trend and then possibly choose 1 decade of the intervention period for more in-depth analysis for a manuscript. And finally, I welcome any suggestions from you. Thank you very much.
Questions for Holly? I have one. Do you expect ocean acidification to get worse with SAI than without it?
I have done some work on aragonite saturation, which is kind of how we measure ocean acidification, and I don't see that SAI has an impact on it either way.
Okay, because I would expect it to be cooler and then you absorb more, but it doesn't.
Yeah, that's been a common thread, a common conversation, but the path for change in aragonite saturation isn't directly related to temperature. It's indirectly related. And so it's a little more zigzaggy. And so far from what I've seen, SAI does not impact ocean acidification at all. Alrighty, thank you all.
Thank you.
Oh, Dave.
Yes. Plenty of time.
Wondering about how you frame this. You talk about a lot about the framing, and so these results sort of show it's not, would you agree, not super concerning, like the system's still behaving and it's taking up CO2, in fact, maybe even taking a bit more. So that's good news. But did you flip it around, or have you flipped it around, or should we be flipping around and saying, what level of change would we concerned that we saw that much change, and then we say, yeah, no, that's a problem. Or how much time should we be spending on that versus
good
just
question.
Probing without thinking that ahead?
Yeah. Well, I think globally we can say it doesn't do much, or maybe there's even an increase for a time. That red curve for flux, just by the end of the intervention, it's back up where the curve is if we do nothing. So I'm very curious about what happens in a longer simulation, which, thanks to Peter, I will be analyzing some new ensemble members in CESM too, once I finish this project. But regionally, I do think that we're going to find some issues. I keep going back to that equatorial Pacific and then the subpolar North Atlantic, and then some in the Southern Ocean too, which I haven't really looked at yet. And so I guess stay tuned. I'll send you an email.
Hi, Holly. Have you looked at the changes to primary productivity and community composition yet?
Not.
Okay.
It was on the list when I was looking at aragonite saturation, but then I had to kind of shift my focus over to flux. But it's definitely worth spending time on. So I will keep that in mind. Thanks. All righty.
Thanks. All right, so that is the last talk. If there's any additional discussion or questions for any of the speakers that we had today, then please do that. Otherwise, we can take the break early. Okay, that's fine. That's fine. That's totally cool. Everybody's a bit tired, I think. So I'm supposed to remind you all, if you have a poster, to take it down, otherwise it'll get thrown away. So, take it down before you leave today. And okay, that's it. That'll wrap up the BGC working group.
I'm not sure. Just
started. This is the new format we've been doing over the last few years is to make this a pretty informal question and answer or comment session. But I do have just a couple remarks before we get into that. First, I just want to say thanks again. So it's a lot of people who work really hard to make this workshop flow, and in particular Elizabeth, as people. I didn't mention this specifically, but the CGD admin team, Kaylin, Daniel, Kayla, Teresa, and Bonnie have all helped out, and I hope I got everybody. There's probably others doing stuff as well. Yep. We've been doing this for a long time, and then every year there's new challenges. So I'm sure as Elizabeth can attest. So it's fun though. It's really fun, and we really appreciate NSF's support, allowing the early careers and to allow us to put this event on. And then of course, multimedia and event services are constantly working all the time, dealing with all the technical issues, complicated things from people around the world, and dealing with some stuff that is maybe not as modern as it should be. We're hoping that can change in the near future. So really want to thank the multimedia services for dealing with all the things they have to deal with. So. And then I really want to thank all of you. Here's our photo from this year. I've had many people come up and be, as we do most years, thankful for the opportunity to be here at the CSM workshop. I think there's a lot of great things about this workshop. I obviously am biased. Been coming to this for 20 plus years, but it's really it's the opportunity to see how the work that we're doing can feed into something bigger. And this year we just did the quick count, over 210 plus presentations, pretty impressive, from 150 different institutions. And so, some people have said, boy, this meeting is it's a lot, it's intense, there's so much science. So if you're trying to understand why you feel like you've had so much science thrown at you, I mean, this is why. There's been a lot going on here. But, we are open to some comments about how we can make improvements. It's hard to know. We've definitely think about this every year in time when we're trying to fine tune. So we can get a chance. You can weigh in on that. But anyway, it's exciting, to see we still have that amount of engagement. And I also really want to thank the working group co-chairs and the cross working group session leads who organized their sessions. I think each session was fun, interesting, and had some great presentations, some unique perspectives. And for example, I really liked the storytelling. That was really fun to have that kind of different thing. And sort of at the other side, you have the high resolution at the same time. And so all the things that we're trying to do all at once. And I know a lot of people wish they could be in each one of these. I know I did. It's unfortunate. They are recorded if everyone has the stamina to go back and watch all those. And another thing I want to sort of say in note here is that, in the background, of course, the CSM team is always working. And I know all you guys have other things going on in your own work lives and probably personal lives too that are going on around the side. But this year, you know, we're trying to get CSM3 ready, and I'm sure I didn't talk about it too much in my overview presentation, but I'm sure you've been hearing a few things about some issues we've been finding in the last few weeks in the spin up, and that were causing some, you know, relatively significant concerns, some, I wouldn't quite say sleepless nights for me and some of the others, but definitely some uncomfortable nights. But we've been working in the background, and we just had a meeting earlier today, and some of the new ideas that we've been testing look pretty like they're going to solve the problem that we are having. So it's probably not the last problem, but I feel like again today that we're on the right track and we're going to get a model released and be able to participate in CMIP. But we'll see. I made the joke like, I don't know, 2 or 3 weeks ago at lunch one day, and I said, I'm really looking forward to the day when nobody comes to my office kind of a little sheepishly talking about a new bug that they found. So I had gone, like at that point I actually had gone 3 days without that happening. And then it's kind of come back a little bit. But no, I am really hoping that we are going to get to this phase of no longer finding bugs. But that's probably not going to happen. We'll just deal with it as we always do. And I would ask people, anybody who's asking their AI assisted whatever agents to go out and look for bugs in CAM and CLM and MOM to just stop temporarily. But yeah, I have heard that people are starting to do that and finding little things. Anyway, so anyway, thanks. I think we have good news. We'll find out, and you'll hear about it, and a lot of you are participating. Just a few notes about upcoming events. Just a reminder, lots of tutorial events coming up. Please, if you have students interested, or you know people who might be interested in participating in one of these events, for especially the tutorials. And there's probably other events that I'm missing. Does anybody want to shout out an event, a CSM related event that I'm missing from this list? Okay, I'm sure there are some things. But anyway, hopefully there's other opportunities to be engaged. And then Elizabeth thought it was a good idea for us to announce the next workshop. So the next workshop, so you can, for your planning purposes, we've scheduled for June 14th to 16th. We do plan these out far out in advance, and we're actually working on the dates for the 2028 workshop as well, negotiating with MPAS. I think you also have a workshop around this time. So, but next year, June 14th to 16th, it's a similar kind of week, I think, around the this Juneteenth week. Is that right? Yeah. So so then we're here. I want to take the opportunity to get feedback. So we'll have a chance here to talk about feedback, but also in your, we're not doing a survey this year. We've done a lot of surveys over the last few years. I know people have survey fatigue, so no survey this year. I think we have a good sense, but if you do have specific feedback about ways to improve this workshop, we're happy to take them in this open feedback form that you got in your email today. So if you don't want to say something now about the workshop itself, please do. And it's not just a workshop, it's really now the opportunity for us to talk about the CSM activity in general. If you have questions, comments, or feedback on anything you heard during this week, or you have concerns about what CSM3 is looking like, are participating in CMIP. So this is where we get to open it up for anyone who has any questions or comments. Eric.
So Monday you talked of CSM, which I thought was really great. I appreciated all the ideas there, and hopefully they work out. It seems like something that's been a problem in the CSM development cycle is that after the release, we go back, each model kind of does its own thing for a while, and we don't really look at coupled results that much until a couple years in, and then we find lots of problems. Is there any thinking about that for this next cycle after the release is done?
Yeah, so that is true. That has been a problem in the past, and in talks that I have with more time, I'll note that we said at the end of the last cycle, we said one of the things we're going to try to do is couple earlier. I feel like we kind of did that this time. We tried a couple earlier, and my perspective is that it didn't help. In fact, it might even have hurt, right? That we started trying to couple before all the components were really ready, and then we were sort of dealing with some things that we probably didn't need to be trying to figure out at that moment. So I do feel like we need to do a postmortem and see if others feel have that same perspective. I haven't really tried to ask that question to the team yet, but that was sort of my perspective, was it didn't really help. So the way I'm thinking about it is that we need to be getting closer to more continual development. And so, it's currently just way too long, not even just like slightly too long. It's just way too long for us to really take it on. But if we could go from it taking effectively now years to get a coupled model version together, once we even have the components ready, to maybe a month or two, which is very ambitious, maybe a month or two is too short. But if it was 3 to 4 months, then it wouldn't be such a big deal. You would just say, oh, we're ready. So we're going to be talking about this more. A bunch of people are aware that Schmidt Sciences is putting out a call soon, and we'll almost certainly be trying to participate in that to spend some, to fund, hopefully, well, we'll see if we get any funding to spend some more dedicated time to it. Because the other thing I'll say is that I feel like the challenge that we continually have is that we are trying to learn better ways to do it in the middle of trying to do it for an operational reason. And that's a hard thing to do when you're trying to sort of think about a research activity to make a faster development cycle while also trying to put out a production model. And so it doesn't lend itself to progress very much. And so we did this cycle. We tried quite a few different things, but I was feeling like we'd kind of get a little ways there, and then something urgent would come up and we'd drop it. So I'm hoping we find the time to do something more dedicated. So we have started talking a little bit, just in a few small groups, about what we could use as a sort of not that important, but still worth doing test bed for this. So, something that we don't have the pressure that if we don't do it. So, and I think we should spend some time trying to think about what it could be. And, an example could be a low resolution version of CSM, or, but I don't know what it should be yet. We haven't 100% decided, but I think that's the way I would like to try to approach it. But I'm really open to ideas on this. I don't think it's going to take the collective wisdom of the people who are in this room to figure out how to do this. So, yeah, good question. And also, we have some people who can pass around mics, so if you don't have to necessarily get up, you can just raise your hand if you have a question.
So I really hate to raise this, but now we're transitioning from developing the model to using the model. Is there any thought about how do we go back to a human dimensions type working group where we start thinking about, because there's been a lot of really good talks in terms of climate interventions and impacts and storylines. And it seems like there's a really natural sort of grouping there to bring people who want to use the models to answer questions that are really societally relevant. And also, as we go into CMIP 7, like the new scenarios coming on board, being able to understand what they mean in terms of using CSM.
Yeah. So the simple answer is I think to a working group in the near term. I don't think we would be able to get the buy-in, whatever, from leadership to take that on. So what we've been doing, and you've probably detected it already, is trying to have these cross-working group sessions, provide that sort of opportunity. So it's not necessarily a standing working group, but it's providing a touch point every year, at least within the CSM annual meeting context, where people can come in and who want to do something like creative, like a storytelling that might not have fit into some other session. And so I think I'm almost certainly we're going to keep doing that. And so we're open to ideas. I don't know if John has any perspective on this as well, but that's been the strategy we've taken over the last few years, and I don't see us changing in the near term on that. So keeping the ideas alive through a slightly more informal way. Any early careers who have been here for the first time who want to share a perspective on their life? That's totally putting you on the spot, but not a specific individual. Thank you.
Oh, God.
Yeah.
Drink in hand. Hi, I'm Leo. Early career, second-year graduate student at the University of Wisconsin-Madison. This is my first year coming to the workshop. I don't know that I could have asked for a more positive learning environment. I think every interaction I've had with the people I've met here has just been really, really positive. And I think that's about it.
Yeah, super good to hear. Thanks for sharing. I've had several people say that to me personally. So we get that every year, and that's one reason why we put a lot of effort into this, is because we do get those opportunities to create these new connections. And one thing I forgot to mention in these sort of wrap-up remarks, but one thing that Elizabeth is working on is ways to, in this current environment, we are getting asked more and more, probably appropriately, to try to quantify and characterize the impact of CSM. Why do we need CSM? And so, I've spent a lot of time. Others here spent a lot of time trying to figure out ways to do it. It's not, it's not easy to do, right? Because it is a kind of a diffuse. There are very specific things. You can count citations and you can count the number of people coming, but a lot of it is this. Things that are hard to quantify, like helping people build their careers, right? Finding a place where people can find a community to get involved in and to learn from people with a lot of experience. And Earth system modeling is science is like this in general, but Earth system modeling in particular, requires this. Like it's such a hard thing to do. You kind of need to learn from people who've been doing it for a while. It's very hard to start from scratch without any sort of mentorship. And so that's a really important thing. So Elizabeth is going to spend some time, I think, over this year to one of the things we're trying to do is track the impact of CSM, our tutorial, and like award winners and people who, first-time attendees to the workshop, and trying to see if we can see anything in data that shows how the careers are being impacted. So Elizabeth has some ideas. I'm not totally sure this is not going to be trivial to do, but I think it would be really impactful. So it's nice to even hear some stories. And we definitely see that, if you look at the list of the award winners over the past years, they're usually still involved, which is a good sign. And I know Brian has talked about this. Brian Dobbins has talked about this a lot of times. To just quantify how many people are using CSM, and they technically know how to do it. I think they could, we can see how many times that GitHub clones, and it doesn't really tell you what's happening. And so we could technically put in something that would allow you to opt in and say that you're willing to be tracked, every simulation you do. I'm not sure exactly, something like that, right, Brian? And so I think it'd be nice to do. It's just, it's like we've always thought that putting out a model is more important than this technical thing, but at some point that becomes not true anymore. So, Brian, you want to?
I will say this is, we're not evil. We're not, going to track you. What we can do, and there's benefit both to NCAR, is we could instrument CSM to report anonymous usage statistics of the value to us is both independent users, but the value to you is if we know what comp sets you're running, what resolutions you're running, we can tune better for that. If we know how you're using the model, we can focus our software engineering resources and our science resources on making that parts of the model more accessible. So this is something like, again, if you're like, oh, hell no, I opt out of all cookies on browsers. I hate any sort of tracking. But if this is something you have concerns about or you think would be helpful, let us know. We just want to make sure that we can focus our resources in a way that, well, A, that we have resources, that's from NSF, and B, that we can focus them on the way that's most effective for the community.
Else? How stressed out are people about CSM participating in CMIP? Or not? Besides me.
You just said the C word.
Yes.
you know, CMIP has been kind of a North Star for us for X decades, but this year really is the transitional year, I think, in terms of what does it mean for the endeavor to have a CSM release, knowing we have all these, you know, machine learned versions or hybrid modeling and a lot of high resolution activities. And I'm wondering what you think about what will we look like, what will the landscape look like for CSM as an activity moving forward? It's extremely organic and it was really hard to pin down, or do you see us still having a kind of on some kind of highway, I guess?
No, it's a great question. Yeah, it's a very good question. Yeah. I guess it's hard not to think that things are going to become more dynamic. It's just the way things are, the way the winds are blowing, and so you know, I think we're trying to think about how to sort of not manage it as much as just like still keep it coordinated and useful and not splintered into a million pieces, which I think has some potential. So, with the new tools, right, you can kind of create things very easily now, and there's the potential that somebody could go off and try to create their own model from scratch or from whatever, from a baseline, and is that like a threat to CSM? I actually think it's probably not as much as a threat as it feels when you first hear it. It's because when you come to this meeting, you kind of realize how much like knowledge is required to actually understand everything that's happening together. So you could technically build something probably, but the ability to build something that actually does something meaningful is going to require a team. And so whether that's us as a software engineering teams or scientists writing code from like we used to, in Fortran, or whether it's going to be something where you just say, hey, introduce this parameterization into, you just tell Claude to introduce this parameterization into CSM and it does it. Who knows what, I know Brian doesn't believe but who knows what's going to happen, right? The technology is changing. I think nonetheless, you're still going to need to have the group of people like this team here to be able to like make sense of what it all is. And so, yeah, I guess I just see a slightly more dynamic, maybe faster paced things, but I think you're still going to need the core team. And as I showed in my opening presentation, one of the first slides I think I showed, it's this sort of terrible AI generated image of the CSM ecosystem, and that ecosystem, the software itself is just one piece of it, really important piece, but it's really it's the people, it's the simulations, it's the clever ways of analyzing that it's going to have to be it's going to continue. So, but yeah, it's an interesting time for sure to be in nerve system modeling for lots of different reasons.
So I mean, maybe what all of this kind of emphasis on machine learning and all the different ways that you can go about doing modeling these days really kind of creates as a need for some introspection and reminding yourselves, of, what really is the purpose, in a certain sense. Because I can create neural networks that emulate things exceedingly well, but if the purpose of the model is to serve as a tool for doing science, then it's not the quality of the simulation that matters at that point so much as the extent to which you can actually do a meaningful geophysical experiment with that model. I mean, an example would be, you could have an emulator that does a really bang-up job on low clouds, but if there's nothing in the architecture of that neural network that allows me to tinker around with the Toomey effect, then I can't do aerosol cloud interaction experiments. And so there's some limitations to that version of the model, even though, if it runs 1,000 times faster, that might be the perfect thing to use for some sort of application space, climate impacts, climate risk kinds of studies. So, I mean, there may come a time when you really have to make decisions about, how to spend resources. And I would think that would be the time when you would really kind of have to think about, the priority in terms of, creating a tool that's useful for doing science.
Yeah, that's a good point, and that's definitely the way we're thinking about it, and DJ is going to comment on this too, I think. And just before DJ's talks, I think that's, if from the NCAR level, having this NCAR AI strategy is part of it, is sort of, maintaining a focus on the science while enabling these tools and helping the people in the community use the tools in good and creative ways is, the emphasis, rather than the race mentality of getting it the absolute best emulator that can crush everything else. So, and hopefully DJ supports that statement.
Yeah, I will say first, this is certainly something on our minds, in that we're not just after making a faster emulator for the sake of making it faster. We're thinking about how do you use all the machine learning tools, which isn't just like a neural network, but things like PyTorch and JAX give you the ability to basically do automatic gradient, automatic differentiation. You can plug in physics equations into PyTorch or JAX and mix it with neural networks, or it can be a whole physics-based thing in JAX, as there's already, like as Duncan's keynote pointed out, people are already building this stuff, and we see I think I see the future as hybrid, and being able to tie in kind of more scientific analysis-based pieces into this process, which could be in the form of your traditional, like, make a parameter change, but we can also look at other levels of abstraction, other scales, and do that within, like, basically composing these different systems together at different scales. And being able to run 1,000 times faster or whatever also opens up a whole new way of interacting with these models. We're starting to play with this in terms of, like, yeah, if you, not just larger ensembles, but also thinking about being more interactive. If you can make a perturbation and watch it actually, like, work through your system in real time instead of waiting for a run to complete, that opens up lots of possibilities, which we've only started, I guess, barely begun to explore. And that's, but we want to be able to work with the community to have the tools and make them easy enough to use, so that the next generation of students and the current generation of scientists can think about how they might start playing with them and see how they might use things differently.
Thanks, CJ.
I just wanted to add a little bit to both Eric's and DJ's. One thing that doesn't get enough attention is equation discovery using machine learning. There were at least a couple of talks which mentioned that, but that's one way you can use machine learning. I think very, very similar to how people develop parameterizations. I think it'd be nice to have more attention for that.
Yeah, there's a few projects in LEAP and Veronica's team with the ICON that have done equation discovery. I think I don't know if Veronica's not here, but it's not a silver bullet either. Then you have to tune that equation, and it doesn't just drop into things. But yeah, it's nice because you can then at least understand it. So some things lend themselves to equation discovery, some things don't. And certainly with the CSM machine learning enhanced version, equation discovery, we'll take that as if someone comes up with a good equation discovery process, that's within scope for sure with that. So we aren't trying to dictate, I will say, from the machine learning enhanced version, we're not trying to dictate how people decide to try to make a new parameterization. It feels like it's too early in the game here to be dictating. The one thing, just it's a bit of a side, the one thing we're trying to dictate, if we are, is to try to go through the FTorch framework if you're using, if you need to get to access to the Python, the PyTorch sort of, is to use that. So we're just being consistent there, so we're not trying to deal with multiple pathways. That's the only sort of thing we're trying to enforce at the moment. But, again, technology is changing quickly, so, but that's one constraint. Yeah, but good point.
I guess one of the things I'm going to ask is, like, when we talk about AI and we talk about machine learning, a lot about it is data discovery, about visualization, about being able to, we don't need to generate more data, we need to understand all the data we already have, right? We already produce huge amounts of data. So it's like being able to understand what we have already produced, the questions we've already asked and the simulations we've already done, or the ones we're going to be doing. And I feel like, we've done a really great job, and, like, Cupid and the ADF and the LDF and all those things are really good, but we need the resources to help the scientists be able to visualize and be able to analyze what we've already got.
Yep, totally agree. And the AI session sort of split into the hybrid modeling, emulators, and sort of analysis tools kind of naturally. We're definitely trying to keep our eye on all three, and yeah, for sure, totally agree. Anything else? John, anything you want to? Sure, yeah.
If anyone's got anything burning, they should say it now, because I like the last word. If not, then I just wanted to echo Dave's thanks to all the people that have helped put this together. The multimedia team, Elizabeth, and the admin team that have so fully supported it, and just say, thanks from me as well on that. But of course, Dave always forgets to thank one extra person, so we've done the working group chairs, and we said, oh, well, everyone's trying to build a new model, but who's leading building a new model, and then who's organising this meeting as well? So I think we should finish by thanking Dave for all his efforts and all of that.
All right, almost last word, John. Yeah, thanks everyone for coming, and really appreciate you all being here, and safe travels home, and yeah, we'll see you next time.